military man, any one of us, the considerations, the problems of atomic warfare are better understood today than ever before. Military participation in Operation Come the Member is a matter of record. Experience to be used for military plans of both warfare and future atomic testing. The Nevada Proving Ground is beginning to be an old stomping ground for a lot of the civil services. On Tumbler Snapper, as on Busted Jangle back in the fall of 1951, headquarters in the forward area is a boom town called Camp Mercy, lying some 20 miles to the south of the test area. This is the place for living, working, and any recreation you are able to squeeze into a very busy schedule. The Armed Forces machine for atomic testing was better oiled than ever before. Every element of that machine ran a good many long, hard hours, hot days, and cold nights to meet a rigid schedule of nuclear detonation. If you've ever been on an atomic test before, either here in Nevada or overseas at any WETOC, chances are you've made a good many friendships with people you see only once or twice a year. It's a big fraternity, this order of the mushroom, and it's growing all the time. As more and more of us from all the services have an opportunity to be a part of this big effort to collect the know-how for atomic warfare. We're still on the ground floor, but the ground floor is getting a little higher on every operation. There's no such thing as a normal working day on an atomic test. The labor pains continue around the clock until the job is done. Because ASWAP, the Armed Forces Special Weapons Project, is the joint service agency that plans and coordinates all of the military effects tests that are run on an operation of this kind, a special command, a test command, was created. Tumbler Snapper, as Busted Jangle, was a combination weapons development and military effects test. A total of 8 nuclear weapons were detonated. Most of the military tests were run on the first 4 shots, the tumbler phase of the operation, consisting of 4 daylight airdrops. However, the 4th tumbler shot did play a part in the AEC weapon development program. The snapper phase of the operation comprised the last 4 shots. The weapons themselves were installed in 300-foot towers and fired during the hours of darkness. Snapper was almost exclusively devoted to AEC weapons development. Since comparatively few military tests were conducted on Snapper, let's take a quick look at that phase first, before we get into the heart of our story. At this moment, the installation of a test weapon is being completed in the first zero-tower CAD. In the study of new weapons, like those on the Snapper phase, much depends on instrumentation in close proximity to the bomb itself. The internal workings as well as the external effects of the weapon are studied and cross-checked in many ways. The events taking place inside the bomb occur with extreme rapidity, in millionths of a second. An instrument located near the bomb in the cab of the tower must be able to work fast enough and capture enough data to accurately analyze the bomb's functioning before being destroyed. The record of the weapon's behavior recorded in the millionth of a second before it flies to pieces is sent back down the coaxial cable from detecting instruments in the cab to a recording station several thousand feet away. The weapon is in position and the firing circuit checked out, ready now for firing from a control panel back at the CP. The underlying philosophy behind the entire weapon development program is to realize the maximum kiloton yield from the fissionable material involved. In other words, obtain the highest degree of efficiency. However, equally important is the continuing development of different weapon types to provide complete flexibility in delivery methods and techniques. At the CP, scientific and military directors wait out the final few hours. Everything is in place. Everything is ready at the Nevada Proving Ground. each hour, the entire test site, all operations, the detonation of an atomic weapon over the Nevada desert, pivots around one focal point, the fortunes of weapons. Here in sequence are the four snapper blasts, detonated atop their steel towers on the 7th and 25th of May, and the 1st and 5th of June. The weapon ideas being proof tested on Snapper involve weapons of a smaller physical size that might be carried externally on fighter-type aircraft in tactical air support of ground operations. Every nuclear detonation is followed up by the priority operation of collecting samples of the unburned fissionable material and bomb debris. Atomic cloud sampling with jet aircraft, an idea tried on Buster Jangle for the first time, is standard operating procedure on Tumbler Snapper. The jets can get the required samples faster and with less personnel exposure. 2 men ride in the sampler aircraft. A pilot to fly the airplane, and a radiological safety man to help him locate and penetrate the hotspots in the clouds where the required samples can be gathered. The planes themselves are radiologically hot, very hot, because the skin of the airplane has collected bomb debris too. The problems of working with high levels of radioactivity are pretty well understood by this time. The safety precautions have been proven and defined in the course of literally dozens of cloud sampling sorties on previous atomic tests. The approach is realistic. The hazards are understood thoroughly. The cloud samples themselves are collected in wing-tip snippets, specially designed tanks suspended from each wing. Inside the snippers, chemically pure paper filters are installed to latch onto and hold particles of bomb debris the plane encounters in its passage through the clouds. The operations are simple and literally eliminate the possibility of any serious personnel radiological contamination. All post-blast recovery of sample papers, as well as decontamination of the planes, will take place here, at a safe distance from the flight line. The jets will be ready for operation in about 24 hours from now. Once the sample paper from the sniffer is removed, it is placed in a lead coffin for safe transport to Los Alamos and complete radiochemical analysis. Well, that gives you an idea of the snapper phase of the operation. Of military interest in the weapons development program, those of us in the armed forces ran almost all of our tests on the airdrop. The first 4 shots of the operation, the tumbler phase. On Tumbler, we had to get the answer to what was perhaps the most important military question with respect to the effects of atomic weapons since the proof test of the first bomb at Alamogordo. Back in about 1948, a series of curves were prepared on blast pressures versus distance for different heights of burst and different yields of bombs. All our offensive and defensive plans incorporating or considering atomic weapons were based on these curves. These curves are wrong. The error is severe according to more complete data collected on later atomic tests. Diagrammatically, an atomic detonation looks like this. 4 effects are produced: light, heat, radiation, and blast or air pressure. Since blast is the primary destruction force of the bomb, let's take a closer look at the blast portion of the event. The bomb is detonated in relatively cold air. The pressure wave produced by the energy release moves faster than the speed of sound in all directions at the same time, in what is known as the incident shock wave. The air is heated by the sudden compression caused by the shock wave. As the incident wave strikes the ground, most of the energy bounces back in a reflected wave. The resultant peak pressure in the reflected wave is about double the pressure in the incident wave. Thereby, thereby doubling the destructive power of the shock force, or front, moving across the ground. Because the air behind the incident wave is hot, the reflected wave can move faster and gradually compress the base portion of the incident wave into a wall or stem of boosted air pressure, called a Mach Y stem. On a graph, the event looks like this. The greatest pressure, of course, is produced at ground zero by the combination of the incident and reflected wave. The pressure gradually drops off as the waves move out from ground zero until the Mach Y develops and increases the pressure again. It was this amplification which extended the area of damage at Hiroshima and Nagasaki. The Mach Y stem worked over every type of structure: masonry, steel frame building, reinforced frame building. From a military standpoint, the atomic detonations on Japan seem to be pretty effective. So Hiroshima and Nagasaki became the norm. The bases were curved on blast effects and damage. During Bikini in 1946, damage to ships in the lagoon and equipment on the beach agreed with blast damage curves developed in Japan. Theoretical height of burst curves were developed from effects observed during Hiroshima and Nagasaki, the Able shot at Bikini, and were backed up by high explosive experiments. During Operation Greenhouse at Eniwetok in 1951, men from each of the services got their heads together and dreamed up the most extensive blast study program up to that date. It involved every principal type of structure, many above, some below the ground, in a variety of orientations to the burst. It involved airplanes in the sky, parts of airplane structures on the ground, tanks, and other types of military equipment. The pre-blast estimates of damage were based on composite blast curves developed from studies of Japan and theoretical calculations. Pressures resulting from the tower shots of Greenhouse were less in some cases by a factor of as much as 2/3 than the original prediction. On the burst of Buster Jangle, even more severe differences showed up between the predicted blast effect estimates and the actual results produced by nuclear weapons. For unknown reasons, nuclear weapons were producing, in some cases, only about 1/3 the blast pressure that we had expected. This raised some very sobering questions in the minds of military planners. We knew the energy was there, but something somewhere along the line was happening to lessen or cushion the full effect of the blast. Where and why are there such discrepancies in our blast curves? Getting the answers was our priority objective on Tumblr. Several things could be happening. For one, the shock-reflecting characteristics of the target itself might be a factor. For another, the thermal radiation might cause the dust on the ground to stir up to such an extent that it cushions the shock wave. It might heat up the ground and the air layer close to the ground to such an extent that it would alter or soften the full effect of the blast or the development of the total potential force of the reflected pressure wave. On the other hand, perhaps there is a completely unknown reason why our estimates of the optimum height of burst for an atomic bomb were wrong. So nuclear weapons were used for the purpose of establishing two blast curves at the Nevada Proving Ground in the spring of 1952. The first weapon will be detonated over Frenchman Flat, site of Operation Ranger in 1951. This is a dry lake bed with moderately stable soil and generally high thermal reflecting characteristics. The blast measurement line stretches 4,000 feet west from ground zero. 50-foot poles were placed every 250 feet along the blast line, with instrumentation running from ground level to the very top, changing the lake bed from its normally flat, deserted appearance to outdoor scientific laboratory, complete with intricate instrumentation of all sizes and purposes. All of this will help determine the blast characteristics produced by a nuclear weapon over this type of target, and to extensively study phenomena occurring in the air layer close to the ground. To aid the many projects in making a more complete evaluation of their results, the Air Weather Service is installing special instruments to record wind direction, speed, air temperature, and relative humidity. This data will help by recording the exact meteorological situation around the test setups and shot times. Another instrument, known as a blast switch, will record the time of arrival of the shock front at ground level, 10 feet and 50 feet. These are installed at stations along the blast line to give us additional information on blast and its behavior as a function of time and distance from zero. The next set of instruments, Wianco gauges, located at 3 elevations on the pole, will measure variations in pressure with time and distance. Gauges on the pole are parallel to the blast line, and at ground level are flush with the earth. The gauge itself incorporates a pressure-sensitive recording element placed behind the pole in a 17-inch battery. We're trying every angle and every gadget we can to find out what really does happen when an atomic bomb kicks out fiercely at the world around us. To get a picture of blast pressure driving into the ground, we're installing self-recording accelerometers 5 feet below the surface. At this shallow level, we hope to obtain data on movement of the shock waves, both vertical and horizontal through the medium of Earth. Other accelerometers placed to a depth of 50 feet will record the deeper responses. To get still another cross-check on the shock front or blast wave, as its arrival time is clocked by succeeding stations along the blast line, we're utilizing another type of blast measurement instrument called a Bendix gauge, installed at ground level at each of the stations. At 10 feet and ground level, we're installing dust collectors to see, first of all, if the thermal phase does kick up dust, and if so, to determine the size and density of the material that could possibly be a factor in reducing the power of the shock wave, besides absorbing and retaining some of the heat. By establishing air temperature at ground level, at 10 feet and at 50 feet before the burst, during the period of thermal radiation, and during and after the shock wave, we hope to get one check on the effect of this hot air layer on the shock wave. We're using a self-recording temperature measurement device called a thermocoupler, which contains a very delicate temperature-sensitive element capable of recording temperatures ranging from normal temperature on the Nevada desert up to 1,000 degrees centigrade and back again to normal in a few fleeting seconds. At some of the closest stations, we're installing other types of air temperature gauges, 2 and 4 feet above the desert floor, to further our studies on air temperature versus time in proximity to 0 point. We're installing another gadget, a sound velocity recorder, to give us still another cross-check measurement of the temperature of the air above the ground at the time of the burst, during the period of thermal radiation, and up to the time of arrival of the blast wave. This is done by measuring changes in the velocity of sound produced and received by the instrument. We hope this will prove to be still another way to determine the interference of the hot air layer close to the ground with the subsequent blast wave. By sundown the day before the shock, we had our blast line poles fully decorated like a row of weird Christmas trees. The working scaffold had been pulled down, the cable trenches filled, and the area leveled. Our job is over for the present. All we can do now is wait. What has been feverish activity during past days and weeks suddenly becomes quiet, sudden, in a way desolate. This is the last check, the final inspection by Los Alamos and military test directors as they survey the blast line with its complicated array of instrumentation above and below the ground. All is secure. Frenchman Flat stands alone and ready for the first shot of this operation. Shot day. 0 hour minus 10 seconds. The drop plane has released the first weapon of the operation, and as the bomb falls, smoke rockets are fired to form a grid. High-speed cameras record their responses as a measurement of blast strength above the ground. This bomb is not a test of a new idea, but a weapon with a 1 kiloton yield detonated at an altitude of 800 feet to closely correlate the effects with the low-yield bomb of Buster Baker. Once the dust is settled and the safest routes for re-entry are chosen for us by the RadSpace people, we quickly move back to the blast line station to recover our instruments and their very hard-to-come-by data as soon as we can. Although radiation levels are high and working time is short, it's perfectly okay for us to go in and pick up our priority data. We're all understandably anxious to get the answers, although this may take weeks or months of study and evaluation before the final determinations are made. With the first shot of the tumbler phase completed, we're taking the rest of the weapons north, some 10 miles across a ridge of mountains into the next valley, Yucca Flat, site of the Buster operation. To try different heights of burst over a completely different type of target. Stretching to the south, 12,000 feet from ground zero, are the various military effects measurement lines. The blast line here is basically a duplication of the Frenchman Flat blast line. The target is a bullseye 500 feet across. By comparison with the lake bed in Frenchman Flat, the surface in this area is rough and dusty. By comparison with data we got at Frenchman Flat, we hope our instruments here will tell us if the thermal absorption characteristic of a target affects the shock wave. Here we will also get a valuable check on the effect of the height of burst on the development and effectiveness of the shock wave and Mach-wide depth. Tumbler, shot 2, 15 April 1952. The weapon for Tumbler, shot number 2, is the same size as the one detonated over Frenchman Flat. Yield, 1 kiloton. Height of burst, 1,100 feet. This gave us a chance to detonate the same weapon over both a reflecting and non-reflecting target. 22 April 1952. Tumbler, shot 3. Weapon yield, 30 kilotons. Height of burst, 3,500 feet. The same scaled height as shot number 2. These two tests should together provide an excellent check on the normal blast scaling laws. To help the defense establishment produce their new height of burst curve, the Air Force dropped the weapon at a standard ballistic scale. Shot 4. H minus 1 minute. Yield, 20 kilotons. Height of burst, 1,050 feet. We have had the opportunity to measure and study the characteristics of blast. basic destructive force released by an atomic bomb. To study it in the course of 4 detonations over 2 types of targets, 3 different heights of burst, and 3 different yields. The tumbler operation provided good experimental data on which we can base new height of burst curves for operational use. These curves falling between the old theoretical curves and the data obtained during busting, providing for the first time experimental proof of the advantage of detonating an atomic bomb high in the air when weak targets such as aircraft are involved. We also found that the normal cube root blast scaling laws developed from high explosive tests applied to the blast pressures from atomic weapons. A new phenomena which may account for the low pressures measured on previous tests was observed for the first time on the 4th shot of Tumbler, a so-called precursor pressure wave moving on from ground zero in advance of the incident shock wave from the bomb. This precursor wave may be caused by the intense thermal radiation released at detonation. We'll have to study, analyze, and cross-check, and then return to our outdoor laboratory again to proof test our findings. But blast phenomena wasn't the only thing studied on Tumbler. Let's go back and take a look at some of the others. Before Tumbler, there was little information about the effects of blast on aircraft dispersed in the vicinity of the burst. We didn't know for sure how much blast pressure an aircraft could withstand and still take off on a mission. So we moved a variety of aircraft types into stations at various distances from ground zero. The aircraft themselves were positioned in a variety of orientations to the burst. Some faced directly into it, some directly away, some at oblique angles, some at right angles. Will orientation be a factor? If so, how much? Since a fighter is built to withstand greater load factors than a bomber, will the fighter sustain less damage? Will jet planes, which are built to withstand the great pressures of high speeds, sustain less damage than conventional aircraft? We're primarily attempting to define the damage area limits under the different conditions of detonation. So if a plane was not damaged on one shot, we moved it closer to the next shot in an effort to find the breaking point. Some aircraft themselves are instrumented to record the strains and pressures inflicted upon them. We are backing up the instrumentation in the planes with thermal measurement instruments near them on the ground. We have positioned some of the planes behind shields and revetments to help us analyze the value of passive defense for enemy aircraft and for our own planes. We're going to get a lot of valuable information, too, on the effort required to return aircraft to an operational status after exposure to a burst. Shot day. The effects of an atomic bomb on aircraft. After a shot, we're all anxious to get back to our test setup to see for ourselves what happened. The data is here. It only needs to be recovered and analyzed in order to be applied to the plans and problems of atomic warfare. Among many other things, we learned that bombers do receive more damage than fighters. Jet aircraft generally sustain less damage. Planes in a side orientation to the burst receive the greatest damage. In all cases, damage is closely related to the height of burst, distance from ground zero, and kiloton yield of the bomb. Planes in some cases can be returned to operational status after exposure to an atomic detonation. Some can go into operation immediately. Hopefully this program will give our military planners a great deal of new and vitally important offensive and defensive information. While we're trying all the time to better our position and approach to offensive use of atomic weapons, we're trying just as hard in the other direction to learn all we can about protection and defense against effects of the bomb. Normally, Normally, in combat, when a man doesn't have something like a trench or a foxhole to seek shelter in, he takes advantage of whatever protection is available, such as a forest or heavy foliage. So we went to Mount Charleston near Las Vegas, selected and carefully removed some evergreen trees that were in perfect condition to bring to the test site. We've been making studies for years on the thermal characteristics in different forest situations. By pulling trees over, breaking them, and various other tests, we have developed some very reliable systems for estimating the static forces necessary to damage trees. Now we need to learn the reaction of trees to the dynamic forces and thermal radiation produced by atomic weapons. Once the trees arrived at the site on special trailers, they were carefully removed to minimize the amount of breakage and planted in concrete foundations at varying distances from ground zero. Since we know the breaking point of these trees pretty well, we're trying to place them in position and at distances to measure how much the trees will bend under the shockwave forces. Then we know how much more it would take to break them. We're instrumenting the trees with strain gauges, scratch gauges, and other gauges. Some of our other trees are like something right out of science fiction. During the operation, they took on the nickname of lollipops. Actually, they're idealized tree models, consisting of flat metal plates mounted on steel beams. The lollipops are instrumented to help us determine the motion and bending strain on trees subjected to the fierce pressures in the shock waves. This combination of real and idealized model trees will also help us to get a good reading on the drag forces of tree crowns. Fires may be a discouraging factor too. So we're setting out a variety of things that could ignite and burn in a forest. These are known as forest fuels, materials that might carpet the floor of any forest, such as logs, pine needles, beech leaves, deep grass, moss, and fir needles. The blast and fire of an atomic bomb are even more dangerous in populated areas. So we're exposing specimens of common structural details, covered and uncovered wall angles, some bare, some exposed with materials that will ignite easily, approximating inflammable trash found in almost any urban area, plus various types of roofing. All of these structural components are without defects that would tend to cause them to ignite or burn. All of this to determine the vulnerability of building components to ignition and sustained burning from atomic weapons. We're also setting up cubicles or miniature buildings to relate to study even more specifically to the problems of a city exposed to an atomic bomb. To find out what ignites inside, we're installing various types of furnishings, such as wood tables and chairs. This project is looking for primary ignition, not secondary ones from overturned stoves or damaged electrical circuits. We're also going to be able to study the interaction between thermal radiation and the blast wave, and the characteristics of the blast wave in spreading or putting out fires. Our forestry line is ready. Shot day. About shockwave effect on our trees, we learned that they are fairly flexible even against the dynamic force of the bomb. There was a minimum amount of breakage and little damage from flying missiles. However, all of our stations did not come out unscathed. We found that with trees in good condition, generally good thermal protection will be available, thus lowering the degree of burning and the ultimate area of damage. But a full evaluation of their blast protection or hazard will depend on more extensive tests in the future. Our fuel samples were upright to provide the most ideal conditions for ignition. and to help us find the limits of the bomb's ability to start and blow out fires. It is only relatively close in that the shock wave blows out a fire. Our miniature buildings and structural specimens gave us valuable data and confirmed many predictions. Sustained burning will not occur if structures in good condition are beyond the primary blast area. After the heat from the bomb has diminished, the fire will generally go out. There would probably be some ignitions through open and broken windows. Then we set out to broaden the foundation of knowledge on which we can reliably base troop participation in atomic warfare. First of all, we want to learn more about the effect of atomic bombs on the combat tools of ground troops. So we're going to let the blast work over a wide range of implements used by soldiers in the field. A cross-section of everything that rolls or shoots will be exposed in a variety of orientations to the burst, and at several distances from the detonation, from large artillery units and heavy machine guns to light weapon emplacements. Shot day. Camp Desert Rock. H-5 hours. Throughout much of recorded military history, it's clear that the effectiveness of troops is due to their psychological attitude toward the weapons used and situations encountered. At their base camp, Desert Rock, these men are mustering for an atomic warfare maneuver, only the second series of its kind in history. Though they are very much a part of Tumbler's Snapper, they operate independently as they would on a military maneuver. They've all been thoroughly briefed on the hazards, precautions, and techniques of their tactical operations in the area of a nuclear detonation. After the time check, the word is roll out. Every man is accounted for. Every man has his own film badge to record the degree of his own personal exposure. Every group is accompanied by trained radiological safety monitors to be with them in the contaminated area. Desert Rock entrenchment area 4 miles from ground zero. H-90 minutes. Like all too many people, both in and out of the military, before these men got their assignment for this operation, they had many misconceptions about the bomb and its effects. Some of them thought they would never again be able to have families. Some of them expected to be deaf or blind. Some of them expected to glow for hours after the bomb went off. Like so many people, many of them were afraid. They had never taken the time or invested the effort to learn the facts about what to do in case of atomic warfare. These men have been indoctrinated in what goes on and what to do when the bomb goes off. Any doubts that are left will be eliminated after the full experience of this operation. Planning level observers from throughout the defense establishment have an opportunity to study the maneuvers from close range. 8 hours minus 5 minutes.
Plane on its bombing run. The time of fall will be 40 seconds. We'll hit a countdown from the far away until the first time. Remain in your hold until the command raise has been given at each plus 3 seconds. If you stand up too soon, the enemy flight will temporarily blind you and the heat will give you the equivalent of a severe sunburn. When the command raise has been given, stand up and lean against the rear of your foxhole. This will raise you up to
Before the Desert Rock maneuver can proceed, before anybody can go back to his test setup to recover instruments and information, the entire blast area gets a radiological survey a matter of minutes after the shot. The armed forces are responsible for all radiological safety on the operation. This is very important experience for military preparedness as well. Helicopters can hover close to the ground, survey and double-check any questionable areas. Re-entry routes and procedures are determined accordingly by the men of RadSafe Operations and the commanding general of Desert Rock. On 3 of the Tumbler shots, the Strategic Air Command operated bombers at operational altitudes above the Earth. This is another part of the Defense Establishment program to give more service people the experience and confidence for atomic warfare operations. We re-enter our display areas close to ground zero, once RadSafe okays us for the move up. Since the biggest value of the operation is for us to prove to ourselves that it can be done, and find any weak points in the training, the Caiaphas are with us to study our reactions before, during, and after the experience. No one can ever fully make you realize what you'll see and feel when you experience an atomic weapon detonated for the first time. It's quite an experience, no matter where you are to watch it. This kind of experience is immensely valuable for any military man, and it will be a part of the tactical training for a great many Army and Marine field forces in the future. In the minds of many of the men, there was doubt and fear before. Now there is confidence. Confidence that comes only with experience. Just treat it with respect rather than fear. Use a little common sense and observe a few basic precautions. After the walkthrough, we move back out of the contaminated zone to our parking area. We made it. And so can anyone else who goes through this kind of operation. 3 months ago, all the gold in Fort Knox wouldn't have made us want to do it. Now we wouldn't take anything for the experience. We've proved a lot to ourselves, and to a lot of other people who need to know it can be done. And we're proud of it.
1945, Alamogordo, New Mexico. Watch the first atomic detonation in history. Operation Trinity. The long series of nuclear tests is underway. July 1946, Operation Crossroads. Bikini Atoll in the mid-Pacific. The war over, scientists and military personnel busy themselves setting up a targeted ship for the first peacetime test of the atomic bomb. High-ranking military personnel and civilian observers watched the able shot. 19 kilotons burst 516 feet above the surface of the lagoon. Damage to the target array is assessed and preparations are underway for the Baker shot. The bomb, similar in type to the Able test, is located in an airtight caisson beneath the surface of this tropical lagoon. With all preparations made, Baker shot occurs on schedule. Many impressive and startling effects are observed on this shot, including the first appearance of a base surge, seen here enveloping the target ship. April 1948, Eniwetok Atoll in the Pacific. Our third nuclear test program gets underway. Operation Sandstorm. 3 weapons, fired on 200-foot towers, with batteries of scientific instruments to record results. As at Bikini, drone planes are used here. Giant planes, heavily instrumented but without crews, take off to fly through the heart of each atomic cloud, to collect samples of that cloud for detailed radiochemical analysis. Three times the sound and fury of atomic detonation shatter the Pacific dawn. 3 times a scientific laboratory is created to study previously unattainable effects of high temperatures and pressure. But what did we learn from these detonations? What were we trying to prove? Why did we expend this almost priceless nuclear material and these thousands of man-hours of labor? Let the men of Los Alamos give us the answer.
We returned to the hill from the sandstone test with new and important information. Information that would enable us to make a sizable contribution to the generally rising curve of man's knowledge of atomic weapons. Information that would help us tackle basic problems involved in high explosive systems, pit designs, core arrangements, initiators. Information that would enable us to increase the small percentage of active material that actually burns during fission. The more efficient use of fissionable material has been and continues to be one of our main objectives. For it is the fissile material itself, whether uranium-235 or plutonium, that is the expensive or elaborately complicated material to produce. The nuclear material is the heart of all our attempts to make bombs economically feasible. At Trinity in 1945, we proved a self-sustaining reaction could become an explosive force, and that the implosion principle was sound. We had a starting point. The drops on Japan were strictly a war measure. At Hiroshima, we tried the gun principle and also used uranium for the first time. The Nagasaki weapon was an implosion type using plutonium. Little or no controlled experimentation was possible. Thus, little data was obtained which furthered the progress of weapon design. As a result of the Japan detonation, the effects from an atomic explosion became of prime concern to the armed forces. Thus, Crossroads using an implosion system. At Crossroads, since we were mainly interested in testing naval materiel, little data was obtained from the Able and Baker shots on weapon development. However, significant effects knowledge was obtained. Stateside laboratory research, in the meantime, developed new weapons for the sandstone test. At Sandstone, we were once again able to tackle the big problem, more efficient use of fissile material. Here, we were able to utilize uranium-235 in an implosion-type weapon. As time went on, we had increased our knowledge of weapon design and had, therefore, increased yield per kilogram of active material. This is where we stood by the end of Sandstone. It is equally obvious that testing at a proving ground is to be a permanent feature of our work. So a proof test division, known as J Division, is organized. Dr. Alvin C. Graves is selected to head this division, a unit with the specific job of testing weapons. By autumn of '48, a test program is framed. This calls for experimentation of new weapon designs with the objective of again moving our knowledge curve upward to a more effective level. Once more, we propose to better yield per kilogram invested. Greenhouse may take us a long way in the direction of smaller weapons. For the first time, deliverability in terms of size and weight is expected to make its mark in improved weapon design. Greenhouse will also give us direction as to what road to follow in the development of a thermonuclear weapon. These are the main objectives in the weapon development field.
And so Operation Greenhouse gets underway, with Eniwetok designated as headquarters island for the Pacific Proving Ground. Engebie, Runnet, and Eberiru are the shot islands. During late 1950 and early 1951, work progresses in the island. Towers are built. Recording stations are constructed. Coaxial cables for the shot towers are laid. Myriads of instruments and intricate wiring hookups are checked and double-checked. Finally, everything is ready for the biggest job in nuclear testing, the job of obtaining exact information about the detonation itself. The builders are through, and the scientists take over the story.
Those of us from the scientific task group are here essentially to confirm or disprove theoretical calculations, to learn what is not always possible to prove in a conventional laboratory. To learn more about the atom bomb, we divide our testing into two major areas, diagnostic testing and effects testing. More specifically, diagnostic tests are an extensive examination of the phenomena occurring during the initial phases of the explosion. Effects tests study the external manifestations of the explosion, the effects of the weapon. To gain an intimate understanding of interior weapon behavior, three kinds of diagnostic measurements are made. These are the time it takes to start the nuclear reaction, transit time; the rate at which the chain reaction multiplies, alpha measurement; and measurements of the total energy released in the nuclear reaction, yield. Most of the diagnostic data is available only during the early microseconds of the nuclear reaction, and extensive instrumentation is required for each detonation. Transit time data, which gives information on the HE system, is cabled down to a recording station and measured by 3 oscilloscopes. Transit time instruments are wired into the same circuit that triggers the detonators of the weapon. Because they are activated by the same impulse, they can literally measure the duration of the implosion, or the time necessary to condense the nuclear material to criticality. Transit time is the interval, then, between the impulse and the appearance of the first gamma ray, which signals the beginning of the fission process. The oscilloscopes are extensively photographed during their microseconds of operation, since transit time is an important index of implosion efficiency and offers a good check of weapon design. The second phase of diagnostic experimentation, giving information on the internal workings of the core, is the alpha measurement. One way to obtain this data is to locate an ionization chamber adjacent to the weapon itself. Other ionization chambers, located at ground level, detect later stages of the alpha phenomenon. Measurements of alpha give valuable information on the multiplying qualities of the fissionable assembly. The multiplication rate is vital. It tells us of the growth of fissions in a given length of time. If we are to have more efficient atomic weapons, we must increase the rate at which fissions multiply. As radiations from the fissions are detected, a signal is sent down the coaxial cable to a recording station. The rate of increase of signal strength is recorded by some of the fastest recording equipment in existence today. In addition to the transit time and alpha diagnostic experiments, we have several methods of detecting the success of new weapon designs in terms of yield. Yield is the determination of the total energy released by the nuclear material undergoing fission. This energy is usually expressed in kilotons. 1 kiloton being the force released in 1,000 tons of high explosive. One means of measuring yield is to attach filter traps to drone aircraft and send them into the core of the atomic cloud immediately after the blast. Nuclear ashes or samples of the residue material saturating the cloud are collected in the traps for radiochemical analysis to determine the total number of fissions that have occurred. Since we know the yield per fission and measure the total number of fissions, the yield of the bomb can be computed. The SNAP sampler, a device new to atomic testing, is another way of collecting debris for radiochemical analysis. Samplers of the air type and samplers of the ground type are arranged in a semicircle close to the base of the tower. In addition to these methods of collecting samples of fission fragments, Greenhouse will test rockets for the first time to see if they are practical as sample collectors. The rockets will be fired just prior to shot time. They will travel in a long arc and pass through the clouds at approximately 5,000 feet. It is hoped that on the pass-through, they will collect samples in much the same way as drone aircraft. Another measure of yield is made with high-speed still and motion picture cameras, which record the rate of growth of the fireball. The more energy developed in the reaction, the faster it expands. To repeat, the diagnostic experiments are concerned with the behavior and phenomena of the weapon itself.
Shot number 1, Dawn. The objective of the test of the Howe weapon were to prove a weapon of higher yield and efficiency than currently stockpiled. The predicted increase of efficiency made possible by the Type D test was confirmed. Shot number 2, Easy. The objective of the test was to prove a lighter and smaller weapon with acceptable efficiency. The feasibility of obtaining acceptable efficiencies with lighter and smaller weapons was confirmed, and thereby future weapons design was advanced. Shot number 3, George. A step was taken along the path to thermonuclear weapons by the achievement of a fusion reaction. Shot number 4, Item. A successful booster reaction proved the feasibility of increasing fission yield by a limited fusion reaction and gave more impetus to the development of booster weapons. Fission weapons proof testing, physics experiments run on thermonuclear reactions, military and civil defense knowledge immeasurably increased. This was the accomplishment at Greenhouse, at Entity, at Ebenezer in the spring of 1951. Once more, the Pacific Proving Ground has proved its value, but the job is far from complete. Each test series leads inevitably to new developments requiring still more tests, more frequent than are practical at distance and a Weetah, where logistic problems make it difficult to run more than one test a year. We need a site much closer to home, a site in the continental United States. But where?
For a long time, and As a matter of fact, ever since Trinity, men from Los Alamos had been eyeing the great barren stretches of the Southwest. This region, for the most part, fits the bill. Isolated from centers of population, with favorable winds, with the necessary consistency of soil and formation of earth strata below. And so beyond the World War II training base, to the north of an early day Nevada stage stop called Indian Springs, 65 miles north and west of Las Vegas, an atomic range was established. A test site of over 400 square miles of flatbed valley, mingled with mountains of solid rock, whose veins once colored history with gold and silver. A range remote from civilization, isolated, forgotten as the names of the men who once made their fortunes. In the pre-dawn hours of January 1951, this long deserted countryside came once more into international focus with Operation Ranger. The test of 5 atomic bombs. 5 successful airdrops that saved the weapons research program months of time, considerable money, and helped Los Alamos prove the radical new idea of small atomic bombs. Soon after Ranger, another use of the Nevada test site was apparent. This was a chance for the military to get more information in a shorter space of time on the effects of atomic weapons. Vital facts. For what good are atomic weapons without full knowledge of what they can really do, and how we can be protected against their effects?
Thus, Operation Buster was born. In the fall of 1951, the combined operation Buster Jangle was held at the Nevada Proving Ground. Five weapons in Operation Buster. 1 on a 100-foot tower and 4 airdrops. A tent city, Camp Desert Rock, was activated and occupied by observers from all the services, arriving here from all corners of the earth to participate in an atomic maneuver. Here they receive extensive indoctrination by experts from the Armed Forces Special Weapons Project in the expected phenomena of the detonation, and by Camp Desert Rock personnel on the assumed tactical maneuver. Early on shot morning, they load into trucks and buses for the long trip to the target area. In the target area, last-minute orientation talks are given, and the observers prepare themselves to watch an atomic detonation from the closest point that personnel have ever been during nuclear tests. Following the detonation, the troops move forward to the ground zero area to inspect the effects of the bomb. The Ranger shots were experimental devices only. This was the first stockpile weapon to be detonated within the continental limits. Operation Jangle, immediately following Buster, was our first test of surface and underground atomic detonation, designed to study military effects of these types of bursts. Jangle number 1, the surface shot, heavily instrumented to study energy coupling in the Earth itself. This low-lying cloud is hot, with radioactivity trapped in Earth particles thrown out by the force of the explosion. In a little while, ground monitors mark off the outer limits of personnel re-entry into the blast site. In the fringes and interior of the crater itself, the spot that once was ground zero, there are soil specimens of great value if they can be collected before their short-lived radioactivity dies. Remote-controlled Army weeds, drone weeds, are warming up for this collection job. A compact television camera mounted on the front of each weasel will inspect the terrain as they go and relay the picture back to their guiding control station. Scoops on the front of one drone will gouge out and bring back surface samples of the crater dirt. A drill rig mounted on the back of the other weasel will bore down and secure cores, which will tell the story of subsurface radioactivity. Now the push is on for Jangle 2, the underground detonation. Like the surface job, this will be a 1 kiloton gadget, but this time it will be detonated 17 feet beneath the surface of the Nevada soil. Very extensive military effects tests will be run with this detonation. Dummy buildings with superimposed loads to represent upper floors, and underground structures, such as fuel storage tanks, water systems under hydrostatic pressure, gas mains, and electrical mains have been constructed to gain realistic data on ground shock and cratering action. Inside the control point, members of the military effects test group supervise the detonation.
5, 4, 3, 2, 1, 0.
After the detonation, test structures are studied, and the many scientific and military personnel involved return to their home bases to evaluate the results of the operation. After the 7 shots of Buster Jangle are complete, the test area lies dormant, waiting, ever ready for future tests. Our proving grounds, Enowetok and Nevada, stand ready to aid the scientists and the military in their job of preparedness, of developing weapons and doctrines for any possible future atomic war.
Age was born. There is no denying that since that moment, the shadow of the atom bomb has been across all our lives. All men of goodwill earnestly hope that a realistic control of atomic weapons can and will be achieved. Meanwhile, good sense requires that all of us prepare for any eventuality. But wisdom demands, too, that we take time to understand this force. Because here, in fact, is the answer to a dream as old as man himself. A giant of limitless power at man's command. And where was it science found that giant? In the atom, a particle so infinitely small that it takes over 100 billion atoms to make up the head of a pin. Just as other millions and quadrillions of atoms are the tiny building blocks which make up everything in the world. Ships, and shoes, and sealing wax, and cabbages and kings. Although no one has ever seen an atom, scientists have learned a great deal about how they behave, and there are widely accepted theories as to what they're like. Let's start by meeting a leading authority on the subject, Dr. Atom. Now, observing the professor himself, we can see that his structure resembles, in many ways, something almost as vast as the atom is small, the solar system. And there are certain similarities. Here is the center with electrons in surrounding orbits. But whereas the planet's movement of electrons is slightly different, there are other differences too. Hey, hold it! Thank you. Now, the solar system together is electrical. The electrons, which are negative, are attracted by the protons, which are positive, and vice versa. But here in the nucleus are other particles with no electrical charge, called neutrons. Very important characters, too, as we shall see. And equally important when it comes to atomic energy is what scientists call the atom's binding force. It's a kind of cosmic glue holding the nucleus together. This, then, is a single atom, but certainly not all atoms are alike. There are in nature more than 90 basic elements, which is science term for families of atoms. To scientists, the atoms of the individual atom families, or elements, are identified by number. That is, the number of protons or positive charges in their nucleus. And they vary all the way from hydrogen, which has just 1 proton, to oxygen with 8 protons, to gold, he's rich with 79, finally on to the heaviest of all natural elements, uranium with 92 protons. Now, within each element, or family of atoms, there can be different members, each one having the same number of protons, but differing in the number of neutrons. The total of an atom's protons and neutrons is its atomic weight. Thus, in natural uranium, we have U-234, U-235, and U-238. These different members of the same element or atom family, science calls isotopes. Some elements, tin for instance, have a great many isotopes. Others, like aluminum, are lone wolves with just 1. Now, most atoms of most elements are content with their lot in life. We speak of them as being stable, but others are busy day and night, being what science calls radioactive. Like radium, throwing off powerful rays along with some of its neutrons and protons, until it actually alters its own nuclear structure and changes to another family, and then to another, until it does become stable at last. This spontaneous changing of elements is called natural transmutation. Its discovery gave men of science an idea. If an atom could change itself, why couldn't man change an atom? Using as bullets the very particles which radium threw off, a noted British scientist bombarded nitrogen and converted it to oxygen. In terms of individual atoms, this is what happened. The radium nucleus threw off an alpha particle consisting of 2 protons and 2 neutrons. One of the protons was absorbed into the nitrogen nucleus, turning it to oxygen. This was artificial transmutation, man changing the elements. From that first experiment, others by the thousands followed as scientists devised ever more powerful particle accelerators, commonly called atom smashers, to transmute more and more kinds of atoms. All scientifically important, but hardly world-shaking. Then, in 1939, some scientists were experimenting with transmutation of uranium. What would happen, they wondered, if they fired a neutron at a uranium nucleus, already the heaviest in nature? Why not try? So they tried. And the result? Nuclear fission. Instead of a minor change, the atom split in 2. Truly a discovery to change the world. For what had happened when the uranium atom split was a kind of double miracle of science. Half of the miracle concerned that binding force we spoke of before, that kind of cosmic glue which holds the atom's nucleus together. We still don't know all about that binding force yet, but we do know it is equivalent to mass. Therefore, we may speak of it as having a kind of weight of its own. Now, the 2 atoms into which a uranium atom splits also have binding force. But for some reason, it takes less of that glue to hold them together, and in the process of fission, a tiny fraction is left over. What happens to it? It explodes as energy, proving Einstein's theory that mass and energy are really the same. But we spoke of a double miracle. To understand the second one, let's slow down that fission a million or so times. A single particle starts the reaction, splitting the uranium atom. Here now is the release of energy as heat and blast. Here are powerful rays being given off, similar to X-rays. But here, Here are free neutrons driven out with tremendous speed. And provided there is sufficient U-235 present, what science calls a critical mass, those neutrons bombard other uranium atoms, causing them to split and split still others. The result? A chain reaction. Over 1 million billion atoms exploding within 2 seconds. And the force? It would take Yankee Stadium full of dynamite to equal the energy released in the complete fission of an amount of U-235 the size of a baseball. With this discovery at the time the free world faced a war for survival, it was little wonder the first thought was a weapon. But how to obtain enough material for even a single bomb? Only a small fraction of natural uranium is the U-235 isotope, which will fission in a chain reaction. And to separate enough U-235 quickly enough seemed all but impossible. But the impossible became reality as industry, labor, science, and the military combined their efforts to build Oak Ridge, where enough U-235 was separated to build the first atomic bomb. At Hanford, Washington, another impossible project proved possible when a huge plant was built for the mass production of the artificial element plutonium. This process involves what may be called the furnace of atomic energy, the reactor pile. Here is a structure or pile of graphite blocks. In the reactor are placed rods of natural uranium containing both U-235 and U-238. As U-235 begins to fission, the graphite slows down the free neutrons, and some of them hit other U-235 atoms, keeping the chain reaction going. But others of those slowed down neutrons hit U-238 atoms. And here's what happens. Remember, we said that U-238 wouldn't support a chain reaction. However, it will capture neutrons from U-235 fission and start a process which converts the U-238, first to neptunium, then to plutonium. And plutonium will fission in chain reaction. Thus, the reactor itself is a source of atomic fuel. Besides producing plutonium, the nuclear reactor makes possible two very important peacetime uses of atomic energy. Remember that the chain reaction process in the reactor creates tremendous heat, which scientists have learned how to control. Thus, a reactor may be substituted in many industrial applications where heat is now provided by coal or petroleum. But such uses in the foreseeable future are limited. For one thing, a reactor pile must be shielded to protect the workers around it from dangerous radiation, and this shielding adds tremendous weight. However, an atomic energy power plant has already proved feasible. The future supplying of electric power to entire cities is far from impossible, while nuclear power in locomotives, submarines, ships, and even very large airplanes may all but revolutionize future transportation on land, sea, and air. But perhaps the most valuable byproduct of the nation's reactor piles is radioactive isotopes. Research has revealed that many elements not naturally radioactive became so when placed in a nuclear reactor. And these isotopes, working as tracers with such measuring devices as a Geiger counter, became invisible detectives, aiding the cause of science in many different fields. In agriculture, isotopes are now used to test such things as the effect of fertilizers on plant growth and the proper timing for their use, helping to assure bigger and better yields from tomorrow's farms. In industry, isotopes have found literally hundreds of new uses, such as the automatic thickness control of sheet aluminum, saving hundreds of man-hours of labor and assuring accuracy never before possible. In the fields of medicine and biochemistry, isotopes are performing near miracles of diagnosis and discovery. With radioactive sodium, doctors are solving more of the seeming mysteries of heart disease and circulatory disturbances. Radioactive phosphorus has been used to locate tumors in the brain and greatly simplify operations for their removal. Iodine-131 finds one of many uses in revealing conditions of the thyroid, and there are many more. New ways of using isotopes are being discovered constantly through the tireless work of modern pioneers in such fields as chemistry, metallurgy, medicine, and biology. Truly, the superpower which man has released from within the atom's heart is not one, but many giants. One is the warrior, the destroyer. Another is the engineer seeking to provide vast quantities of energy to run the world's machines. Another is the farmer helping to better feed tomorrow's world. Still another is the healer helping to diagnose and cure the sick. And the last is the research worker working on in the fields of pure science to reveal more of the mysteries of the universe. But all are within man's power, subject to his command. On man's wisdom, on his firmness in the use of that power, depends now the future of his children and his children's children in the new world of the atomic age. Clicking sounds, sounds that reveal the presence of radioactive rays. The instrument, a Geiger counter, is converting radioactivity into sounds we can hear. This radioactivity is coming from a small piece of radioactive material inside this plastic cylinder. The small amount of radioactivity coming from the cylinder is harmless. The luminous dial on this watch also gives off radioactive rays, which we hear on the Geiger counter. Even when there's no radioactive material near, the Geiger counter continues to click. This is caused by cosmic radiation that continually bombards us from outer space. But we don't get enough cosmic radiation to harm us. Today, atomic scientists produce radioactivity in large amounts. Radioactivity and radioactive materials have many peacetime uses. But we know, too, that they can be used harmfully, as in atomic bombs. The chance of your being hurt by an atomic bomb is slight. But since there is a chance, you must know how to protect yourself. To protect yourself, you have to know what the bomb does. Besides blast, there's radioactivity and heat. Can we protect ourselves from these? These children are protected. Concrete walls help stop radioactivity. Any wall stops the heat. The heat scorches the house, but does not harm the children. Any solid gives some protection. The thicker it is, the better. We have the national defenses to intercept an enemy, and we all form a team to help each other through emergencies. You are on that team. So is your family, each member of it. And in your community, every doctor, fireman, every policeman and nurse, every lineman and operator, every civil defense worker, in fact, every community employee is ready to help you if you need them. So your community is prepared for emergencies and ready to help other communities. We have state and national headquarters for civil defense. And your city has a Civil Defense Corps. We have a warning system and a system of defense. Yes, we have the equipment and the people for an effective team. But, like any team, it can win only when everyone knows his job and does it well. What is your job? What if a warning siren sounds? What should you do? Look for cover, the nearest cover. Don't try to make it home unless home is the nearest place to go. Don't hesitate. Find cover. Everyone is in on this. Strangers will understand. Finding shelter quickly may save your life. If you can't get into a house, get behind a wall or a steep embankment on the side away from the city. Civil defense teams will go into action immediately. If you're home, you've work to do.
Hi, Susie. Everything's fine upstairs. How you doing here?
Okay, I guess.
That's good.
We repeat, cover windows to protect against the possibility of broken glass, heat, and radioactivity. Turn off fires. If you are home and are not assigned to civil defense duties, go to your prepared shelter. Those who are in shopping centers, go to prepared
Well,
shelters
fire in the kitchen's
immediately.
out. Now we'll go down the
In
basement.
this practice alert, we are assuming that the attack will come on the waterfront area.
See, it's just practice. All this rushing around for nothing.
Now, there's just where you're wrong. We need this practice. Now, come on, let's do our job.
That's good thinking. We all need practice. Here's a clean, well-prepared shelter in the basement. Ted and Sue have a battery radio, and they have soda ash and stirrup pump fire extinguishers. They have other emergency supplies, too. A flashlight, a well-equipped first aid kit with plenty of bandages, tape, and scissors. A Red Cross first aid book, a few cans of food, a good supply of water, blankets, and an electric lantern in reserve.
You know, Susie, this stuff would come in handy on a camping trip.
I'd a lot rather be on a camping trip. Say, what will they do if we didn't have a basement?
At school, they told us we should be away from windows and behind double walls. You know, like an inside hall.
Ted's right. If you live in an apartment house, you can't all go to the basement. Head for a shelter area. If none is marked for you, find cover away from windows and in a hallway if possible. Wait for the all clear. Be calm. If you're on the playground, run for shelter. If you're in the schoolyard, get into the building. Move quickly, but in good order. Inside, go to the shelter area you've been assigned. Take your place on the floor. Here's one good way to protect your eyes and neck in case of a bombing. Wait for the all clear. So far, you've been watching a practice drill. But what if there is a bombing that comes without warning? What is your job then? Find cover immediately. Don't look at the flash. Stretch out. In about 1 minute, the immediate danger is past. Then head for safer cover. Another bomb may fall. Get indoors if you can. Shed your outer garments. They may have radioactive particles on them. If you're home, take shelter and stay down for about 1 minute. By then, the danger from radioactivity, heat, and blast have passed. Protect your eyes and neck.
Let's get things shut up.
Sue found shelter under her bed.
Dad, let's get the battery set.
When the house current is off, that battery radio is essential. Keep tuned in.
The airburst of 3:01 p.m. was zeroed on Union Station. Heavy damage extends from about 14th Street north to as far south as the waterfront.
You know, we're lucky.
To Western.
That blast was miles
Stay
from here.
undercover unless you have civil defense to... I've just been handed a bulletin. There's been an underwater burst at the waterfront. Water thrown up by the bomb is falling as mist and rain, and it is radioactive. Avoid radioactive mist and
What does
rain.
he mean
which
by
the wind is blowing south from the
radioactive
river.
mist?
All
According to what Dad said, the radioactivity gets into the mist and rain. And if the mist or rain gets on you, it's apt to make you very sick.
What would you do about it?
I'd scrub thoroughly with a detergent and water.
What's a detergent?
It's something like Mom uses when she washes dishes and clothes.
Don't drink tap water. It may be contaminated.
Ted and Sue are waiting for the all clear.
I'll see who it is. Hello, who's there?
It's your block warden, Mr. Carlson.
Come on in, Mr. Carlson.
Hello, Ted. Hello. Ted, this is Mr. Franklin, our radiological monitor. He's here to check for any radioactivity. I saw your mother down the shopping center. She's fine. Well, there's no damage here.
No, it's been very good here.
Hello, Sue.
Say, have you seen my dad lately?
He's down at headquarters, and boy, he's really busy.
Yeah?
Well, there's no radioactivity here.
Say, Mr. Franklin, is that a pen on your coat there?
Oh, no, that's a dosimeter.
A dosimeter? Well, what's a dosimeter?
Well, it measures the amount of radioactivity that I've been exposed to. But this is the meter that I use to check with.
Say, Mr. Carlson, is there anything I can do outside to help?
No, Ted, everything is under control. You just stay here till the all-clear signal is given. You've done a good job.
Thank you, Mr. Carlson.
Bye, Sue. Bye.
A good job. That's what everyone must do to be safe. Doing a good job means simply following the rules in an alert or an attack, and waiting until all is clear again. In this early and troubled stage of the atomic age, our very lives may depend on always being alert.
Spread across some 15 million square miles of the Pacific, the 1962 Overseas Nuclear Test Series was an undertaking of impressive proportions. The test program, under the code name of Operation Dominant, required a technical and operational buildup of unprecedented scope, with planning, preparation, and deployment, all on a tighter time scale than ever before attempted in overseas nuclear test operations. Concurrent testing at 4 widely separated points was necessary to meet these requirements. Off Christmas Island, a series of weapon development airdrop tests was made, followed by later drops in the Johnston Island danger area. All drop aircraft staged from Hawaii. A Polaris weapon system test was launched from the open sea into the northeast corner of the Christmas Island danger area. A combined ASROC anti-submarine weapon system and underwater effects test took place in the open ocean several hundred miles off San Diego. And high-altitude nuclear-tipped missiles were launched from Johnston Island, with instrumentation to gather weapon effects data distributed over wide areas of the Pacific Ocean basin. All were prescribed for completion in the shortest feasible time. Here are the highlights. The high-priority inception of the operation to its successful termination. Operation Dominic was triggered by the Soviet resumption of atmospheric nuclear testing in September 1961.
The Department of Defense, under presidential direction, on 24 October 1962, activated Joint Task Force 8 under the command of Major General Alfred D. Starbird to prepare for a series of nuclear tests in the Pacific. The job handed General Starbird and his staff was an enormous one. To plan, organize, and prepare the task force and to complete the materiel buildup in time to be ready to fire by the 1st of April, with preparation time only 1/3 of that typical for previous, comparable but less complex test operations. Involved were the organization and movement of over 28,000 men, both military and civilian, along with preparation and shipping of almost 200,000 tons of materiel. Each man and each item was ticketed for a specific point somewhere in the vast Pacific Test Laboratory. This buildup included the development and installation of thousands of pieces of intricate instrumentation. Some were fitted in trailers, some in modified aircraft or ships. Other apparatus was scheduled for direct movement overseas for placement at one or another of the 31 Task Force overseas sites, which first had to be built, including remote instrument stations carved out of tropical jungle forests. These preparations were all parts of the master plan rapidly taking shape. One group of operations was the weapon development test. Initially, it was planned that these tests would be accomplished by placing an instrumented ship array in an open ocean area south of Hawaii to control and observe technical data from the detonation of the test device, which would be dropped by a B-52 based in Hawaii. This airdrop method had a twofold mission. It would provide for the proof test of weapons which, during the moratorium, had gone into the national stockpile without having been tested in weaponized form. And it would provide for the test of new development devices of advanced design. Supplementing the shipboard apparatus were specially modified aircraft diagnostic platforms. While the open ocean preparations were underway, negotiations were being conducted with the British government for the use of jointly owned Christmas Island, 1,200 miles south, as a location for the airdrop tests. In mid-February, the task force was notified that the necessary agreement had been reached. Because of the many technical advantages expected from the use of the island test base, plans were immediately altered to move the weapon development tests there. This location switch was indeed a substantial effort, with the prescribed first shot readiness date only 6 weeks away. The main features of the 1962 test program were by now essentially defined, although many details were far from firm. This fluid condition continued as developments throughout the test period brought forth new requirements. Although work in each of the 4 main areas was proceeding simultaneously, in this film, each of the locations will be considered separately, beginning with Christmas Island. Late in March, the Joint Task Force headquarters began to move to Christmas as the main forward location for the first phase of the operation. This 222 square mile atoll, hard by the equator, was governed by the British. They had used it for their nuclear test operations from 1956 to 1958, but equipment connected with their tests had been withdrawn and their camps deserted. Equatorial weather attrition, the task force's additional needs, required extensive preparation for the task force program. Since the atoll possessed no harbor, all ship-transported equipment, materials, and continuing supplies had to be transferred to lighters and barges in the roadstead, moved to the Port of London for offloading. Inland, Christmas was dotted with lagoons, possessing a swamp life all its own. On firmer ground lived 400 Gilbertese islanders, who produced copra from the atoll's thousands of palm trees. The weapon airdrops were made off the southeast shoreline of Christmas Island. The air array was controlled from the Joint Operations Center, housing the command post, the Air Operations Center, units associated with control of all drop and test elements. Additional radar apparatus located at A site plotted the precise second-by-second position of the drop aircraft during the bomb run to assure that the device would fall within the finite time and space limitations set by scientific and safety requirements. This plot information was relayed directly to the Joint Operations Center by a microwave television link, providing the Air Task Group Commander with instantaneous positive information on which to base his operational decisions. Also at A site, as well as at other locations on the island, basic diagnostic instrumentation housed in trailers was positioned to secure data associated with the detonation. Special tracking radars assisted this diagnostic array by assuring they were oriented toward the nuclear device on its trajectory from the instant of release to detonation. Optically and electronically, the trailer diagnostic instrumentation recorded the most minute detail of each detonation in millionth of a second segments for scientific analysis. Under the precise positioning of the Air Operations Center, various types of aircraft also gathered additional diagnostic and weapon effects information. 2 modified C-130s were platforms for fireball measurements with high-speed cameras. They also carried other instrumentation to record data on internal device behavior. This technique, rudimentary at the start, was perfected to a high degree of effectiveness during the Christmas airdrop. Control aircraft backed up the Air Operations Center's positioning of the air array, along with checking out the feasibility of an all-airborne diagnostic concept. Other aircraft recorded thermal radiation, radar attenuation, and chorioretinal effects for eye damage studies. Specially instrumented KC-135 aircraft also recorded a variety of experimental data. Aloft, too, were search and rescue aircraft and photographic planes documenting the Dominic detonations. After each shot, B-57 sampler aircraft went aloft, as they had in operations of years past, to fulfill one of the chief diagnostic functions of each event, stalking the radioactive cloud to obtain particulate and gaseous samples for radiochemical analysis. Throughout the Dominic test, maximum security was maintained around the Christmas and Johnston Island test area boundaries by the Navy destroyer and P-2V watchdogs. Round the clock, throughout the entire test period, the P-2V aerial fence layers rose from their Christmas and Johnston bases for their 10 to 12-hour runs, constant touch with the destroyers below. Daily, they greeted the Soviet instrumentation trawlers, which for 7 weeks lurked just beyond the danger zone periphery. On 23 April, the President directed the waiting task force to proceed with the first shot of the weapon development round. The initial airdrop was on the 25th of April, the last on 11 July. During this period, a total of 24 weapon development shots were detonated in the Christmas area. All drops were on target within the precise time and space limitations established by the requirements of diagnostic instrumentation, a record by the B-52 crew, which reflected a high degree of bombardment skill. Detonation technological efficiency also scored high in the fusing and firing systems and in the device telemetry. Throughout the Christmas airdrop, the backup airborne diagnostic method was progressively refined to the point of becoming a proven capability to collect the scientific data required. The weapon development effort was completely successful in all its primary test objectives. The series also yielded important new weapons effects information. Meanwhile, the task force was equally active at its 3 other test areas. Early in May, the test of the Polaris nuclear weapon system was ready for launch by submarine in the open sea. Detonation was scheduled to take place in the Christmas danger area. As the nuclear submarine Ethan Allen moved toward its rendezvous with range, safety, and instrument ships at the launch point some 1,500 miles from Christmas Island. All concerned were well aware that this was not only the first test of the complete Polaris nuclear system, but also the first proof test of this particular warhead in weaponized form. On the 6th of May, the Polaris was fired. Two submarines near the burst area, together with orbiting Christmas-based aircraft, confirmed that the warhead detonated on target at expected yield. First proof test of a United States ballistic missile nuclear warhead in its full re-entry environment was completely successful. Meanwhile, a group of task force ships several hundred miles off the Southern California coast were completing preparations for the ASROC event. This test had a dual purpose. It provided a system test for the nuclear ASROC anti-submarine weapon system, and also a major underwater nuclear effects test using a heavily instrumented test array. 11 May. With test equipment ready, the destroyer Agarho moved on station. The regular crew selected an unmodified stock ASROC, lofted its nuclear warhead toward a target centered in the test array. The entire operation was successful, with both the operational and effects test objectives achieved. During this same period, at Johnston Island, the launch center for the high altitude program, deployment of men and instrumentation had proceeded on schedule for a first event early in May. The purpose of the high altitude tests is to gather a wide range of effects data bearing on both the offensive and defensive aspects of nuclear attack upon incoming ballistic missiles, including warhead kill mechanisms and electromagnetic blackout effects on both radar and communications. On mile-long Johnston Island's limited acreage, crowded around and between the runway and ramp areas, were the missile launch complex and a line of more than 30 instrument rocket launchers, together with the many other necessary testing and support facilities. World War II bomb shelters were utilized for housing the command post of the Joint Task Force and other stations manned during the launch event, including those of the Scientific Readiness Team and Launch Control Group. This radar unit, scanning the sky for electromagnetic effects data, is representative of the test equipment set up and operated by the scores of technical projects. The launch vehicle groomed to carry the nuclear warheads to test detonation altitudes was the Thor missile. In the early plans, it was scheduled to do the job for 2 and possibly 3 nighttime bursts at various altitudes above the Earth's atmosphere. For these tests, the Thor was modified to carry 3 scientific instrumentation pods to obtain key data in close proximity to the burst. Each pod was ejected from the launch vehicle at a predetermined position along the missile's trajectory. The Pacific Missile Range ship moored at Johnston tracked the missile in flight for range safety purposes. Other tracking units followed the rocket instrumentation and scientific pods and determined their accurate positions relative to the detonation. Positioned at various distances from Johnston Island were 9 test ships, including the downrange anti-missile measurements program ship American Mariner, on loan from the Atlantic Missile Range. Pod recovery and surveillance ships were also on station, along with an aircraft carrier, whose marine helicopters evacuated from the island all personnel non-essential to the actual operation during each event. But Johnston Island itself was only the hub of an extensive network of land, ship, and aircraft instrument stations radiating in all directions, deep into both northern and southern hemispheres of the Pacific. Between the northern arc of Okinawa, Adak, Fairbanks, and Palo Alto, and the Polynesian islands of Tonga Tapu and Rarotonga, far south of the equator in Johnston Island's southern magnetic conjugate area, the roll call of islands hosting effect instrument stations evokes images both geographical and logistical, especially the latter, where over 200 ground instrument stations were prepared, installed, and manned. High-altitude effects data were also secured from aircraft platforms, more than a dozen planes took to the air from Hickam Air Base in Hawaii for each event, and 3 more from Nandi Airport in the Fiji Islands. Besides the instrumentation ships at Johnston Island, 2 minesweepers put to sea from Pearl Harbor for electromagnetic data reporting. And from its mooring at Pago Pago in Samoa, the instrumented motor ship Acania moved out prior to each shot day to be on its mid-ocean station. Johnston's opening event on May the 2nd was a daylight certification shot, testing all systems during flight trajectory, but without nuclear warheads. This proof test went as planned, achieving all programmed objectives. But hereafter, the course of shot events did not follow the scheduled script. The first 2 hot launches did not carry through to nuclear detonation. Neither of the failures was caused by the missile or warhead. On 8 July, the 3rd nuclear launch, another try for the very high-altitude Starfish event, was flawless, including the performance of the many auxiliary instrumentation rockets sent into selected trajectories about the birth region. Starfish detonated at its planned strength and height, producing wide upper atmosphere glow and extensive auroral effects. Here is how it appeared from Mount Haleakala, Hawaii's island of Maui. Recovery of the instrumentation pods ejected from the Starfish missile involved pre-dawn ship, patrol plane, and helicopter convergence in the splash area, drawn by radio signals, flashing lights, and green dots. As soon as the pods were fished from the water, they were taken to the Johnston Island recovery area for removal of the scientific instrumentation. The second bluegill attempt was made on 25 July, but a one-of-a-kind missile misadventure caused by a sticking fuel valve destroyed the Thor and its warhead on the pad. The pad itself suffered extensive damage, including long-life radioactive contaminants. Repairs to permit another try at bluegill caused a significant delay. Additional construction on Johnston Island during this incident, as well as the scheduling of more shots, reflected the value attached to the testing being carried out on Operation Dominant. 3 more high-altitude effects missile events were added to secure data at different heights. Also, 5 more over-ocean airdrops were scheduled, these to take place within the Johnston Island danger area. Besides a second Thor launch pad, the construction included facilities for the launch of XM-33 rockets, Nike Hercules missiles. The U.S. Army deployed a missile battery to provide launch support for the Nike Hercules missiles, which were scheduled both as nuclear warheads and instrumentation vehicles. On 15 October, high-altitude testing was resumed, resulting in another failure of a bluegill, this time due to internal missile guidance malfunction. This was the last such disappointment. All remaining launches culminated in detonation at their planned altitude. First came Czech, boosted to altitude by a Sargent-engined XM-33 rocket. Besides furnishing new basic scientific data on upper atmosphere phenomena, the tests fulfill the vital military aims of providing information on the offensive and defensive aspects of nuclear attack upon incoming ballistic missiles, as well as data on blackout effects on radar and communication. Meanwhile, the 5 additional weapon development airdrop tests in the Johnston Island danger area were conducted. To gain the scientific information required, the airborne array refined at Christmas Island was utilized as the sole diagnostic force, with the original C-130 aircraft joined by KC-135 jets carrying additional diagnostic gear. The makeup of the remainder of the test aircraft formation was generally the same as at Christmas, including the post-shot B-57 diagnostic cloud samples, this time staging through Johnston Island to conserve flight hours and to reduce pilot radiological dosage accumulation after cloud penetration. The air array was under the guidance of the Air Task Group Commander in one of the RC-121 aircraft, while overall control was maintained by the Joint Task Force Commander from Flag Spot in the Princeton near the drop area. Target rafts were again used as guideposts for orienting the air array, the point of aim for the B-52 device drop. The rafts were moored in the open ocean by the Navy task group in water as deep as 3 miles. Late in October, after the last airdrop test device had been developed, the series was pronounced a success, both in refinement of weapon design concepts developed for the Christmas test, and in further confirmation of the feasibility of the airborne diagnostic method for future testing. With Operation Dominic completed, the test apparatus roll-up underway, the time had come to evaluate the far-flung operation and its scientific results. Despite Dominic's unprecedented 4-operation complexity, with all the tests prepared under conditions of the greatest urgency in both time and circumstance, the 1962 series is regarded as the most productive since U.S. nuclear testing began. The analysis and correlation of Operation Dominic's wealth of test data will continue for some time. Nevertheless, the Atomic Energy Commission and the Department of Defense already have been enriched with vital inputs, both in new areas explored and information gaps plugged. This is reflected in the improvements of weaponry in the national stockpile, in new weapon design, and in the planning for future test programs, should the national interest require. On all counts, Operation Dominic proved to be a significant milestone in the ever-vigilant task of keeping the nation's ramparts secure.
Ladies and gentlemen, you've heard the reports that enemy planes are approaching. In less than 3 hours, an H-bomb might fall over Portland.
Like myself, I think you're going to be very interested in this story that we're going to tell you. And in this age of missiles and man-made moons, takes on added significance. There are no actors in this story, but there are a lot of people. The people of the city of Portland, Oregon, and what happened to them, or could happen to them, on a day that we'll call X. This is the land, between the mountains and the sea, between the snow-capped crater of Mount Hood and the Pacific. It's tall timber country. And this is the city, largest dry cargo port on the Pacific coast. And its people are friendly and rugged in the tradition of the Oregon Trail. Population, about 415,000, more or less. More or less about the size of Hiroshima. And this is what happened, or could happen, on a certain day called X. The sun came up at 6:31. Joe Fodek was there to observe and chronicle the event. The paper, Joe noted, was a little heavier than usual, but naturally he didn't stop to read the headline. And Mrs. Frank Stufel, Portland housewife, mother of 5, was concerned at 8:02.
Don, it's time to get up. You'll be late for school.
Children late and coffee boiling. And with these problems duly appraised, she turned to the woman's page of the Oregonian, thus managing to avoid the front page, which, after all, contained nothing but scare headlines. The time?
The time is 8:27. Wake up, Portland. It's a wonderful day today. Stay tuned to KOIN for the best of music and news. And now, we continue our wake-up show with more Transcribe Tunes.
At 8:36, the population of Portland increased by 1. Timothy James made his first comment at a local hospital and settled down to life in the 20th century. Like all communities, religion is important. The people, like its church architecture, are forward-thinking. At 9, a special service is being held. And at the busy port, 9:18, Ray Matthews, a longshoreman, loaded scrap iron bound for Japan. At 9:37, at the Central Fire Station, the men were busy with their morning chores, scrubbing hose, cleaning ladders, and shining the pumper. By 10 that morning, at the Harvey Scott School, the kindergarten class of Elsie McGlendon was much involved with the morning's activities.
Come to order, clerk will call the roll. Dean, Booty, Bowes, Earl.
And the twice-weekly meeting of the city council was much involved, too. The matter of sewer maintenance was one of the problems up for discussion. At police headquarters, the messages at 10:31 so far indicated 2 cars stolen, a drunken disorderly. An average day in an average American city.
Number 126.
126. A cat in a tree, 14 in Ankeny.
Except this day. This day is the one called X.
Attention all stations. Emergency. This is an air raid warning and tunnel rest radio alert. This is an air raid warning and tunnel rest radio alert. Enemy aircraft are over the alert. Stand by for 1 time. This is West. Return to County Transit Station. Time to Seattle, 2 hours, 30 minutes.
Portland warning point. Air raid warning. Enemy aircraft over Canada and Alaska. Time to Portland, 3 hours, 15 minutes.
Thank you. I'll notify the mayor. At 10:32, Jack Lowe, the city's civil defense director, received the words. Enemy planes have crossed the pole. Probably they carried H-bombs. Likely one, maybe two, are headed for Portland. From there, delivered.
Clerk, gentlemen of the Consul, I've just received information that enemy planes are approaching this area. Just authorized the sound of the evacuation. The Consul will be in recess and we will immediately reassemble at the Emergency Operations Center.
And so this day, called X, which began in such an ordinary way, is no ordinary day. At 10:35, the banshee wail of the siren echoes the warning, and the city prepares for survival. Cities in the United States are considered critical targets, and Portland is just one of them. And it's so hard to know in advance how any man will react when that day comes. There will be those like Ben Conrad the mechanic, who has heard the sirens before in practice, and who will disregard them. And there are those like Tom Cook who can't go. He's one of the power load dispatchers for all electric power in the Northwest. These men are expendable. Others can and do go.
Radio alert. Normal broadcasting will be discontinued for an indefinite period. Civil defense information will be broadcast in most areas at 6:40 or 12:40 on your regular radio receiver. I repeat, this is a Conrad radio alert. Normal broadcasting will be discontinued for an indefinite period. Civil defense information broadcast in most areas at 6:40 or 12:40 on your regular radio receiver.
When the sirens sound, some cities go underground, take to shelter, particularly if there's little warning. But Portland evacuates according to a well-thought-out plan. The question is at 10:45, on the day called X, will it work? Quietly, without panic, the city organizes, becomes mobile the best it can. Civil defense is not apart from normal city functioning. The same utilities involved in caring for a city in peace are those equipped to care for her in an emergency. When the siren sounds, each man knows his responsibility. Public buildings follow a pattern well learned in practice. The idea, to move out of the city, to move fast, but with caution. Like other Portland mothers, Mrs. People moved her family to a prearranged location outside the city beyond radiation range with necessary supplies. function. Evacuation can be controlled, and if necessary, the city can be reorganized. The Portland plan revolves around the local government with Mayor Terry Shrunk its head. Government must survive if its people are to survive. Civil defense is government operating in an emergency.
Morning, Mr. Mayor. Well, the situation looks pretty bad right now. We don't know exactly what's happening, but we do have planes over Alaska and Canada.
Ladies and gentlemen, you've heard the reports that enemy planes are approaching. Less than 3 hours, an H-bomb might fall over Portland. Mr. Jack Lowe, Civil Defense Director, will coordinate activities here. Jack, what's the situation?
Mr. Mayor, according to our latest reports from SONAD, enemy planes are still headed this way at 450 knots. That will put them just about there on the Alaska-Canadian border. I'd say we still have about 2.5 hours if Portland is where they intend to make a drop.
What's the condition of the evacuation movement?
Well, we have very scanty reports now, so there's only been 15 minutes, but we can check with the police and with the traffic engineer and see if we get what information we have. I have no information yet as to how it's presented.
By 10:55, the heads of utilities, Red Cross, military liaison, Civil Air Patrol, Weather Bureau, and all city departments are functioning as a civil defense. While city commissioners and bureau heads remain behind working with their departments at the emergency seat of government, their families are among those evacuating. By 11, the operations officer is receiving reports on the evacuation of the city, and he is the reporter of the day. Traffic, time, weather, and in the operations center's broadcast studio, the time is...
The time is 11:10. This is an official civil defense broadcast. Enemy aircraft are over Canada and headed this way. Normal broadcasting has been discontinued until after this emergency has passed. You are now tuned to Conelrad and will receive official information and instructions on this frequency. Keep your radio tuned to this frequency. Remember, there is a traffic plan for the evacuation of the city. All cars in the downtown area must follow the green light. They will lead you out of the danger area by the quickest route. Do not try to cross the flow of traffic. Follow the green light. Turn with traffic. Proceed with care.
John Carpenter, a sportscaster, becomes the warning voice. The people of Portland know his voice. Trust it. In 1955, Portland held a practice mass evacuation. The heart of the city was cleared in 34 minutes. It's safe to say that practice evacuation will be responsible for saving a great many lives this day. Should the bomb fall, many will be killed. The more that move out of the city, the greater the chances of survival. Pedestrians are helped out of the city. The great dangers are jam-ups and bottlenecks. Whirling over the city, a police helicopter reports traffic movement to the operations center.
Copter 1 to dispatcher. Copter 1 to dispatcher.
Copter 1, go ahead.
Barber and Slavin traffic moving very slowly, bumper to bumper. Suggest 1 or 2 lanes be diverted east on Hamilton. Over.
10-4, 11:31.
And at 11:32, at the operations center, Police Chief Hildrunner receives a suggestion, and with traffic engineer Fred Fowler, he works out a way to divert traffic. Motorcycle policemen are sent to split the load onto a side road. There's no way of knowing if Portland actually is an enemy target. But with 3 hours of warning, and the time fading fast, it's vital that all roads lead to safety, that all roads be kept open, allowing people to evacuate from the potential target area. Meantime, county and state police halt and divert incoming traffic away from the target area. Should a bomb fall, fire and utility equipment must be available to move back into the city to restore services. And so trucks of all sizes, of all varieties, speed to points outside the city by a detailed plan. 11:45, the men and equipment have arrived at the dispersal areas away from the target. Auxiliary police and auxiliary firemen are also in action.
This is serious business, man. We anticipate attack. Secure your vehicles as best you can. Turn off the ignition. Put on the tarps on the fire apparatus. Take the radiation instruments with you. Move immediately to dispersal area. Move as quickly as you can to dispersal cover. I say again, move to dispersal cover.
Around the dispersal area, in local public buildings, emergency kitchens are in operation. Rumors are everywhere. Facts are hard to find. But back underground, at the operations center, with time running out, only facts are considered.
According to information we have just received from Western Air Defense Command, the situation remains the same. Enemy aircraft are still approaching in this direction. If they continue on this same course, we can expect an attack in this area anytime after 21:47 Greenwich time. That is 1:47 p.m. Pacific Standard Time. And now I would like a brief situation report from all departments on how we stand. First, John, what is the fallout situation?
Jack, according to our latest weather information, the winds will continue in a northeasterly direction at about 10 knots. Let's face facts, gentlemen. If we have a blast on target, downtown Portland, it'll be hours and probably days before we can get back in.
Engineering, Gordon Burt.
We have reports that 80% of the city-owned public utility equipment has been successfully evacuated from the city. However, there is one group of electric company trucks caught on the west side. We're working now on a plan to get them out.
Fire Department, Chief Simpson.
Fire Department's initial dispersal plan is in effect. Several units have already moved out to their respective dispersal points. Engine 24 and Engine 30 are currently fighting a residential fire, and they will stay on the job until this fire has been controlled.
Police, Chief Hillbruner.
As for police activities, the city is about 65% evacuated. Traffic appears to be moving at about 15 miles an hour outbound. State and county police have set up an effective roadblock diverting inbound traffic, thus enabling us to use all lanes for outbound traffic.
Emergency medical, Dr. Metter.
City hospitals are continuing to evacuate. Emergency hospital units are functioning in Forest Grove and Mount Angel. Others should be heard from soon. You might be interested in knowing that en route, one boy and twins were born.
Gus Lang, welfare.
As the reports continue, it is obvious that the Portland plan is working smoothly. Only 7 years earlier, Portland had no civil defense. It was then that the idea that civil defense was not to be separated from normal government evolved. And in 1952, a 1 mil tax levy to finance the plan was put on the ballot by a unanimous decision of the City Council. After civil defense leaders went out and campaigned, the people voted to tax themselves to protect themselves. And later, the city charter was amended to assure continuity of government, so that in an emergency like this, should the executive branch become casualties, they would automatically be replaced by a legally established line of succession of other experienced city officials. The people, as now and after the emergency, are assured of continuity of their government.
Schools report complete evacuation. There's no panic among the children. They've rehearsed this before. Reports from industries indicate approximately 90% evacuation. I think we're doing quite well.
And so, at 1:25, with some 22 minutes till 0 hour, Portland seems to be doing quite well. Should a bomb fall now, city officials and city services will be able to carry on. In the meantime, vital messages are passed on to maintain contact with state and county headquarters.
Okay. W7SAA from W7BS.
Upstairs in this unique underground operations center, an emergency telephone system is functioning as the details of evacuation are reported and relayed. Part of the civil defense levy went to a comprehensive microfilming project supervised by Will Gibson, city auditor. More than 3 million documents and records that go back to the first handwritten city council minutes in 1851 have been microfilmed. Duplicates of laws and the engineering records without which the city cannot function are here. And so, in time of disaster, the records are preserved. And now, with a moment to breathe, some can take time for coffee in a built-in cafeteria. It's time to talk with families which have been evacuated. And it's time to be alone, think of the future. And there's even time for those who need it now to rest. 300 can live here for a week, eat, sleep, and breathe. The operations center has its own water supply, its own electric power, even its own purified air. At 1:30, on this day called X, the air outside is strange and silent. Almost all its people have gone. And at 1:32, as directed by the mayor, the siren sounds once more. Take cover. The evacuation is stopped, and there is nothing to do but wait. Back in the operations center, the day called X reaches its climax.
Time now, 1:47. Enemy bombers are probably overhead.
What happened after that moment, we leave you to contemplate. The one thing is certain, Portland has a plan for the survival of its people and the continuity of its government. You know, actually, the survival of this entire nation depends upon the ability of federal, state, and local governments to carry out their responsibilities in the event of a massive nuclear attack. Each new scientific development in the weapons of war presents a new challenge. The people of Portland, through working together, they're ready. If there really were a day called X. How about you?
This is a radiological defense operations room, a nerve center for survival, which we hope we will never have to use. But since war could come, this room is ready, and so are others throughout the country.
Radar. Louisville, 740 people, thank you. 5 metric ton producer.
The USA, almost 3.5 million square miles. And at the other end of our scale of size, tiny dust-like particles. They too have a name. And the name is fallout, radioactive fallout. A large-scale nuclear attack on the United States could produce a patchwork pattern of fallout covering 2/3 of the nation. More than 2 million square miles in a single day. In this 2 million square miles, more than 100 million people living well beyond the destructive range of blast and heat could be subjected to dangerous or deadly amounts of radiation from fallout. Carried upward 15 miles or more by the mushroom cloud, spread laterally by shifting winds at all altitudes, fallout from a single thermonuclear blast could severely contaminate a 60-mile strip downwind from ground zero. 1,200 square miles within an hour of explosion. 4,000 square miles in 6 hours. All of us, even in small towns and on farms, live within fallout range of a likely target. Furthermore, since these targets are often only a few hundred miles apart, fallout patterns can overlap, intensifying the danger. How do we know all this? From practical experience. A thermonuclear test in the Pacific in 1954 produced a highly contaminated area 20 miles upwind and 220 miles downwind, with a variable width up to 40 miles. Large enough to reach from Washington, D.C. to New York City, along the densely populated eastern seaboard. In this 7,000 square mile area, there would be enough radioactivity to threaten seriously the lives of all who failed to take shelter before fallout arrived. Let's look at it in another way. Let's assume that industrial St. Louis were hit by a weapon with the explosive equivalent of millions of tons of TNT. Depending on winds, fallout could extend 40 miles into southwest Illinois in an hour, to Terre Haute, Indiana, 150 miles to the east in 7 hours, and to Wheeling, West Virginia, another 325 miles within 24 hours. Total drift, more than 500 miles.
Civil defense tests have brought the problem into sharp focus. In one exercise, an imaginary force of 500 bombers severely damaged this country's key industries. Yet, effects from fallout posed a more serious threat to the nation's survival than did the devastating but more localized effects of blast and heat. Let's examine some of the problems. Although most sources of water are located well outside of big cities, the wide drift of fallout could cause serious contamination of our surface water supplies. Fallout from a nuclear attack could gravely affect the nation's agriculture. Food supplies in fields or in open storage could become dangerously contaminated. Possibly they could be recovered for later use. But what about future harvests? They too could be dangerous if grown in seriously contaminated soil. Cattle, horses, and sheep might have to be kept out of pastures for a long time. In short, fallout from nuclear attack would threaten us with thirst and famine, as well as with sickness and death from direct radiation. That is why our survival as a nation can depend on how well we prepare to defend ourselves against radioactive fallout. And there is a defense against fallout. Before we examine our radiological defense programs, let's take a look at the basis of the problem. As every youngster learns today, there is nothing new or mysterious about radiation. A Roentgen, which we call an R, is a standard unit for measuring radiation. In an average lifetime, a human being is exposed to perhaps a dozen Roentgens. This exposure comes from natural radioactive elements in the Earth and cosmic rays from outer space. The human body withstands continued exposure to small radiation doses. It is when the rate of delivery is high, or the total dose in a short period is large, that recovery cannot keep pace with damage. Exposure of the whole body in a short time to 600 or more Roentgens of radiation will almost certainly be fatal. People receiving 200 Roentgens or more in a short period of time will get radiation sickness. Those receiving 600 or more in a short period of time will die. For your protection, shelter is the answer, since highly dangerous doses can be produced by fallout radiation. This is what happens.
3, 2, 1.
About 85% of a nuclear weapon's energy results in light, heat, and blast. But 15% of the released energy is radiation. This is of two types. The first, initial radiation, is emitted from the fireball shortly after detonation. Since for large weapons it generally does not spread beyond the blast area, initial radiation is of minor concern in the overall problem of radiological defense. It is the second type, residual radiation, that creates the fallout problem. Its production can be described simply. When countless billions of atoms in a large megaton weapon are blasted apart, hundreds of pounds of highly radioactive material are produced. When such a bomb bursts at or near the ground, tens of thousands of tons of earth and debris are carried as high as 15 miles in the mushroom cloud. This tremendous cloud becomes a floating carrier, which drops tiny radioactive particles back to Earth. Where these particles land depends on a combination of three factors. One, their shape and size.
even the largest, may be no bigger than a single grain of sand. 2, the height to which the radioactive cloud rises. And 3, the direction and speed of winds at various altitudes. Fallout deposit resulting from the combined effects of these conditions is generally divided into 3 categories: close in, intermediate, and delayed. Close-in fallout usually settles within a few hundred miles of the burst and reaches the ground within 10 to 20 hours. It is made up of the heavier particles in the cloud. Intermediate fallout descends within a few weeks of the detonation. Since the particles are small, they remain in the air for weeks, covering many thousands of square miles. Sometimes they are driven to Earth by rain or snow. Delayed fallout is composed of very small particles that may drift completely around the Earth several times and may not descend for months or years. Radiological defense personnel, RADEF personnel for short, are primarily concerned with close-in fallout.
As you can see, close-in fallout is our real problem in radiological defense. And the problem becomes even more complicated because the speed, range, and direction of fallout depend upon ever-changing wind and weather conditions. Large particles fall fast and land relatively near ground zero. Smaller particles fall slowly, land further away. Winds, which vary at all altitudes and seasons, affect the pattern of these deposits. With winds variable at different altitudes, the spread of fallout will result in the effects of all winds acting upon it. For this reason, radiological defense officers cannot use surface wind direction alone as a basis for forecasting fallout. Radioactive materials decay with time. You might say they cool down. After all fallout is down and radiation has been measured, knowledge of decay rates permit estimates of how hot it will be days and weeks later. With this information, civil defense can estimate when it will be safe to evacuate or to leave shelter. Remember this rule of thumb. There is a 10-fold decrease in radiation rate for every 7-fold increase in time after detonation. For example, a level of 1,000 R per hour at 1 hour after the explosion would be reduced to 100 R per hour 7 hours following the explosion. At 7 times 7 hours, or in 2 days, the level would be down to 10 R per hour. At 7 times 49 hours, or at the end of 2 weeks, the level would be reduced to only 1 R per hour. But remember, until decay reduces radiation to tolerable levels, there are only 2 safeguards against it. Distance, that is evacuation to safe areas, or mass, which is shelter. Underground shelters covered by at least 3 feet of earth, or basement shelters, the types recommended by civil defense, will give substantial protection. This is why we believe that most people who live beyond the areas destroyed by blast and heat can survive fallout if they will follow civil defense instructions.
As serious as fallout is, we can cope with it through action as individuals and through an effective radiological defense program. An active program carried on by federal, state, and local governments. At the federal level, representatives of many agencies meet regularly to perfect methods of collecting and analyzing fallout information and to find the best means of advising our states and communities about fallout conditions after a nuclear attack. An important important part of the radiological defense program is a series of monitoring networks stretching across the country. A combined system of federal, state, and local stations, thousands in all, which will gather information on radiation levels as soon as fallout begins to spread downwind. On the basis of this information, transmitted by top priority communications of every type from coast to coast, early, effective action for our protection would begin at state and local levels. In some cases, evacuation. In most cases, shelter. The federal monitoring network at Weather Bureau stations, Federal Aviation Agency sites, Department of Defense Air Weather Service units, and other government organizations operates on a round-the-clock basis. At every level of government, radiological defense units are being equipped and trained to act. Fallout forecasts, issued several times daily by Weather Bureau stations, will be useful in estimating local fallout areas if we are attacked. Certain stations gather weather information that is processed to give an estimate of the areas in the nation where fallout could be expected. Sent over a vast teletype network to civil defense and other offices throughout the nation, the coded information is charted on maps to show sections threatened by fallout. Lines on the map show where and when the fallout is likely to arrive. At all civil defense regional offices, radiological defense personnel help state RADF staffs in their region. Regional officers arrange for the distribution of training kits, supervise the contribution of federal funds to state RADF work, set up RADF training in their region, and coordinate RADF activities of all federal agencies in the region. After an attack, the regional RADF staff will collect, analyze, and evaluate all fallout information received from the state, and will coordinate the flow of information to and from federal and state control points. The state RADF people will use both ground and aerial monitoring units to make broad, statewide surveys. Entire highway systems and key transportation routes, major industrial and supply sites, as well as urban and rural areas, will be checked as rapidly as personnel safety permits. The state RADF unit also maintains working maps. It plots and correlates data, analyzes reports. By transmitting its summaries, it links regional and local offices. But it is at the local government level that radiological defense will be on an immediate, down-to-earth basis. Local RADF will perfect and test detailed plans for operations. Keep all equipment in readiness condition. Train and rehearse operating crews so they too will be ready. It will set up communications between its units and for liaison with state RADF organizations. When an attack warning sounds, local survival plans go into effect. Monitors will report to their stations. The public will be advised to take shelter or evacuate. After attack, first reports of radiation measurements will come from sheltered monitoring stations. As soon as radiation levels permit, police, firemen, highway maintenance men, conservation officers, everyone trained to use survey meters will begin the vital work of getting detailed data to control centers. From this information, current situation reports will be prepared. Using these reports, RADEF officers can answer urgent questions raised by local authorities. Can short survival missions be undertaken? Is our water safe? What roads are safe? Are feed, livestock, and crops contaminated? When can emergency teams begin decontaminating and reclaiming property? When will radiation die down enough to make it safe for people to leave shelters for brief periods and for utilities to be put back into service? Survival of whole communities can depend on the accuracy of answers given to these questions. Local RADEF plans also cover places where people work. Employers must shoulder their responsibilities by providing fallout shelters for workers. At work and at home, everyone must understand the hazards of fallout and the value of shelter. Every family must provide for its own survival for at least 2 weeks. Since radiation levels outside would often be deadly, fallout shelters will protect the most people. Both the underground and indoor basement shelters recommended by Civil Defense can be very effective. They must be stocked with a 2-week supply of food and water. First aid supplies, flashlights, and a battery radio with Conelrad frequencies 640 and 1240 clearly marked on the dial should be included. Factories, offices, apartment houses, and schools all must provide shelter. Remember, too, that personal decontamination is important. Fallout particles can be brushed from clothing and washed from skin. All in all, a big program. Some of it in being, some under development. But it takes action to fulfill this program. Radiological defense training is being expanded. First priority, train more instructors. At 3 national centers, in classrooms, on calibration ranges, learning theory and practice, more than 2,000 adult students each year are taking basic or advanced courses. Courses that will qualify them to instruct classes back home. A total of 600,000 monitors must be trained to make radiological defense effective in every community. To support this program, radiation survey meters are being distributed widely. These instruments, which measure radiation levels in terms of Roentgens or milliroentgens per hour, are the backbone of radiological defense. In addition to survey meters, dosimeters, instruments which measure total doses of radiation, are being distributed to the state and federal agencies. Radiological defense instrument kits for use in science classes are being distributed to 15,000 high schools throughout the nation. With the aid of this equipment, our young people will acquire a better understanding of radiation and will be better prepared to contribute to the nation's RADEF efforts. Improved radiation measuring instruments and multiple-purpose computers are being designed, built, and tested. An intensive public education program to tell the American people about radioactive fallout and shelter is underway. For it is an informed public that will mean the difference between success and failure in meeting this threat. Informed people in homes and factories and offices must know their personal responsibilities for shelter and protection. Informed officials at all levels of government, from Washington, D.C. to the smallest town council, must understand the RADEF program and help make it work if the people of the nation are to survive.
Charleston, West Virginia, KC 0900 check.
Our efforts now to build a workable radiological defense will pay off richly by helping to deter aggression and by saving countless lives if nuclear attacks should come.
This film is concerned with the effects of high-altitude nuclear explosions on radars, optical sensors, and communications. To understand how nuclear explosions affect such systems, it is first necessary to understand the interaction of explosions with the atmosphere. We will discuss this interaction or phenomenology for explosions at very high altitudes in the ionosphere and in the upper atmosphere. We shall not consider the blast and other lethal effects that nuclear explosions produce. The air we breathe consists almost exclusively of gases and are electrically neutral in their ordinary condition. The number of electrons shown here is of course symbolic rather than literal. As we progress towards the top of the atmosphere, however, the gases are exposed to powerful X-ray, gamma ray, and ultraviolet radiation from the sun and from cosmic rays. Above about 90 kilometers, radiation increasingly breaks more of the molecular gases into their atomic or single atom state. This dissociation, primarily from the ultraviolet radiation, affects as much as 50% of all molecules at altitudes of about 100 kilometers. The cosmic and particle radiation also causes ionization. Detachment of the single electron leaves the remainder of the atom or the molecule with a positive charge. This can happen to single atoms or to either one of the atoms of a molecular pair. Being electrically charged, free electrons are attracted to and tend to recombine with positive ions at the first opportunity, thus again creating electrically neutral units. If an electron does not recombine with a positive ion, it can be taken out of circulation by temporary attachment to a neutral atom or molecule, which then has a negative charge until the electron is snatched away by the stronger attraction of some positive ion. Because of the strong recombination tendency, ionized gases will not remain in that condition
unless there is a constant supply of energy to cause new ionization as fast as the previous ions can recombine. The first significant quantities of naturally occurring free electrons begin to show up at an altitude of approximately 60 kilometers, which we therefore consider as the bottom of the ionosphere. From there on up to heights of several hundred kilometers, free electrons become more and more prevalent. Their rate of increase with altitude is non-uniform, and there are several clearly defined regions which exhibit distinctive electromagnetic characteristics. The first region is the D region, frequently called the D layer, between 60 and 90 kilometers above the Earth. Centered at roughly 120 kilometers is the E region. At 200 kilometers, the F1 region. And finally, at some 300 kilometers, the F2 region. In the relatively dense atmosphere of the D region, there are sufficient numbers of diatomic positive ions that no free electron can exist for long without either combining with one of these ions or becoming attached to a neutral particle. There is no solar radiation to produce a resupply of new ions in the Earth's shadowed or night regions. However, cosmic radiation provides a source of ionization both during the day and at night. Nevertheless, the absence of solar radiation at night allows recombination to proceed more rapidly than ionization, and the free electron density is reduced compared to that during the day. Up in the F region, however, the extremely rarefied atmosphere allows a large free electron density to exist throughout the night. Shortly after sunrise of the following day, the D region ionization, consisting mostly of electrons, is reestablished by solar radiation. We are concentrating attention on atmospheric ionization processes because the free electron density at the various altitudes determines the signal propagation behavior of many of our radar and long-range communication systems. Now, in what way do high-altitude nuclear explosions affect these free electron densities? To begin with, roughly 70% of the total energy produced in a nuclear explosion is emitted in less than a microsecond as a flash of X radiation. A few percent more of the bomb energy is emitted as prompt gamma and neutron radiation. Most of the remaining energy appears as directed motion or kinetic energy of the expanding explosion debris. Delayed gamma and beta radiation from this radioactive debris material emits some 5% of the total weapon energy over a longer period of time. We will examine the effects on the atmosphere of nuclear detonations at 50 kilometers, 100 kilometers, and 250 kilometers altitude. First, let us consider the events that follow the detonation of a sub-megaton weapon at a moderate altitude of 40 to 50 kilometers. Most of the X-ray energy is deposited near the burst point, heating air to incandescence. The prompt gamma and neutron radiations from the explosion can, on the average, travel large distances before colliding with air particles. Therefore, the ionization caused by such collisions is spread out laterally over a region several hundred kilometers in diameter. Radiation in an upward direction increases the D-layer ionization, which we symbolize with the blue shading. It is important to realize that the greatest range of these radiations will be upward and horizontal, because the exponential nature of our atmosphere causes its density and absorbing qualities to decrease very rapidly in upward directions. Specifically, each 15 kilometers change in altitude in either direction will make about a 10-to-1 change in air density. At 45 kilometers altitude, the density is approximately 1,000th of the air density at sea level. Coming back to our explosion, the X-rays heat the surrounding air to incandescence. Within a tenth of a second, the tremendous radiant energy output and gas expansion processes have created a fireball of superheated air several kilometers in diameter. Inside the fireball, both the air and the smaller central mass of expanding weapon debris are fully dissociated from the molecular into the atomic state, and the atoms themselves are highly ionized. In another view, a high-velocity shock wave is seen to race outward from the radiation front, which is still at a temperature on the order of 10,000 degrees. The fireball expands at a slower rate to a diameter of 10 kilometers within about 5 seconds, during which time it also begins rising upward at a rate approaching 300 meters per second due to the buoyancy of its heated low-density gases. We watch the remainder of the explosion development through a camera located directly underneath the fireball. Sometime during the first minute, the rising cloud of fireball and debris material from explosions at this or lower altitudes interacts with the surrounding air, and the fireball transforms into a torus or donut shape. Both gammas and high-energy electrons or beta rays are continuously emitted from fission fragments in the debris. The cooling fireball and debris mixture, no longer luminous, continues to rise and expand, reaching a diameter of about 40 kilometers at 1 minute. It finally stabilizes some minutes later at an altitude of about 100 kilometers until dissipated by atmospheric winds. We will next consider a nuclear explosion of large yield at an altitude of 100 kilometers, where the atmosphere is less than 1,000, as dense as it was at 50 kilometers. The initial heavily ionized X-ray fireball will be an order of magnitude larger than from our low-altitude shot, and much more tenuous and less brilliant in appearance, because so much of the X radiation escapes to large distances, over which it causes a significant ionization increase without luminosity. The atmosphere is so rarefied that the highly penetrating prompt gamma and neutron radiation from the explosion will produce only negligible concentrations of new ions in horizontal and upward directions. Ions are produced in the D layer and at lower altitudes. The hot and rapidly expanding fireball rises ballistically with something over 5 times the average velocity seen for the lower shot. Its diameter is some 300 kilometers after the first minute. Magnetic forces progressively distort the rising material, elongated along the geomagnetic field lines. Maximum altitude on the order of 1,000 kilometers is reached in 7 or 8 minutes. With the upward ballistic impulse exhausted, the material, being heavier than the ambient atmosphere, tends to fall back to denser regions on the order of 150 to 200 kilometers. The fall is oriented primarily along the Earth's geomagnetic field lines. The diameter is several hundred kilometers with a thickness perhaps a tenth as great. The diffuse radioactive debris continues emitting both gamma and beta radiation with significant intensity for many hours after the explosion, thereby continuing to produce ionization. Most of the ionization from gamma radiation occurs at altitudes near 30 kilometers. However, ion lifetimes are very short down in such relatively dense air. Reattachment is so rapid that we actually find the greatest net population of gamma-produced free electrons up at the D layer altitudes, where the reattachment rate is much lower. The other major radiation from the debris, the super high-velocity electrons from fission fragment decay, referred to as betas, are less penetrating than the gamma rays. Most of the downward-directed betas dissipate their energies in the D region at 60 to 80 kilometers, adding to total ionization in that region primarily by collision with neutral particles. The area of the ionization region created by beta radiation will correspond roughly in size to the area of the stabilized debris material itself. Actually, being electrically charged, the beta particles are constrained to follow the Earth's geomagnetic field lines. Thus, a region of ionization commonly called the beta patch is caused by these downward traveling electrons. The few beta particles that start out parallel to the field line will continue to follow them. If the particles encounter the field lines at an angle, however, they will spiral around them. Here we see beta particles streaming along the magnetic field through the fireball and debris of a burst. Those electrons ejected upward may be trapped along the Earth's magnetic field lines and are mirrored back and forth if the reversal or mirror point is substantially clear of the atmosphere. If the mirror points are too low, the electron will dip into the atmosphere at each end of its shuttle and soon will be lost by collision with air molecules. This collision excitation mechanism is generally accepted as one of the causes of auroral displays. Thus, a nuclear burst at sufficiently high altitudes can produce auroras at conjugate points in both hemispheres. Since the debris from a nuclear detonation begins radiating at the moment of the explosion, its conjugate point auroral effects can be expected to change location as the debris rises and intersects with successively higher magnetic field lines. Note that when the debris is located below about 200 kilometers, most of the electrons shuttling along the field lines will be lost in the atmosphere on their first pass, with very little mirroring back to the other conjugate point. We will next consider a nuclear explosion at altitudes above 250 kilometers. Mass asymmetries in the construction of the nuclear device and its carrier can be very important and are observable in this 400-kilometer explosion. At this very high altitude, a substantial change occurs in the mechanism of containment, the forces which slow and finally stop fireball and debris expansion. While ordinary hydrodynamic pressure resists the explosion expansion at low altitudes, geomagnetic back pressure becomes increasingly important at altitudes above 100 kilometers. The heavily ionized debris and gases in an expanding fireball are electrically conducting. So the Earth's magnetic field tends to be excluded from that region, creating a so-called magnetic bubble, which presses back against the expanding gases. At great altitudes where air pressure is negligible, expansion might continue indefinitely if it were not for a collisionless process in the debris and surrounding air plasmas, which permits a degree of coupling between the weapon debris and the ambient atmosphere. The degree and nature of the coupling are believed to be very dependent on yield and burst altitude, but these processes remain major unknowns in the phenomenology of very high altitude nuclear explosions. Looking back again at another weapon effect on the atmosphere, most of the prompt gamma radiation is deposited between 25 and 30 kilometers altitude. The air molecules are ionized. The free electrons split off and start spiraling around the magnetic field lines. Each spiraling electron emits minute radio waves. All of the electrons exist nearly simultaneously, and the minute radio waves add together. This is the primary source of the high-altitude electromagnetic pulse, or EMP, which is a broadband pulse of radio frequency energy radiated from the deposition region. When this electromagnetic pulse is coupled into a system, very large voltages and currents may be induced. Other EMP generating mechanisms are operative in other burst regimes, but are outside the scope of this film and will not be described. In brief summary of the important effects on the ionosphere, we see that a nuclear burst in the 40 to 50 kilometer region produces first a heavily ionized fireball area. while the flash of prompt gamma and neutron radiation causes significant ionization lasting for several minutes and extending to large distances horizontally and upward, but with only minor range and duration in downward directions. Debris radiation continues to create intense ionization in the region of the fireball while it rises. At all explosion altitudes substantially above 50 kilometers, the immediate radiation produces almost completely ionized fireball regions of multi-kilometer dimension. Its strong but radially decreasing ionization extends to many hundred kilometers. The fireball and debris materials rise to maximum heights of from 100 to 1,000 kilometers as the first height is raised from 50 kilometers to the 100-kilometer region. Unlike debris from the lower explosions, material from the higher explosions falls back from its maximum altitude, ultimately settling around 200 kilometers. With rising burst altitude, greater quantities of beta particles and charged debris particles will shuttle north and south along the magnetic field lines to conjugate points in both hemispheres. Both beta ray and debris interaction with the atmosphere at those points will, for a number of hours, create significant ionization with vivid auroral effects and radio disturbances. Debris gamma and beta radiation will also enhance ionization in the D region at both conjugate points. Other phenomena associated with irregular structure in nuclear burst ionized regions are also important to communications, infrared, and radar systems. One is the eventual development of magnetic field-aligned filaments, or stria, in ionized regions. The irregular ionized structure also results from the upwelling or heave of explosion-heated air above 100 kilometers altitude. These phenomena are treated in greater detail in Part 2 of this film, which considers the effects of atmospheric ionization on military systems.
presented Mr. John Dalton with a royal medal for his development of the theory of definite proportion, usually called the atomic theory of chemistry. This presentation set an official seal upon the emergence of the scientific theory of an idea of matter which had existed for over 2,000 years as a belief, unsupported by experimental proof. chemistry was becoming an exact science, thanks to accurate methods of weighing and analysis introduced in the 18th century. Dalton was able to work out fairly accurately the relative combining weight of many elements. In his new system of chemical philosophy, published in 1808, Dalton pointed out that these combining weights, which are constant for each particular compound, must be related to the weight of the ultimate particle or atom of the combining element. Thus, the atomic theory was reborn. According to Dalton, matter is composed of small particles which cannot be split up any smaller. These particles he called atoms. Our diagrams illustrate his ideas, but not, of course, the real shapes of atoms. He believed, secondly, that all atoms of one element are exactly alike, and differ from the atoms of other elements, and have a characteristic relative weight. Thirdly, he believed that atoms are indestructible and cannot be created. Fourthly, that chemical combination occurs between small whole numbers of atoms. Such combinations of atoms are now called molecules. In any given compound, all molecules are alike. Dalton invented a system of symbols to represent the atoms of the different elements. He used these to show how the atoms combine to form molecules. Though some of his conclusions proved wrong, atomic theory was the foundation upon which the chemistry of the 19th century was built. Painstaking chemical analysis based on Dalton's theory and research arising out of Avogadro's hypothesis concerning molecules and gases enabled accurate atomic weights to be assigned to the elements. A connection was sought between atomic weight and chemical properties, and in 1869 this was supplied by Mendelev's periodic table, which arranged all the elements then known in families according to their atomic weight and properties. Thus, the column headed by carbon contains a group of elements with actually similar properties. The next column contains another group of similar elements, and so on. Now, from left to right, the elements are arranged in ascending order of atomic weight. The whole table fits together like a puzzle. The properties and place in the table of unknown elements were predicted, and the discoveries of later years proved the accuracy of these forecasts. The decomposition of solutions by an electric current was used as a means of chemical analysis in the early 19th century. By careful measurement, Michael Faraday was able to show that in such cases, a definite quantity of electricity was associated with definite amounts of the elements produced at the electrode, that is, with definite numbers of atoms. Hence, he suspected that electricity itself might be atomic by nature. It was established that there were two kinds of electricity. Unlike charges attracted each other. Like charges repelled each other. By convention, these two kinds of electric charge became known as positive and negative. In a solution like common salt and water, the sodium chloride exists as ions or charged atoms of sodium and chlorine. When the solution is electrolyzed, the positive sodium ions travel towards the cathode and the negative chlorine ions to the anode.
work of many scientists on liquids and gases led to the theory that in all matter, molecules are in a state of perpetual motion. The botanist Robert Brown was the first to see in his microscope what is now called Brownian motion. This is the intricate motion imparted to fine particles in suspension in a liquid by the impact of molecules. One can imagine the tiny particles being pushed about by the their active molecules. Each molecule is so small that 27 million are contained in 1 cc of gas at 0 degrees centigrade and normal pressure. The thinnest soap bubble that can be made by ordinary means is about 100,000th of a centimeter thick. In this space, about 1,000 molecules could lie side by side. Each of these molecules would be 3 or 4 times the size of a small atom. This much was known at the close of the 19th century, which Lord Rutherford sums up in these words.
At the close of the 19th century, the labors of the chemist have resolved the matter of our material world into 80 or more distinct elements, and the atoms of these elements appear to be permanent and indestructible by the forces then at our command.
The physicists of the 19th century were not less active than the chemists. Faraday investigated the conduction of electricity by liquids. Later scientists investigated the passage of electric current through gases at low pressures with this kind of apparatus. Air is pumped from the tube until a luminous discharge passes from cathode to anode. As evacuation proceeds, brilliant rays are seen streaming from the cathode. The rays become invisible as pressure is reduced, but they still cause a faint green glow on the walls of the tube. This bell-shaped vessel shows the behavior of the cathode rays more clearly. At first, the current passes from the cathode to the edge of a fluorescent screen beneath it. Next, the glow of the cathode rays is clearly seen around the cathode itself. As the pressure continues to fall, the rays will disappear, but their presence is revealed by a powerful green glow when they strike the fluorescent screen. These cathode rays can be made to cast a shadow of an object in their path. This proves that they travel in straight lines from the cathode. The rays are capable of transmitting energy. The little vanes in this tube are turned by energy supplied from the motion of the tiny particles rushing up from the glowing cathode beneath. It can be proved that the rays are negatively charged. A wire connected to a plate on which the rays fall will discharge a positively charged electroscope. In 1897, Sir J.J. Thomson devised an apparatus to measure the ratio of charge to mass of these particles, which had been named electrons. He was able to make an estimate of the actual mass of the electron. In this apparatus, a luminous spot shows where the electron beam from the cathode fell on a fluorescent coating on the end of the tube. This beam could be deflected in one direction by an electrostatic field between charged plates, and in the other direction by a magnetic field. These fields could be adjusted to balance each other, and from their strength, the velocity of the particles could be calculated. Then, from the strength of the magnetic field alone, and the deflection caused by it, the ratio of charge to mass could be found. From experiments such as these, the mass of the electron has been estimated at 1/1840th of the mass of the hydrogen atom. Sir J.J. Thomson's own description of this tiny object has been preserved for us.
Could anything at first sight seem more impractical than a body which could only exist in vessels from which all but a minute fraction of the air has been extracted, which is so small that its mass is an insignificant fraction of the mass of an atom of hydrogen, which itself is so small that a crowd of these atoms, equal in number to the population of the whole world, would be too small to have been detected by any means then known science.
Thus the existence of a negatively charged subatomic particle, the electron, was established beyond all doubt. It was even thought possible to photograph the track of an electron. This was done by an ingenious apparatus invented by Professor P.T.R. Wilson. During the war, most people saw the vapor trails left by high-flying aircraft. Wilson, while investigating the ionization of gases by charged particles, built a chamber in which such particles could be made to leave a vapor trail. It consisted of a glass-topped chamber filled with moist air. The bottom of the chamber is really a piston head, supported by the air beneath. Connected by a valve to the main apparatus is a large vacuum chamber. When the valve is opened, the air beneath the piston is sucked into the vacuum, and the piston drops sharply, creating an expansion of the moist air so that a cloud is formed. Now a charged particle from a source of radiation entering the chamber will ionize the gas along its path. Because of the sudden expansion, drops of moisture will condense on the charged atoms or ions along the path of the radiation and leave a visible trail. This is photographed by a synchronized electric flash. This apparatus, much improved since the original model, has proved invaluable in atomic research. Today, the electron is a commonplace. Any metal raised to red heat gives off electrons. The stream of electrons from this hot filament can discharge an electron current. This is made use of in the radio valve, where the electrons from the hot filament can be used to send and detect signals broadcast over long distances. On this radar screen, electrons act as the eyes of a ship as it makes its way down the crowded river to the sea. And on the television screen, electrons paint pictures for our amusement.
The electron owes its practical utility to its small. It's like the current in Shakespeare, say my use is great because I am so small.
The discovery of electrons raised big problems. Ordinary matter is neutral. For instance, it has no effect on an electroscope. Yet the cathode in this discharge tube can give off negative particles much smaller than atoms, which concern the density. Some sort of electrical equilibrium has been upset by the diffusion of negative electrons from neutral matter. Surely positively charged particles must have been left behind. Investigation of the so-called canal rays, first discovered by Goldstein in 1886, proved that this conjecture was true. If a series of small slits be pierced in the cathode of a gas-filled tube, a luminous ray can be seen streaming in the opposite direction to the cathode rays. These rays were subsequently found to be positively charged.
Sir J.J. Thomson used this discovery to build an apparatus in which the mass of the rays could be measured. A fine beam of positive rays was directed onto a photographic plate. A magnetic field produced the deflection of the beam horizontally. Similarly, an electrostatic field produced a vertical deflection. In both cases, the different velocities of individual particles produced a line instead of a spark. If both fields were applied simultaneously, the particles fell on the plate in a parabola. The position of this parabola in relation to that of the undeflected spot was determined only by the ratio of mass to charge. Thomson was able to calculate the mass of each particle. He found that each particular kind of positive ray consisted of charged atoms of the gas present in the discharged tube. Under certain conditions, the different types of glow due to positive and cathode rays can both be seen. These phenomena could only be explained by supposing that the neutral atom contained both positive and negative charges in equilibrium. The stream of electrons from the cathode detaches other electrons from the atoms of the gas through which they pass. These atoms immediately become positively charged and rush towards the cathode. If the cathode is pierced, they emerge as positive rays. The sequence of events resembles electrolysis, and these charged atoms of gas are called ions. A gas in which such conditions arise is said to be ionized. In 1896, Röntgen found that the green glow excited by cathode rays struck into glass was itself giving off rays which caused the fluorescent screen to become luminous. The rays could penetrate like metals, but not dense material like lead. The centerpiece of metal here is lead. The outer ones are aluminium. Lead stops the rays completely, but the lighter elements are penetrated and cast a lighter shadow. These powerful rays became known as X-rays, and doctors soon found that they could use shadowgraphs made with X-rays to see inside the human body. Dentists were able to study the internal structure of teeth. And industrial X-ray machines such as this one have been developed to search for hidden defects.
radioactive in any of the four houses. The curious call is radium, and devoted the rest of their lives to the study of radioactivity. The power of this radiation is easily shown. A scrap of radium embedded in a lead capsule ionizes the air to such an extent that the charge on the electroscope leaks away. The complex nature of this radiation and radioactive substance was revealed by reporting on a photographic plate its behavior in the magnetic field. A fairly weak magnetic field produced a deflection of lightly charged particles called ether rays. A very strong field draws further deflection of ether rays, and in the opposite direction, a deflection of heavier charged particles, so-called alpha rays. There remains a penetrating radiation unaffected by the magnetic field, the gamma ray. By 1902, the alpha ray was known to be a type of positive ray, the beta ray is electric, and the gamma ray to be electromagnetic waves, similar to X-ray. Curie and Laborde discovered that the rays from radium can manifest their energy in the form of heat. Here are two Dior flasks, which are tubes containing a radium source on the left and a barium source on the right. The barium flask also contains a coil of known resistance, which can be used to raise the temperature in the flask. Both flasks have thermometers. At the start of the experiment, the left-hand thermometer shows a higher reading owing to the heat from the radium. Next, the electric current was used in the coil. Heat from the radium was calculated as the amount of electricity used to raise the barium to the same temperature as the radium. Such experiment gave an increase of the great energy locked in the atom. 3 years after the discovery of radioactivity by Becquerel, Rutherford enclosed a radioactive gas called radon, which was surrounded by an outer state, from which all the air had been absorbed. The alpha rays coming from the gas penetrated the thin glass and collected in the outer tube. After a few hours, it was found that the outer tube contained the gas helium. Therefore, the alpha particles were atoms of helium. This was the first direct evidence of one kind of atom actually changing into another.
A great change in our ideas resulted from the discovery of the electron and of the spontaneous radioactivity observed in the heavy elements, uranium and thorium. Tommy and I were able to show in 1903 that radioactivity was a sign and measure of the instability of atoms, and that the atoms of uranium and thorium were undergoing a series of spontaneous transitions.
Uranium, during its transformation state, is by a whole new series of unstable elements, which ultimately break down and lead. The rate of change from one element to another may vary from a fraction of a second to millions of years. Only a few elements are normally radioactive. The majority are stable.
The next problem was to examine whether means could be found to break up the stable elements by artificial methods. Before this could be attempted with any chance of success, it was necessary to have a clearer conception of the structure of atoms. The idea of the nuclear structure of atoms, which I suggested in 1911, has proved very useful for this purpose.
Experimental evidence supported Rutherford's idea. Alpha particles from the radioactive source, emitted by a system, will expose immediately on the fluid. It goes on, faster, causes the radiation, going to scan the alpha particles like a heavy acid stone. Geiger and Marsden investigated the nature and extent of this gas.
Became clear
that to effect a veritable transformation of an atom, it was necessary to change, charge, or mass of the nucleus, or both together. Now, the minute nuclei of atoms are held together by powerful forces, and to effect their disintegration, it seems likely that a very concentrated source of energy must be applied to the individual atom. The bombardment of the nuclei by the energetic alpha particles of radium appears to be the most promising method for such a purpose.
In 1919, Rutherford found that nitrogen nuclei could be transformed by bombarding them with swift alpha particles, and that protons were ejected at high speed as a result. In effect, he added together helium and nitrogen, and changed them into oxygen and hydrogen. This was transmutation, the dream of the atom, which the nuclear theory had at last given up. Most significant of all, there could be no doubt that the proton, the hydrogen nucleus, was the fundamental particle in all atoms, the positive counterpart of the negative electron. How is the atom built up in these complex systems? Let us go back to our table of the elements. The atomic numbers represent the charge on the nucleus, and also number the elements according to their increasing atomic weight. Now consider each atomic weight. 1 for hydrogen, 4 for helium, 7 for lithium, and so on. Our figures are approximations to the nearest whole number, but they show that in most cases, atomic weights are at least twice as great as the atomic number. How could this difference between mass and charge be accounted for? Consider the atom of one element, say lithium. It has 3 electrons circling round the nucleus. This nucleus, we know, must have a positive charge of 3. So we put 3 protons in the nucleus. Each has a charge of 1 and a mass of 1. But the atomic weight of this is 7 approximately. So the nucleus must have 4 more protons added to it to give a mass of 7. Now we have upset the balance of the charge. 7 protons, 7 positive charges. 3 electrons, 3 negative charges. There is only one way to correct this. 4 electrons must be added. Now our charge is balanced. The negative charge of 3 electrons is balanced by the outstanding positive charge of 3 on the Such was the theory. But even in 1920, Rutherford suggested that there might be a neutral particle with the same mass as protons, which could account for the extra mass without affecting the charge. Ultimately, this proved to be another instance of his amazing insight. But in the years between, the drive to penetrate the secrets of the nucleus continued unabated.
collecting on the central wire as a result of continuous alpha particle emission can be measured. Development of radio valves enables the pulse current from each single alpha particle chamber or micro window to be amplified until it could operate a type of counter. Then Geiger and Miller developed an ionization chamber which could multiply the original effect by a principle known as gas amplification. Here is a modern Geiger counter, capable of counting at the rate of thousands per minute. Linked to it is an electric counter capable of high-speed recording. As the tiny strip of radium fitted with this rod is brought near the tube, the dials record the gamma rays from the disintegration of single atomic nuclei. These gamma rays are actually penetrating the walls of the tube, but charged particles can be counted by using a suitable type of tube. The ionization effect can be amplified and passed through a loudspeaker, so that each click represents the percentage of a single particle, or as in this case, the ionization caused by a single gamma ray. Then mode is to operate an oscilloscope in which cathode rays trace on the speed the effect of these nuclear explosions. Subsequent to this apparatus, economic disintegration and study and accurate measurements obtained. About 1920, Aston, working at the Cavendish Laboratory, designed this ingenious instrument known as the mass spectrograph. Positive particles or ions produced in the same way as in the Thunderstorm apparatus were allowed to pass through an electric field, which reflected the particles at varying angles according to their velocity. All particles of the same mass could be brought to a common focus on a photographic plate by means of a magnetic field of the right shape and intensity. In effect, Aston could weigh atomic nuclei very accurately. Work done with this apparatus showed that most of the elements accepted as individuals by the chemists were actually mixtures of two or more substances of different atomic weights. The atomic weights of the elements have been very accurately determined by many chemists. Very few of them could be expressed as complete cell numbers. Aston showed that chlorine, with its atomic weight of 35.5, is in reality a mixture in a definite proportion of two forms of the same element, one with an atomic weight of 35 and one with an atomic weight of 37. Such different forms of the same element were called isotopes, and subsequent research has shown the number of elements in which isotopes exist is very large indeed. Little by little, hundreds of experiments all over the world built up a store of knowledge about atomic nuclei. As time went by, experimental evidence and theory both emphasized the increasing probability that there did exist an uncharged particle of about the same mass as a proton. In 1930, Botha and Becker in Germany announced that they had noted what seemed to be an unusually penetrating gamma radiation produced by allowing alpha particles from polonium to bombard beryllium. The radioactive polonium gave off alpha particles which struck the beryllium. Radiation of some kind from the excited beryllium gave a high reading in the detector. Frederick and Madame Joliot-Curie measured the penetrative power of the radiation by inserting screens with varying colors. If these screens were of suitable density and thickness, most of them reduced the amount of radiation reaching the detector. But when screens containing hydrogen in the form of paraffin wax were used, a heavy increase of radiation was observed. In England, Sir James Chadwick confirmed the findings of the Joliot-Curie that this radiation consisted of protons. He suggested that the protons were ejected from the paraffin
by an uncharged particle of about the same mass as the proton. Imagine that this billiard ball is a proton. No stream of light particles like a liquid, no known type of wave, could have any more effect on such a body than these light grains have on a billiard ball. But another particle of equal mass has the opposite, just as this second ball about half a centimeter at first and in this way. A particle of unit mass, but without electric charge, and so very difficult to detect. Edward's reasoning recalled Lord Rutherford's suggestion in 1920, and the idea of a nucleus composed of protons and the uncharged particles, which were christened neutrons, was accepted. The field force around the nucleus acts as a barrier against the penetrative power of charged particles. Neutrons, however, being uncharged, can penetrate these barriers and strike the nucleus. The majority of nuclei are much heavier than the neutrons. If collision occurs, the neutron quickly bounces off and continues with a slight loss of speed. Now, paraffin is made up of carbon and hydrogen. Protons, or hydrogen nuclei, are no heavier than neutrons. So, in a collision, the neutron is able to transmit a large amount of energy to the proton. This is the explanation of the proton radiation observed by the Joliot-Curie and Sir James Chadwick. The neutrons once explained the existence of isotopes. Chlorine, for instance, has an atomic number of 17. That is, there are 17 electrons circling round a nucleus in which there are 17 protons. But chlorine has two isotopes. The atomic weight of one is 35, and of the other 37. If we add 18 neutrons to 17 protons, we get an atomic weight of 35. And in the 37 isotope, we have to add 20 neutrons to get the correct atomic weight. An isotope of hydrogen, called heavy hydrogen, has a nucleus consisting of the single proton of ordinary hydrogen plus one neutron. This nucleus, called a deuteron, has proved useful as a particle for bombarding atoms.
It became clear that to extend our knowledge, a more copious supply of bombarding particles of different kinds is necessary. Charged atoms of various sorts can be produced in vast numbers by the electric discharge of the vessel, and then accelerated by the use of high voltage. In this way, we have been able to obtain very experimental transmutation in denser beams of proton and alpha particles, while the discovery of heavy hydrogen has given us a new prototype of remarkable efficiency transmuting atoms.
Here at the Cavendish Laboratory in Cambridge, the experts of this modern alchemy of transmutation go about their business. The purpose of these huge electrical machines is simply to use electrostatic forces to accelerate beams of charged particles to very high energy, and with these atomic bullets, to bombard the atoms of various elements in order to see what changes occur in their structure. This laboratory grew out of the converted lecture room, where, in 1932, Cockcroft and Walton operated one of the first successful machines to produce high-speed particles, and obtained significant results by bombarding lithium. The machine you see is a descendant of their original set. Ions are produced inside the large mushroom-shaped insulator, and are accelerated down the rearmost tower. The bombarding tube continues down into the room beneath, where the stream of charged particles can be bent by a powerful magnetic field and directed toward the target. outside Kensington is preserved, the observation cabinet and accelerating tube of the original voltage quadrupler used by Cockcroft and Morgan. Three cylindrical metal electrodes are arranged vertically inside a glass tube where a high vacuum exists. Protons emerge from a narrow positive ray canal at the top of the tube. As the protons descended, they passed through intense electrical fields by which they were accelerated and sharply focused. At the bottom of the tube, they struck the element set up as the target for bombardment. Any particle ejected from the target element passed through a micro window and caused scintillations on a fluorescent screen, which could be observed through a microscope. With lithium as the target, a startling result was obtained. Alpha particles of high energy were ejected. This result received wide publicity. Through the press, the public imagination was stirred by the vague implications of the phrase, splitting the atom. But to understand the significance of this result, it is necessary to appreciate one of the most important aspects of Einstein's theory of relativity. Let us hear Professor Einstein himself.
It followed from the special theory of relativity that mass and energy are both different manifestations of the same, a somewhat unfamiliar conception for the average mind. Furthermore, the equation E is equal mc squared, in which energy is first equal to mass multiplied with the square of the velocity of light, shows that very small amount of mass may be converted into a very large amount of energy, and vice versa. The mass and energy were in fact equivalent, according to the formula mentioned above. This was demonstrated by Vogler and Walton in 1932 experiment.
In 5 non-chemical terms, scientists summed up their results thus. It seems not unlikely the lithium isotope of mass 7 occasionally captures a proton, and the resulting nucleus of mass 8 breaks into 2 alpha particles, each of mass 4, and each with an energy of about 8 million electron volts. This reaction, which you see here, can be written down. We start with lithium of mass 7, placing 7 at the top left corner of the lithium symbol. Its nuclear charge is 3, so we add the figure 3 at the bottom left corner. The lithium is bombarded by protons. That is, hydrogen is added rather forcibly to the lithium, so we put down plus H. Hydrogen has a mass of 1 and a charge of 1. As a result of the reaction, we get 2 alpha particles or helium atoms, each with a mass of 4 and a charge of 2. Note that the two sets of numbers add up to the same on each side of the reaction. 7 plus 1 equals 4 plus 4. 3 plus 1 equals 2 plus 2. The actual masses concerned in the reaction are known from mass spectra. On the left, they total 8.0241 mass units. On the right, 8.0056 mass units. There is a difference of 0.0185 mass units. Measured in grams, this amounts to 3.07 times 10 to the minus 26. It is this amount of mass which has been converted into the energy released in the reaction. In other words, the relationship between mass and energy is a constant, and is expressed in Einstein's equation E equals mc squared, in which energy is put equal to mass multiplied by the square of the velocity of light. So, to find the energy released, we substitute for m the amount 3.07 times 10 to the minus 26. And for c squared, we substitute 3 times 10 to the 10 all squared, which is the square of the speed of light in centimeters per second. Thus, the energy released expressed in erg is the product of these values, namely 27.6 times 10 to the minus 6. Now, the energy of each alpha particle released in the reaction can be directly calculated. It is 8.5 million electron volts. Or, more conveniently, 8.5 MeV. Thus, in our equation, we get E equals the sum of these energies, that is, 17 million electron volts. Measured in erg, this becomes 27.2 times 10 to the minus 6. Thus, one calculation gives 27.2 times 10 to the minus 6, and the other 27.6 times 10 to the minus 6. A sufficiently close approximation to show that Cockcroft and Walton were correct, and that great energy can be released by splitting the atom. Man has set his foot firmly on the road towards the unlocking of great knowledge and power. All over the world, atomic physicists sought machines of higher and higher voltage with which to reach a goal that was still hidden. This machine is known as the electron. In it, electrons are whirled around at fantastic speeds by new methods using small high-frequency currents combined with powerful magnetic fields. High-speed electrons cause gamma radiation, which is betrayed by this sensitive detector. Even a thick screen is easily penetrated by this radiation. Energies as high as 8 million electron volts can be obtained on this machine, and in the United States, electrons of 100 million electron volts have already been produced. Giant synchrotrons are now being built to accelerate positive ions. Hidden behind thick concrete barriers to absorb the dangerous gamma radiation is this latest type of linear electron accelerator, in which electrons pass through a series of alternating magnetic fields arranged in line along a corrugated tube, known as a waveguide. Eventually, this machine will hurl electrons at its target with an energy of 5 million electron volts. Older in conception, but impressive in size and shape, is this electrostatic generator, designed to accelerate positive particles such as protons and neutrons. And this is one of the newest Spanish draft machines to be built in England. These are so called after the American scientists who first designed them. Electric charge was sprayed onto a moving belt inside this tower and carried to the top of the accelerating tube, where the high potential thus generated is used to drive the particles down towards the target at great speed. When in operation, the machine is enclosed in a high-pressure casing, which permits a potential of 2 million volts to be built out. Most impressive of all in their suggestion of a well-dimmed world are these 1 million and 2 million volt generators in the Cavendish laboratory at Cambridge.
This is a cyclotron, one of the most famous of these accelerators. The inventor was Professor E.O. Lawrence of the University of California. The accelerating chamber or tank is fixed in the middle of the apparatus, between the poles of a very powerful electromagnet. The principle is ingenious. The tank, which is completely evacuated, contains two hollow D-shaped electrodes, to which a high-frequency alternating current is fed. Minute quantities of the gas which is to provide the ions are admitted. The ions are produced in the center of the tank by electrons from the small arc or filament. Once produced, they are sucked into one or other of the Ds by the powerful electric field. But this movement of the ions takes place between the poles of a big magnet.
Consequently, the ions will travel with a circular motion in the magnetic field. The alternating voltage accelerates the particles each time they cross the gap from one D to the other, so that they are whirled round faster and faster until finally they are led off towards the target by means of a charged deflector plate. Here, an element is being set up and bolted into the target chamber, ready for bombardment. Nowadays it is known that almost all elements, if bombarded by neutrons, can be made radioactive for varying periods. Irene and Frederick Joliot-Curie first produced artificial radioactivity, and Professor Fermi made brilliant advances in this field. As the operator moves off towards the control panel, he passes through the water screen, 3.5 feet thick, which protects the scientists from the intense radiation produced by beams of accelerated particles. Now he begins to switch on the complicated high-frequency installation which feeds current to the beam. To build and operate such machines, atomic physicists become engineers, overcoming step by step problems of high vacuum, screening from harmful radiation, construction of special magnets, and so on. For the production of neutrons, deuteron beams are usually found the most convenient. When the deuteron strikes the target, it splits up, liberating a neutron, which easily penetrates to the nucleus. At last, the full power begins to flow. Through the observation window can be seen the arc in the center of the tank, and round it the pulsation of the accelerating particle. Some idea of the Newton's effect on a nucleus can be given by this simple experiment. Imagine that the saucer is the nucleus of an atom. One might think that the neutron would go straight in and out on the other side, like this. Now let us fill the saucer with marbles to represent the particles in the nucleus. If we let the neutron marble roll down into the nucleus, it will jostle the others but remain in the saucer. The nucleus has captured a neutron. It becomes unstable and gives off its excess energy as beta and gamma radiation. If the neutron marble enters the saucer with a somewhat greater energy, one or more marbles will be knocked out. Thus, neutron capture can eject particles from the nucleus and cause disintegration. Outside the laboratories, the world was disturbed by the strident voices of evil men and the ever louder rumble of approaching war. But in 1939, atomic scientists made a fateful discovery. Professor Frisch, now at work in England, was closely concerned in this.
Early in 1939, Professor Hahn and Dr. Strassmann in Germany found that uranium, bombarded by neutrons, gave rise to what appeared to be an isotope of barium, only about half the atomic weight of uranium. Professor Lieschen Metzner, who had previously worked with Hahn and Strassmann, was by then Swede. He told me of their puzzling discovery, and together we considered the possibility that the uranium nucleus sometimes broke into two halves. We found that such a process, although quite unexpected, was indeed compatible with what we knew about atomic nuclei. If we were right, a great amount of energy was to be released in such a process, and I was able to show this experimentally.
Hahn and Strassmann's evidence that the disintegration of the unstable uranium gave rise to elements such as barium in the middle of the atomic table was purely chemical and required a physical confirmation before it could be accepted. The uranium nucleus is unstable and radioactive, as is known from its ability to emit an alpha particle. If a uranium nucleus could indeed capture a neutron, becoming more excited and splitting into two approximately equal fragments, it was to be expected that a large amount of energy would be released in such a process, sufficient fragments being hurled apart with great velocity. Professor Frisch obtained confirmation that this was so
in an experiment essentially similar to the one shown here. Uranium was placed in the ionization chamber, which was placed over the end of a bombarding tube through which high-energy neutrons could be sent. The chamber was connected as you see to an oscilloscope. The trace you see here is made by alpha particles from the radioactive uranium. Now the high-tension set is switched on, and the uranium is bombarded by neutrons. On the screen of the oscilloscope, the fission pulses reveal the large amounts of energy released when uranium atoms are split. If each fission had to be provoked by elaborate apparatus like this for accelerating particles, there was no hope of deriving useful energy from the process. But each fission was found to be accompanied by the release of a few neutrons. One neutron had been used to provoke the fission. The fission itself produces more than one neutron, and is thus itself capable of provoking more than one fission, and so on. There is thus the possibility of a self-sustaining chain reaction. The reaction can begin without any neutrons being supplied from outside, since a few fissions are always taking place spontaneously. These would supply the fused neutrons. While these facts were being investigated, the political high tension in Europe sparked over into actual war. Years of aggression had at last forced the Western democracies to challenge the attempt at fascist domination of the world. Under wartime security, research on the use of atomic energy was pushed ahead. What was the problem to be attacked? The possibility of a fast chain reaction suggested an atomic bomb. There are two isotopes which make up the bulk of natural uranium. The atomic weight of one is 238, of the other 235. Over 99% of natural uranium is U-238. U-238 undergoes fission only with very fast neutrons. Many neutrons are scattered by uranium atoms and lose the speed necessary to cause fission. So, a divergent chain reaction will not take place in uranium which is predominantly U-238. U-235, on the other hand, undergoes fission with neutrons of any velocity. It seems possible that a controllable chain reaction might be achieved by using slow neutrons to cause fission in U-235. Using pure uranium containing both isotopes, a pile was built, in which uranium rods were embedded in a mass of pure carbon in the form of graphite. Neutrons produced in the uranium were slowed down by collisions with the light atoms of the carbon, the moderator as it is called, giving them a chance to cause fission in U-235. A slow, controlled chain reaction was achieved on December 2nd, 1942. If natural uranium as a moderator were replaced by a small amount of pure U-235, slow neutron reactions would give place to fast neutron reactions. Fissions would occur, but so many neutrons would escape before hitting another nucleus that no chain reaction would build up. But if the amount of U-235 became larger than a certain critical size, a fast chain reaction would take place in less than millionths of a second. This would produce a violent explosion. A simple mechanism for an atomic bomb thus suggests itself. Take two pieces of U-235, each smaller than the critical size, but which, if placed together, exceed that size. They are driven together, and so U-235 became bomb material number one, and its separation from U-238 became a war priority. The behavior of U-238 in a pile is also of great importance. Low neutrons are sometimes captured by U-238. No fission is caused, but this nucleus becomes U-239. This is unstable. A beta particle is emitted, causing a change to a new element with different chemical properties, Neptunium-239. This new element is also unstable. Another beta particle is given off, forming another completely new element, Plutonium-239. Now, Plutonium-239 has fission properties similar to U-235 and will be built up by this process of neutron capture and subsequent beta disintegration throughout the uranium in the pile. Being a different element, it can be separated by chemical means from the uranium and used also for a bomb. So, plutonium is bomb material number 2. Huge plants for the production of pure U-235 and of plutonium arose in the United States. By 1943, it had become plain that Great Britain was fully extended in war production. In consequence, a nuclear physicist crossed the Atlantic to continue with American and Canadian colleagues the brilliant work already done. The main practical effort and most of its prodigious cost now fell on the United States, where very active research has been going on since 1939. The processes were laborious, and at all times elaborate precautions had to be taken by workers on the atomic pile and in the chemical laboratories because of the ever-present dangers from gamma and neutron radiation. Danger signs and warning signals, lead and concrete shields, remote controls, detectors, protective clothing. These were the everyday equipment of the men who worked to make the material for the bomb. At last, in the desert of New Mexico, the first atomic bomb was set off under conditions of great secrecy. Thousands of calculations, years of work, reached their climax in this moment of dreadful splendor. Within a few weeks, the bomb burst upon Japan, and the news of it upon a startled world, which has now seen this supreme destroyer in action 5 times in all. We are aware now of the compelling urgency of the situation created by the bomb. We know that war must be banished, or else our civilization may die, as Hiroshima died on that summer morning in 1945. The tale has been told in full by those who lived through it. A city destroyed in an instant, 60,000 people dead, many of them flesh burned, thousands more by blood, many of them strange sicknesses caused by gamma radiation. For a short while, the world was content to accept the fact that atomic energy, by destruction, had brought peace. Then came the question, can this power be controlled to serve mankind? Professor Einstein has recorded his opinion.
To give any estimate of when atomic energy can be applied to confront this purpose is impossible. What now is known is only how to use a fairly large quantity of uranium. The use of quantities sufficiently small to operate, say, in a car or an airplane is as yet impossible. Presumably, all materials which may be used for such purposes will be among the heavier elements of high atomic weight. Those elements are relatively scarce because of their lesser stability. So, though the release of atomic energy can, and no doubt will bring a great deal to mankind, that may not be for some time.
The core of the problem is to turn the atomic pile into a heat engine. The release of energy in a pile results in the generation of heat. If the reaction is allowed to run fairly fast, a cooling system is necessary to absorb the heat. To control the rate of reaction, rods of cadmium or some such substance must be introduced which can absorb neutrons if lowered into the pile. Now, if the cooling fluid, probably helium gas, were passed through a heat exchanger containing water tubes, the water could be heated up and turned into steam. Most of this part of the installation would have to be screened off by heavy concrete or water shields and operated by remote control. The steam could be used to drive turbo generators to provide electricity in a powerhouse or in a big ship. This adaptation of the atomic pile as a source of heat energy is now being tackled in the United States and Great Britain. The use of radioactive byproducts from the pile is also being investigated. Medical research is now employing new tracer techniques based on radioactive elements. In this test, a radioactive sodium salt is being used to check blood circulation time. The Geiger counter picks up the radioactivity from the sodium. Now the doctor prepares to inject the sodium into a vein in the patient's foot. The radioactivity will be picked up by the counter as the sodium in the blood reaches the patient's groin. The injection is made and the scientist starts his stopwatch. The radiosodium travels up the leg in the bloodstream. The counter is shielded from outside radiation by a lead block to the slot beneath. Now, 10 seconds have passed, and the counter reveals the arrival of the radiosodium. From such experiments, it is hoped to devise a test to help prevent some of the complications which follow childbirth. Other possible sources of atomic energy are suggested by what is known as the generation of solar and stellar energy. Under conditions of tremendous heat and pressure, complicated nuclear reactions are provoked, resulting in the building up of helium nuclei from hydrogen. In this process, large amounts of energy are released. Perhaps man may one day obtain energy by building up heavier atoms from the lighter ones. Meanwhile, the representatives of the United Nations in conference strive for some formula to banish the atomic bomb and permit the blessings of atomic energy to be used for peaceful ends. Great Britain's research establishment at Powell is under the direction of Dr. Cockcroft.
You have seen the story of a remarkable scientific achievement based on the work of scientists of many nations, but owing most of all to the work of Rutherford and the School of Nuclear Physics which he developed. The final achievement of the released nuclear energy for war is due largely to the scientists and engineers of the United States, stimulated and helped by British physics. We have now the task of using the immense power of nuclear energy for peaceful purposes, for the production of radioactive materials, for medical and biological research, and for the generation of heat power. With our present knowledge, it is possible to design nuclear power stations which will produce power at a modern efficiency. Until we acquire operating experience of these plants, we do not know how economical they will be, nor are we sure of overcoming all the technical difficulties which will occur in a large-scale development of nuclear power. Nevertheless, there is a real promise that over the next few decades, world power resources can be greatly increased, and that the very great benefits will be obtained will do much to increase standards of living. It is the hope of every scientist that nuclear energy will lead to the establishment of a world organization for the effective control of all weapons of mass destruction, and through this, for the abolition of war.
From Dalton's theory to atomic power. It is a long road, but the landmarks are clear. With the atomic theory as a basis, a pretty complete picture of the elements of our material world was fitted together during the 19th century. The discovery of electrons, the realization of the nature of positive rays, the strange powers of X-rays revolutionized conception of the nature of matter and of the atom itself. The study of radioactivity, first investigated by Becquerel and then by the Curies, led Lord Rutherford to make the greatest single advance in atomic theory. He pictured a small heavy nucleus in the atom round which the electrons revolve. In 1919, Rutherford discovered how to change one element to another by bombardment with alpha particles. He suggested that the nucleus of the atom might contain protons,
and uncharged particles of about the same mass. In 1932, scientists could say with certainty that the atom contained electrons carrying unit negative charges and a nucleus built up of protons carrying unit positive charges and of neutrons, uncharged particles equal in mass to protons, whose existence was proved by Sir James Chadwick. In 1932 also, Cockcroft and Walton split the lithium atom by bombardment with protons and found that mass could actually be translated into energy in perfect accord with Einstein's theory. Atomic disintegrations provoked by great machines became a commonplace of well-equipped physics laboratories. In 1939, uranium fission was first noted. The possibility of a self-sustaining chain reaction suggested the wholesale release of energy. Controlled chain reactions were achieved in the atomic pile. The imagination of the world has been stirred by the prospect of adapting such piles to use as sources of heat energy and as sources of radioactive materials for use in medicine. In research laboratories, the scientists are even now writing fresh pages in this unfinished story. But overall, the smoke of the atomic bomb hangs like a pall. If we are to reach the future that promises so bravely, the peoples of the world must see that this new power is wisely used.
Should there be a nuclear attack, many billions of them would fall from the sky and settle to Earth, releasing radiation that could cause sickness or death in the area where they fall. Flaming fireballs in space. We call them stars. And there are millions upon millions of them. Each star, like our own sun, is a raging nuclear furnace. It shoots out showers of particles too tiny to be matter as we conceive it, along with invisible forces that we call radiation. This radiation and these particles travel through space at fantastic speeds until they strike some other matter which may make new flares of radioactivity. They strike wandering asteroids, moons, and planets such as our own. Everything in space, Earth included, we don't worry about the small amounts of natural background radiation. Amounts increase, so do the dangers. crater area, there is almost total destruction from blast and heat. And now, large amounts of pulverized debris and molten earth are pulled up into the mushroom cloud. This is where radioactive fallout is formed. The radioactive atoms produced in the explosion join with the particles of earth and debris. Mushroom-shaped clouds form and climbs high. It now contains billions of highly radioactive particles of matter that we call fallout. The strong winds of the upper altitudes go to work on the cloud, blowing it off in one or more directions. Gravity tugs on the particles. The larger and heavier ones sink toward the ground, while the lighter particles continue to drift with the wind. Some of the lightest particles remain suspended in the upper atmosphere. As time passes, their radioactivity grows weaker, so that the longer they remain aloft, the less dangerous they are. But the heavier particles, spread by high-altitude winds, fall to the ground within 24 hours. Several miles from the explosion, they are about the size of table salt or fine sand. These are the most dangerous, because they carry the greatest number of radioactive atoms, and so emit the largest amount of nuclear radiation. Which brings us to an all-important fact. Deadly as radiation can be. And this gives us an invaluable ally. Time. Suppose a nuclear explosion takes place at 12 noon. By 1 o'clock, the total force of the residual radiation is at a high level. By 7 o'clock, it's down to 1/10. In 2 days, although still dangerous, it's only 1/100. But in 2 weeks, it's only 1/1000. With this decay rate in mind, consider radioactive fallout conditions which might confront us after a massive attack. Within an hour, fallout would be a serious problem in the vicinity of explosions which occur on or near the ground. By 7 hours after the attack, the fallout area covers more and more of the country as the prevailing winds expand the fallout in a downwind pattern. 24 hours. 48 hours. Without shelter, millions would face death. A few days later, those who have taken shelter will survive. In many areas, people can even leave shelter for brief periods of time to carry out important tasks. Within 2 weeks, most people can leave their shelters for longer periods as the radioactivity decays to lower levels. The lesson is obvious. We must shield ourselves from radiation through the dangerous period. To do this, we need more than time. Fortunately, we have another ally. Distance. The greater our distance from the fallout particles, the less radiation we receive. You would receive less radiation in the middle of a tall building than you would receive on the top or bottom floors, because there would be more distance and partition between you and the source of the radiation, the fallout particles which would cover the roof and the ground around the building. Only an insignificant amount would get inside. And finally, along with decay rate and distance, you have still another and very important ally. Mass. When highly radioactive fallout covers our immediate area, we can shield ourselves through the most dangerous period by using the sheer weight of any material. But the protecting material must be heavy. To shield out some 99% of the radiation, you would need about 5.5 feet of wood, or 2 feet of earth, or 1 1/3 feet of concrete, or a half foot of steel. Even though the thickness of these
material varies, they all weigh the same. Taking a house as an example, it offers a small amount of mass and distance from radiation, but not enough protection in an area of heavy fallout. The solution is plain. Fallout shelters are the best defense against nuclear radiation, whether in a home for a single family or a large community type in an apartment building. They offer the kind of protection from radiation you would probably need in case of a nuclear attack. The key then is the amount, the total dose of radiation received. We measure radiation the same way speed is measured by a speedometer. Only instead of a speedometer, we have a rate meter. And instead of miles per hour, we measure the rate in Roentgen per hour. We need not enough to affect his health. This same healthy person would need medical care if he received more than 200 Roentgens within a few days. 300 Roentgens in the same period would cause severe radiation sickness or possibly death. And as we go beyond 300 Roentgens, the danger of death increases rapidly. So now we see why shelter is vital. The difference between accumulating a large dose because of little or no shielding and a small dose because of adequate shielding is the difference between death and life. No clothing, of course, could possibly provide enough shielding. However, if you were to be in the open during fallout conditions, clothing would keep the particles from touching your skin. There is no such thing as a fallout suit, but ordinary clothing would help until you could reach the safety of a shelter. Then the fallout particles can be brushed off and outer clothing removed. If fallout settles on your food, the food itself is not harmed, since radiation damages only living tissue. And you can easily decontaminate it using almost the same methods you use in everyday food preparation. Actually, even if you accidentally swallowed some fallout particles, it wouldn't kill you. The effects, if any, probably wouldn't show up for years. Still, since there is a possibility of long-term effects, such as shortened lifespan, cancer, or hereditary damage, it's wise to remove the radioactive particles by simply washing, wiping, or peeling. But it's vital to remember this. Neither water nor chemicals can destroy radioactivity. The fallout particles can only be moved or washed away. Only time can reduce their potency. And what of water? Well, here again, the same rules apply. If necessary, you could drink water containing fallout particles without worry or immediate harm. The chances are you wouldn't have to for long. The water helps to wash itself through the natural processes of sedimentation and filtration. And swiftly moving rivers like this would carry most fallout particles downstream. In still waters, most particles would settle quickly to the bottom. Others might remain suspended in the water for a long time, while a small percent of the radioactivity would dissolve. The normal processing of a water treatment plant would make it safe to drink. And water coming from a covered well would be safe from radioactive contamination. There is no problem with breathing, for air is not contaminated once the fallout is on the ground. Fallout is not a poison gas. If ventilation is needed in the shelter, a simple inverted U fitting on a ventilating pipe will keep fallout particles from entering the pipe and getting inside.
Surviving a nuclear attack means more than just waiting in a shelter for radioactivity to decay to safe levels. Survival, reconstruction, and recovery would involve decontamination in many areas. A very difficult job.
Unit 8 at Elman Morse. Growth rate 15 reference per hour.
Fallout would have to be removed from important areas by street sweeping. And the remaining particles should be flushed out of the way. Consumption would be grown in areas that had received the least fallout. The reason we would be able to grow and eat food planted in this land is the transfer of radioactivity from soil to plant is extremely low. Survival can only come through knowledge. The basic facts we must all know are relatively simple. First, there is nothing new about radiation. It has always been with us. What is new is the vast amount we will be exposed to as a result of nuclear explosions. Much of this danger would come to us in the form of fallout. But we are not without personal weapons or defense. One of these is time. Radiation decays, and so we would not have to take maximum precautions indefinitely. Another defense is distance. Radiating particles 50 feet away, for instance, would not affect us as much as particles a few feet away. And our third defense is mass. Any material with enough weight will keep the penetrating rays from hurting us. The greater the weight of the material between us and the particles, the safer we will be. The best way we can use all three weapons of defense is with an adequate shelter, thick enough to shield off a good part of the radiation until it has decayed to safer levels.
That's why food remains good no matter how much radiation has passed through it.
Fallout accidentally swallowed with water or food will do you no immediate harm. But for long-term safety, it's best to wash, wipe, or peel the food and filter the water. Even if you were caught outside under fallout conditions, ordinary clothing would keep the radioactive particles from touching your skin, but you would still need to find shelter quickly. If we remember these facts, if we act on them intelligently, we can increase our chances of surviving nuclear attack. And the key to survival is adequate shelter. That is why the federal government has a nationwide fallout shelter program. The goal is adequate fallout shelter space for every man, woman, and child. This goal can be reached. For with knowledge of radiation, we can face the facts about fallout.
take action to protect ourselves, and learn how to live in the nuclear age. But should there be a nuclear attack, many billions of them would fall from the sky and settle to Earth, releasing radiation that could cause sickness or death in the area where they fall. Contains billions of highly radioactive particles of matter that we call fallout. The strong winds of the upper altitudes go to work on the cloud, blowing it off in one or more directions. Gravity tugs on the particles. The larger and heavier ones sink toward the ground, while the lighter particles continue to drift with the wind. Some of the lightest particles remain suspended in the upper atmosphere. As time passes, their radioactivity grows weaker, so that the longer explosion, they are about the size of table salt or fine sand. These are the most dangerous because they carry the greatest number of radioactive atoms and so emit the largest amount of nuclear radiation. Which brings us to an all-important fact. Deadly as radiation can be. And this gives us an invaluable ally. Time. Suppose a nuclear explosion takes place at 12 noon. By 1 o'clock, the total force of the residual radiation is at a high level. By 7 o'clock, it's down to 1/10. 2 days, although still dangerous, is only 1 to 100. But in 2 weeks, it's only 1 to 1,000. With this decay rate in mind, consider radioactive fallout conditions which might confront us after a massive attack. Within an hour, fallout would be a serious problem in the vicinity of explosions which occur on or near the ground. By 7 hours after the attack, the fallout area covers more and more of the country as the prevailing winds expand the fallout in a downwind pattern. 24 hours. 48 hours. Without shelter, millions would face death. A few days later, those who have taken shelter will survive. In many areas, people can even leave shelter for brief periods of time to carry out important tasks. Within 2 weeks, most people can leave their shelters for longer periods as the radioactivity decays to lower levels. The lesson is obvious. We must shield ourselves from radiation through the dangerous period. To do this, we need more than time. Fortunately, we have another ally. Distance. The greater our distance from the fallout particles, the less radiation we receive. You would receive less radiation in the middle of a tall building than you would receive on the top or bottom floors, because there would be more distance and partition between you and the source of the radiation, the fallout particles which would cover the roof and the ground around the building. Only an insignificant amount would get inside. And finally, along with decay rate and distance, we had still another and very important ally. Mass. When highly radioactive fallout covers our immediate area, we can shield ourselves through the most dangerous period by using the sheer weight of any material. But the protecting material must be heavy. To shield out some 99% of the radiation, we need about 5.5 feet of wood, or 2 feet of earth, or 1 1/3 feet of concrete, or a half foot of steel. Even though the thickness of these materials varies, they all weigh the same. Taking a house as an example, it offers a small amount of mass and distance from radiation, but not enough protection in an area of heavy fallout. The solution is plain. Fallout shelters are the best defense against nuclear radiation. Whether in a home for a single family, or a large community type in an apartment building, they offer the kind of protection from radiation you would probably need in case of a nuclear attack. The key then is the amount, the total dose of radiation received. We measure radiation the same way speed is measured by a speedometer. Only instead of a speedometer, we have a rate meter. And instead of miles per hour, we measure the rate in Roentgen per hour. We need them. Not enough to affect his health. this same healthy person would need medical care if he received more than 200 Roentgens within a few days. 300 Roentgens in the same period would cause severe radiation sickness or possibly death. And as we go beyond 300 Roentgens, the danger of death increases rapidly. So now we see why shelter is vital. The difference between accumulating a large dose because of little or no shielding and a small dose because of adequate shielding is the difference between death and life. No clothing, of course, could possibly provide enough shielding. However, if you were to be in the open during fallout conditions, clothing would keep the particles from touching your skin. There is no such thing as a fallout suit, but ordinary clothing would help until you could reach the safety of a shelter. Then the fallout particles can be brushed off and outer clothing removed. If fallout settles on your food, the food itself is not harmed, since radiation damages only living tissue. And you can easily decontaminate it using almost the same methods you use in everyday food preparation. Actually, even if you accidentally swallowed some fallout particles, it wouldn't kill you. The effects, if any, probably wouldn't show up for years. Still, since there is a possibility of long-term effects, such as shortened lifespan, cancer, or hereditary damage, it's wise to remove the radioactive particles by simply washing, wiping, or peeling. But it's vital to remember this. Neither water nor chemicals can destroy radioactivity. The fallout particles can only be moved or washed away. Only time can reduce their limits. And what of water? Well, here again, the same rules apply. If necessary, you could drink water containing fallout particles without worry or immediate harm. The chances are you wouldn't have to for long. The water helps to wash itself through the natural processes of sedimentation and filtration. And swiftly moving rivers like this will carry most fallout particles downstream. In still waters, most particles will settle quickly to the bottom. Others might remain suspended in the water for a long time, while a small percent of the radioactivity would dissolve. The normal processing of a water treatment plant would make it safe to drink. And water coming from a covered well would be safe from radioactive contamination. There is no problem with breathing, for air is not contaminated once the fallout is on the ground. Fallout is not a poison gas. If ventilation is needed in a shelter, a simple inverted U-fitting on a ventilation pipe will keep fallout particles from entering the pipe and getting inside. Of course, surviving a nuclear attack means more than just waiting in a shelter for radioactivity to decay to save lessons. Survival, reconstruction, and recovery would involve decontamination in many areas. A very difficult job.
Unit 8 at Elmer Ward. Dose rate 15 Roentgens per hour.
Fallout would have to be removed from important areas by street sweepers. And the remaining particles could be flushed out of the way.
radioactivity from soil to plants is extremely low. And so, if nuclear attack should ever come, in spite of every effort to avoid it, we must be able to survive and rebuild for the future. But survival can only come through knowledge. The basic facts we must all know are relatively simple. First, there is nothing new about radiation. It has always been with us. What is new is the vast amount we would be exposed to as a result of nuclear explosion. Much of this danger would come to us in the form of fallout. But we are not without personal weapons or defense. One of these is time. Radiation decays, and so we will not have to take maximum precautions indefinitely. Another defense is distance. Radiating particles 50 feet away, for instance, will not affect us as much as particles a few feet away. And our third defense is mass. Any material with enough weight will keep the penetrating rays from hurting us. The greater the weight of the material between us and the particles, the safer we will be. The best way we can use all three weapons of defense is with an adequate shelter, thick enough to shield off a good part of the radiation until it has decayed to safer levels. That's why food remains good no matter how much radiation has passed through it. Fallout accidentally swallowed with water or food will do you no immediate harm, but for long-term safety, it's best to wash, wipe, or peel the food and filter the water. Even if you were caught outside under fallout conditions, ordinary clothing would keep the radioactive particles from touching your skin, but you would still need to find shelter quickly. If we remember these facts, and we act on them intelligently, we can increase our chances of surviving nuclear attack. And the key to survival is adequate shelter. That is why the federal government has a nationwide fallout shelter program. The goal is adequate fallout shelter space for every man, woman, and child. And this goal can be reached. For with knowledge of radiation, we can face the facts about fallout, take action to protect ourselves, and learn
It takes the form of a short wave and blast. The explosion of one atomic bomb releases as much energy as thousands of tons of TNT. This release of energy becomes manifest in three forms: heat, radiation, and blast, with latter being by far the most important. The effect of the atomic bomb on the selected target depends on three factors. First, the nature of the target. Second, the power of the bomb. And third, the height at which the bomb is detonated. For the purpose of this film, we shall assume that the target will be a large British city, and that the power of the bomb will be equivalent to the explosive force of 20,000 tons of TNT. This size is known as a homicide bomb. The assumed height of detonation will be 1,000 feet above the sea. This is about the height at which maximum destruction would be caused to a British city. To explode the bomb below this height would reduce the area of destruction, while to explode it at a greater height would reduce its power to destroy large steel frame buildings. If the bomb were to be more powerful than the nominal, then the height of detonation would be greater. Now we'll examine the three kinds of effect. First, there is that of heat. The heat originates at the moment of detonation and continues to constant. The gaseous products of the explosion glow and form what is called a ball of fire. It expands rapidly, and as it cools, it shoots up into the atmosphere at an initial speed of 200 miles per hour. The gases then form into a familiar mushroom-shaped cloud at a height of some 40,000 feet. Although the heat flash is of very short duration, it can cause considerable damage. The heat on it will scorch and may set on fire any exposed inflammable material up to a distance of 2 miles on a clear day. Atmospheric conditions play an important part in the effect of heat. On a misty or foggy day, the range of the heat flash will be greatly reduced. Effect number 2 is that of nuclear radiation. The effect of radiation becomes manifest in two forms. First, immediate radiation, and second, residual radiation. There is immediate radiation of gamma rays and neutrons at the target. They are centered in the lightning ball of fire, which carries them out of range within less than 1 minute after the explosion. The gamma rays travel at the speed of light in all directions of the explosion. They have a lethal range of about 3/4 of a mile to any person directly exposed to them or insufficiently shielded from them. Beyond this point, the power of the rays fall off rapidly. They do not make the objects they strike radioactive. The neutrons are atomic particles produced in the explosion, which have the power to make some materials which they strike radioactive. Their effect is largely outweighed by that of the gamma ray. The second form of radiation is that known as residual radiation. This consists chiefly of gamma rays which arise from deposited radioactive material, and to a lesser extent from material made radioactive by neutrons. Since only a small fraction of radioactive material ever reaches the ground, the danger from residual radiation is much less than from immediate radiation. These gamma and other rays are less concentrated, and they only become dangerous to human life if a person is exposed to them for a long time. In the case of a bomb detonated at 1,000 feet, there would be relatively little danger from residual radiation. Last, but by no means least, we come to the third effect, that of blast. This effect is caused by a shock wave resulting from the sudden and terrific heat produced by the release of atomic energy. With the normal types of explosives used in the last war, detonation of the bomb usually occurs on or after impact with the ground. Thus, the size of the
several severely damaged buildings up to a distance of 1.5 miles from the explosion. So there we have the three kinds of energy atomic bombs: heat, radiation, and blast. And the relative effect of each if a nominal bomb is detonated at 1,000 feet above the ground. If the atomic bomb is detonated on impact or below ground level, like this, the effect is somewhat different. A very deep crater would be formed, and it would be surrounded by a great ring of crater debris. The blast effect would be considerably less, although there would be a large area around the crater where buildings would be collapsed by earthquake effect. The danger from heat flash and immediate radiation would be less, since the insulating properties of the earth on the sides of the crater would absorb the greater part of it. But the danger from residual radiation would be greatly increased in the vicinity of the crater. The same applies to an underwater explosion. Considering once more our nominal bomb detonated at 1,000 feet, let's get some idea of the area that would be affected. The area may be divided into three circles, the first of which will be a quarter of a mile radius from the point of the explosion. This point is known as ground zero. Within this quarter-mile circle, the target will be completely devastated. The second circle, drawn at a radius of 3/4 of a mile from ground zero, will contain a large number of buildings totally or partially destroyed. The third circle, at a distance of 1.5 miles from ground zero, marks the limit of houses suffering severe structural damage. Outside this area, the damage will be progressively less severe, tailing off at about 2 miles. If such a bomb were detonated over London, the relative area affected would be approximately this size. Over Birmingham, the relative area would be this size. Over Glasgow, this size. And over Liverpool, this size. Now we will take an imaginary city, call it Sheffield, a typical British city of 500,000 people, and see more clearly what the effect of the atomic bomb might be. The air raid warning has sounded and people are in the shelter. Stretching out to 1.5 miles from ground zero, a large number of buildings are destroyed and many are burned. Let's take a closer look and see what it looked like before and then after the bomb. There is no need to study the whole area, as it may be presumed that the effects are similar at comparable distances from ground zero in any direction. So we'll take a slice or sector of the surface, like this. Here is a portion of Sheffield, about 1/4 mile from ground zero before the explosion. First there was the flash, and then the blast. This entire area is now devastated. That is to say that it is more than 80% totally destroyed. As a result, the fires here will be of little consequence, but the spread of rubble may make the locating of air raid shelters and the ultimate rescue of their occupants extremely difficult. Now let us examine the second circle, a distance of 3/4 of a mile from ground zero. Here it is before the explosion. Again, the flash and the blast. Notice that the damage is severe. Many streets are blocked with rubble.
And this fact, combined with the large number of fires caused by the heat flash, will produce many problems for those responsible for rescue work. And so we come to the third, or 1.5 mile circle. Here it is, before, and now after. Windows are broken, roofing damaged, doors blown off and hit. Structural damage is unlikely to be. In this area, a number of small fires would be started by the heat flash entering through windows of the upper and therefore more exposed floors, igniting curtains and other combustible materials. Beyond this distance from ground zero, damage will be confined to broken windows, fallen tiles and chimney pots, and similar minor damage. Only in exceptional circumstances would there be major structural damage. That then would be the effect of a nominal atomic bomb detonated at 1,000 feet over a British city. You may have noticed that no mention has yet been made of casualties. In Hiroshima, the aircraft carrying the atomic bomb was mistakenly thought to be a reconnaissance plane, and the population did not take cover. That mistake cost many thousands of lives. In a British city with wartime evacuation, with an efficient air raid warning system, and with the cooperation of an intelligent public using crucial shelter, such a terrible death row could be very greatly reduced. The number of casualties, however, will depend on the state of preparedness of the population to meet such eventualities. In particular, it will depend on the number of trained civil defense workers, who, together with the police and firefighting services, would be available and ready for action if and when the time should come. For the purpose of this film, the atomic bomb used will be assumed to be of nominal size and to be detonated at a height of 1,000 feet. We know that the first of the three effects of an airburst atomic bomb is that of heat. Heat from the searing flash at the start of the explosion. Although this heat flash, as it's called, may start a number of primary fires, it is not dangerous to human life, provided that a person has some form of protection or cover from it. Only those exposed in a direct, unshielded line to the bomb will be affected. The heat flash produces its own phenomenon, that of flash burn shadow. All the ground surrounding an object is affected by the intense, momentary heat of the flash, with the exception of that part directly in the shadow of an object, like this burn leaf. This effect occurs so rapidly that the outline of the leaf is fairly left before the leaf itself is destroyed by the heat. In this case, the shadow of a man was left before he was struck down. Here, the flash came through the window and left the imprint of a man's pipe. This phenomenon can be used in determining the direction of ground zero. A simple device like this board, fixed in suitable positions near civil defense posts, will give the controller both the height and the direction of the burn, measured by the length and the angle of the center pole shadow. This shadow will be indelibly marked on the board while it's still fixed in place, and its reading will be true no matter where the blast effect may shift the board to. Should the population have failed to take cover prior to the atomic bomb explosion, severe skin burns would be very heavy up to a distance of 50 miles from ground zero and here west. It's important to realize that the weather conditions at the time of the explosion have a marked effect on the range of the flash. In heavy mist, rain, or fog, the effective range of the flash is more than half. Types of clothing worn by unsheltered people will also affect the number of injuries from burns. Thick woolen garments offer the best protection, and at the extreme range of the flash, lighter colored cloth is more heat-resisting than dark colored. The covering of all normally exposed parts
material will invariably lessen the severity of the burn. However, if we assume, as we have done, that the population has taken cover, there is no danger directly from the heat flame. The indirect danger, that of fires started by the flash, may produce a number of problems, and must be considered as a common factor with all atomic explosions. Any easily inflammable material exposed within a 2-mile radius of ground zero in clear weather is liable to be ignited by the heat. In this country, there is little use made of wood or other combustible material on the exterior of buildings. Therefore, the main danger from fire would be internal, the flash having entered through windows or other avenues. Only those windows directly exposed to the flash would be so affected. Therefore, it is likely that a large number of primary fires started will be situated on the upper floors of buildings. These fires may be quite small, started by ignited curtaining or furnishing, and easily dealt with by hand-operated equipment. It's very important that the small fires occurring in otherwise undamaged areas be dealt with quickly. Otherwise, the spread of such fires would seriously impede the firefighting and rescue squads endeavoring to reach the more heavily damaged areas. The risk of fire from heat flash can be very greatly reduced by the simple expedient of whitewashing the window panes. It must be remembered that although glass in itself offers little protection against heat flash, any more than stopping heat from the sun, the glass will not be shattered until after the flash has done its part. This is because the shock wave of glass travels much slower. Any white or lime wash on the glass will reflect heat and reduce its penetrating fire considerably. All skylights should be similarly treated. At night time, a wooden blackout screen fitted to the window will also serve a useful purpose as a deterrent to heat flash. The wood may be charred on the outside, but it should prevent fires being started in the room. All such screens should, of course, be whitewashed on the outside. If the curtaining material is very heavy, it will also serve to stop the heat flash from entering, though there's a risk of the curtains themselves igniting. There are, however, several ways of making materials fire resistant. This can be done at home, and householders will be advised on how this is best done. The more serious fire situations may be expected at the 3/4-mile range from ground zero. These will include a number of secondary fires started by collapsing buildings. It will be important to warn the public that all domestic cooking and heating appliances must be turned off at the main before taking cover. It will be even more necessary than in the last war to obtain cooperation from the public in sharing their attics and lofts, and in providing their own firefighting equipment to deal with small outbreaks. Remember, with the explosion of an atomic bomb, fire will be a very great danger to human life and property. For the purpose of this film, we will assume that the atomic bomb used is a nominal bomb, and that it is detonated at a height of 1,000 feet. We know that one of the three effects of an atomic bomb burst is that of nuclear radiation, and that this effect is itself divided into two stages: immediate radiation and residual radiation. It must be emphasized that nuclear radiation will not be a source of danger to a civil defense worker, provided that he is protected from the immediate radiation and does not exceed the specified safe dose of residual radiation. The rays emitted by the bomb at the moment of the bomb's detonation come to the first immediate check. The most important of these are gamma rays and neutrons. The lethal range of the neutrons is smaller than that of the gamma rays, so the latter must be our main consideration. The effects due to the activity induced by neutrons in various materials will be examined with the other effects due to deposited fission products when we deal with residual radiation. forms of radiation can be measured in terms of wavelength. Gamma rays have a very short wavelength. Related to other and more easily identified forms of radiation, gamma rays have a wavelength even shorter than X-rays, which, as you know, has the power to penetrate a human body and affect the photographic plate exposed on the far side. At a longer wavelength are the ultraviolet rays produced by the sun. Longer again is that of visible light. Then infrared rays, and considerably longer, the radar and radio wavelengths, and so on. It will be seen then that the gamma ray wavelengths are among the shortest wavelengths known to man. Short wavelengths also mean high energy, and therefore a high power of penetration. Gamma rays cause damage to human tissue, and can be lethal if the dose is large enough, as indeed can X-rays unless properly controlled by a doctor to specified safe dosage. Gamma rays are, in fact, used medically for destroying tumors and other internal growth, but of course they are then controlled to a very fine degree to ensure safety. When an atomic bomb is detonated, gamma rays are emitted in all directions at a very high speed, and may travel up to 1.5 miles from the burst. Except in the case of very massive doses, there is no immediate physical reaction to these rays entering the body. It may be some days before radiation sickness is experienced. With a lethal dose of gamma rays, death will usually occur at any time up to 6 or 8 weeks later. The gamma ray dose received by a human being when an atomic bomb is detonated is governed by two factors. First, the distance from the explosion, and secondly, the amount of protection available. As the rays stream out from the source, they are spread over an ever-widening sphere, so that their density falls off very rapidly. At a range of 3/4 of a mile, the density is so far reduced that the dose received should not be lethal, although it may cause serious illness. At distances greater than 3/4 of a mile from the explosion, the energy and penetrating power of the rays fall off rapidly, and by the time they reach the 1.5-mile circle, they are virtually harmless. The second factor, that of protection, is of great importance. For protection from gamma rays, the denser the material, the less the thickness required. At 1/4 mile from ground zero, protection from a lethal dose may be obtained from 7 inches of steel. The same degree of protection can be obtained with 2 feet of concrete, or 3 feet of well-packed earth. Air raid shelters of the last war type will afford definite protection depending on their distance from the explosion, and with an additional covering of earth or concrete can be efficient to a substantial degree. Now we will examine the kind of radiation known as residual. As its name implies, it concerns the radioactive particles left on the ground after the explosion. Into an area some 1/4 mile radius from ground zero may fall a quantity of radioactive particles called fission products. These are the products resulting from an atomic explosion. They are radioactive and emit gamma rays. The rising cloud following the explosion is also filled with these particles. They may be carried by the wind and will be widely dispersed. Some may fall to earth anywhere downwind. This is called fallout. The radioactivity of the fallout is likely to be relatively weak, and therefore not a serious problem. The neutrons which were emitted from the bomb at the same time as the gamma rays also have the power to cause residual radiation. With this type of airburst bomb, a number of these neutrons will reach the ground in the vicinity of the explosion. In doing this, they may make other objects on the ground radioactive. That is, they cause those objects to radiate gamma and other rays. Except with air bursts of about 500 feet or below, the potentially dangerous gamma rays of residual radiation, whether caused by fission products at ground zero, or by neutrons, or in the fallout, are not likely to
you see here, there is believed to be some radiation due to a street fallout, and a reconnaissance party is sent to investigate. Radioactive rays are measured in dose rates of units received per hour. These units are called Roentgen. It is known that a single dose of 500 Roentgen has a 50-50 chance of being lethal to human beings, and that a dose of 25 Roentgen has no observable effect. Although it's unlikely that civil defense personnel will absorb even this amount in the normal course of their duties, nevertheless, in special circumstances, they may be called upon to receive considerably greater doses, since it's known that a dosage of 50 Roentgen can be absorbed without undue risk. In these cases, civil defense workers may, where circumstances permit, be withdrawn temporarily from radioactive areas. Although it might at first sight appear advisable for civil defense personnel to wear respirators so as to avoid inhaling radioactive particles, the real danger is from the residual gamma radiation. And provided this is restricted to 25 Roentgen, it has been found that there is no danger from inhaled particles. It is possible for the radioactive dust of fishing products to contaminate exposed food and water and thereby lead to radioactive poisoning. However, food and water stored in undamaged airtight containers would be immune from the risk of contamination. It is important to realize that radioactivity in any of its forms cannot be destroyed. This makes decontamination a difficult problem. It does, however, decay rapidly with the passing of time. In the case of fishing product contamination, at the end of the first 24 hours, the gamma ray activity is only 1/50 of what it was after the first hour. Provided the civil defense worker is adequately protected from gamma rays at the time of the explosion, and that an accurate record is kept of the dosage that was used, radiation is the least dangerous of the atomic bomb proved to be.
You will no doubt have seen, even if you have not studied, Civil Defense Handbook number 10, entitled Advising the Householder on Protection Against Nuclear Attack. In order to illustrate the contents of this handbook more graphically, the Civil Defense authorities have produced 7 short films based on the 7 sections that form the contents of the handbook. If the government decides that the time has come for this advice to be acted upon, these films will be shown to the public on all television networks. Their present purpose, however, is for your information. So we shall now show the 7 films as one film. Here we go. The government has decided that in the present state of international tension, you should be told how best to protect yourselves from the dangerous effects of nuclear attack. If this tension should lead to war, it is essential that you should have taken every possible precaution to safeguard your family, yourself, and your home. This film will show what are the dangers you expect and the best means of protection. First, the basic facts. When a nuclear weapon explodes, it produces 3 main hazards. The first of these comes from the heat generated by the fireball. This may last as long as 20 seconds. The heat is so great that for some miles around the explosion, it could kill people who are caught in the open, and it could burn exposed skin over a much wider area. The heat also threatens your home. By striking through unprotected windows, it would start fires across the whole area. The second danger is from blast. For some miles, buildings will be destroyed or severely damaged. Further out, buildings will suffer less severe damage as the blast effect diminishes. And for many miles beyond that, there will be light damage, such as broken windows. The third danger is from fallout. If the bomb explodes on or near the ground, dust is sucked up by the explosion and is made radioactive in the rising fireball. It rises high in the air and is then carried downwind, falling slowly to earth over an area which may be hundreds of miles long and tens of miles wide. Within this area, everything in the open would become covered with a film of radioactive dust. This fallout dust gives off radiation, rather like X-rays. Radiation cannot be seen, felt, heard, or smelled, but exposure to radiation can cause sickness and death. The radiation is at its greatest intensity during the first 2 days, but the danger decreases rapidly as time passes. After 2 days, it is 100 times less harmful than at first, but even then it is still dangerous. These then are the dangers that may face all of us: heat, blast, and fallout. In the other sections of this film, you will be shown what precautions will help to protect you from these dangers. To obtain protection against fallout, and as far as possible against heat and dust, it is now select and fortify a room in which to shelter, both during an attack and during the period of intense radiation that may follow. The penetration of harmful radiation is cut down by heavy and dense materials such as brick, concrete, and earth. The more, therefore, of these materials you can put between yourself and the fallout, the greater the protection you will obtain. The fallout will not get inside a house that has its windows and doors shut and has not been damaged by the blast, but it will settle on the roof and around the house. It is the radiation from this external fallout that endangers anyone inside. Now the choice of a fallout route. A basement or a cellar will give you the best protection and is the most suitable as a fallout route. Many houses will not have a basement or a cellar, but you can still find a room in your house which will give you protection from fallout. Remember that the more material there is between yourself and the fallout, and the further you are from the outside walls and the roof, the better the protection you will obtain. You can see why this ground floor room gives the best protection against fallout. It has only one outside wall, with the other walls either connecting inside the house or with the house next door. The room is also shielded by the houses across the street, which give it extra protection. The radiation from fallout can come from an appreciable distance, so this makes the front room more suitable than the back room, which overlooks a wide area and is far more exposed. If you live in a modern concrete block of flats of 5 or more floors, unless there is a basement, the best protection is given by the middle floor. If your home is in the upper or lower parts of the building, it will be best if you made arrangements to join the families living in the middle floor. In no circumstances should the top stories be used. In a block of flats with 4 stories or less, or one which has wooden floor joists, the best protection will be on the ground floor. A room should be selected in the same way as for a house, with not more than one outside wall and with the most protection from neighboring buildings. Prefabricated houses or bungalows give little protection from radiation. If you live in one, you should try and join friends or neighbors whose houses give better protection from fallout. If this should not be possible, there are other steps you can take which will be described later. Wherever you live, when you have chosen your fallout room, it should then be modified to improve the protection it can give you. The windows will be the weak point and will have to be blocked in with some heavy material. Using sacks or sandbags, which should be about 2/3 filled, you can block the windows from the outside Here, they are piled on strong cables until the whole window is locked. Alternatively, you can fill boxes or other containers with tightly packed earth. If you can't lock up the windows from the outside, pieces of heavy furniture should be positioned in front of the window and then packed with earth or board. A second method to use is to remove the window altogether. Fill the gap both on the inside and the outside with planks or balls. These rest on the windowsill and should be bolted or wired together. As you build them up, you should fill the space between the walls with tightly packed earth. Thirdly, after removing the window frame, you could fill the space with bricks, a double layer if possible. Both these methods are as effective as sandbagging and may be the most suitable for your house. You can make the fallout room more effective by blocking the outside door and any windows in the passage leading to your room, by treating adjoining rooms in the same way, and finally, by thickening the outside walls. By constructing a core, or heavily protected shelter, you can greatly improve your protection for the first few hours when radiation is at its greatest intensity. This is especially important for those of you living in a bungalow with no alternative shelter. There are several simple kinds of shelter core you can make. Here, 2 doors are leaned against the wall, leaving a space in which the householder and his family can sit, and then bags of earth are placed over the top. Here, the floorboards are taken up and the trench is dug under the floor. Ensure that it is in the corner furthest from the outside wall. You could also use a cupboard under the stairs, with sandbags outside the door and on the stairs.
For some of you, it will not be practical to build a shelter indoors, but a trench dug outside your home would give good protection. It should be deep enough to stand in, and the sides should be shored up. The trench should be covered with planks or other available material strong enough to support at least 2 feet of earth. Don't forget to leave an entrance with a movable cupboard.
In one or other of the ways you have just seen, you should now take steps to protect yourselves against the hazards of a nuclear attack. After an attack, it may be necessary for you, your family, and any others who have taken refuge with you to live in your fallout room for at least a week. It may not be safe for you to go outside to obtain any more food and water, so you will have to be prepared to live on the supplies you collected before the attack. You will now be shown what general provisions you should make. First of all, your furniture. Your shelter is going to be your living room, your bedroom, washroom, your kitchen, and your storeroom. It must have the basic furniture to fulfill all these requirements, but at the same time, floor space should be saved wherever possible. Use shelf space to its best advantage. Your room will need heating, bedding, a portable radio and spare batteries so that you can receive advice and further instructions, amusements and pastimes for you and the children, simple cooking equipment and fuel, and a large store cupboard for food supplies. You will need to have by you a reserve of tinned and other non-perishable food. This should be enough to feed the whole household and possibly some extra miles for at least a fortnight. Wrap up all your food, except for tinned stuffs, and keep it in closed cabinets or cupboards. Food is not harmed by fallout radiation, but anything that has had fallout dust on it will be contaminated and made dangerous to eat. If there are babies or young children, remember their special food, and don't forget the pets. It may not be possible to keep all your food in the fallout room, but you should keep as much food there as possible. Any remaining food should be kept in your larder or in a cupboard close to your fallout room. Once there has been a warning of fallout, it may be dangerous to leave your fallout room except for very short periods to collect more food and water. After a nuclear attack, the mains water supply may fail or become contaminated by fallout. Store as much water as you can. For drinking, you will need a minimum of 2 pints per person per day. 3 days' ration of drinking water should be kept in sealed flasks, bottles, or jars inside the fallout room itself. Do not waste the water. It may have to last you a fortnight. Fill the bath, the hot and the cold tanks, and every available container. Keep reserves away from the light and covered. Water stays fresher in the dark, and if fallout dust gets into the water, it will be contaminated. Find the whereabouts of your main stopcock, and be ready, if there is a warning of attack, to turn off the supply. After an attack, you may not be able to use your lavatory because of insufficient water for flushing. Therefore, you must make alternative arrangements for sanitation, either in your fallout room or just outside the door. You will also need to provide a dustbin, as there will be no way of disposing of your refuse. Finally, first aid. A simple but well-stocked first aid box. You must be able to help people who are injured or taken ill. It is essential that your fallout room is properly equipped for sleeping, eating, drinking, storage, cooking, refuse, sanitation, and emergency first aid. Remember, you may have to live in the room for at least a week. Your survival may well depend on the care and foresight with which you have supplied your room. When you have completed the preparation and equipping of your fallout, you should next take precautions to safeguard the rest of your house. You should be prepared to deal with the worst effects of heat and blast, in particular, the menace of fire. Fire is the most immediate danger after a nuclear attack. Though the heat will not set light to the bricks or plaster of your house, it will strike through unprotected windows and set any inflammable material on fire. Whitewash the windows, especially those at the top of the building. This will greatly reduce the fire risk by reflecting away much of the heat, and the heat should have passed by the time the slower-moving blast wave arrives. There are other things you can do to reduce the fire risk. You should remove all inflammable materials from upper floors, which are the most exposed to the heat wave. Clear away all newspapers, magazines, and wooden furniture, so as to leave as little as possible that could start fire. You should also remove any boxes and inflammable material near the outside of the house. If you have a garden syringe or a slip pump, this should be kept close to your fallout room. Fires can be put out quite easily if tackled at once, while they're still small, but they spread rapidly and can soon get out of control. Keep buckets of water on each floor of your house. Remember, fires can be extinguished just as well with dirty water as with your valuable drinking water. To minimize the danger from flying glass, you should draw your curtains and lower your blinds. After an attack, it may be necessary to move you and your family to a safer area. To provide for this emergency, you should have a suitcase ready packed. You should include a change of clothes, personal valuables, eating and drinking utensils, and a blanket. Take an overcoat or mackintosh in case of rain. You must remember you will only be able to take what you and your family can carry. Finally, a point for all car owners. Always keep your car topped up with petrol so that if you're instructed to move to a safer area, you will be ready to leave at any time. But until you are told, you will not know where it is safe to go.
These are all necessary precautions, as there will be no time for preparation once an attack starts. By taking these steps, you can increase the safety of your home and of your family. I'm going to explain to you the system of warning signals that was used in this country in the event of the nuclear attack, and on which you should be prepared to act. An exact knowledge of the signals and what to do when you hear them could save your life. There are 4 warnings: the red, the gray, the black, and the all clear. First, the red warning. This siren is sounding the red warning. It means that there is imminent danger of an attack. This is the gray warning. It means that fallout is expected in an hour's time. Where sirens have not yet been provided, the gray warning may also be given by church bells, or in Scotland, where church bells are not in common use, by word of mouth or by whistle. These are maroons. They indicate the black warning. It means there is imminent danger of fallout in your area. Where maroons have not yet been provided, this warning might be given by a gong or whistle sounding 1 long and 2 short notes, which is the Morse note D. Finally, this is the all clear. It means that there is no further threat of air attack or fallout and that you can leave your place of shelter. The all clear may also be given by civil defense workers or the police. Now, what to do when you hear the signal? First and most important, you should take cover immediately if you hear this red warning. If you are outdoors and cannot get home in 4 or 5 minutes, take cover in the nearest building. If you are caught in the open, take any available shelter. But if there is no obvious cover, you should lie in a ditch or a depression in the ground, covering the exposed skin of your face and hands to protect them from the heat flash.
Here is an emergency announcement. An air attack is approaching this country now. Go to shelter or take cover at once.
If you are driving a car, park immediately. But do not leave your car in any place where it might obstruct the many vehicles that will be engaged on urgent rescue work. Park it off the road if possible. Find the nearest cover, and if there are no buildings, lie flat in a ditch or depression. You should always give shelter to anyone who is caught in the open near your house when the warning sounds. They may have no other protection from the attack.
An air attack is approaching this country now.
If you are visiting, take cover wherever you are, unless you can get home in 4 or 5 minutes. If you are at home, you should turn off the gas and oil supplies and disconnect your electric heater. Damp down any fires with earth or sand and close all your windows. Then take cover in your fallout room or shelter. Now a grey warning, with fallout expected in an hour's time. If you had only taken temporary cover, you should go home, if you can get there quickly. If, however, you are still in the open, look for safer and more comfortable shelter as quickly as possible. If you are visiting and have taken shelter, go home if you can get there quickly. But if you can't, stay where you are. If you are at home,
Finish any last-minute preparations and then go to your fallout room. Finally, a black warning, which means fallout is imminent. If you are still outside, find the best available cover. If you are visiting, take shelter where you are. At home, go at once to the fallout room when the black warning is heard. Remain there. Keep the door of the room shut, as there will be plenty of ventilation from around the door. Everyone must realize there is the possibility of an attack taking place before any warning can be given. If this happens, the first indication would be the flash of heat and light, produced by the explosion and lasting up to 20 seconds. This would be followed by the blast wave. Whatever happens, you must not look in the direction of the flash. It could blind you. If you are caught in the open by the attack, fling yourself on the ground instantly, wherever you are. Do not move until the blast wave has passed. If you are at home or visiting, move instantly away from open windows or doors and take cover behind the nearest solid protection. When the heat flash passes, go to your fallout room if you can reach it in a matter of seconds before the blast arrives. If you can't, you should stay where you are until the blast wave has passed. It is unlikely that an attack will come without any warning, and the warning system is aimed to give notice of the threat of attack and of fallout so that you have time to take cover. Instant recognition of the warning signals is vitally important. So let's recap. The red warning. Imminent danger of attack. The gray warning. Fallout expected in an hour. The black warning. Danger of fallout imminent. The all clear. No further danger of attack or fallout. Warnings will only be cancelled by the all clear, or by word of mouth from the police or civil defense warden. Once a warning has been given, there is danger, and you must not expose yourself needlessly. From now on, you must listen for and take immediate notice of warning signals. For your own safety, you must follow exactly and promptly any instructions given by civil defense workers or the police. The warning system can save your life. You must not only know what to do in the event of a nuclear attack, you must also know what action to take immediately after. Your safety may depend on prompt action taken during the short time that may elapse before fallout arrives. As soon as the heat and blast waves have passed, one of you should leave your fallout room and find out the extent to which the house has been damaged. Fire will be the most immediate danger. You should go round the house and put out any fires that you think may have started before they have a chance of becoming established. Call your family to help you if necessary. Fires can be extinguished by using mains water if still available. You must turn off the stopcock as soon as possible so as to prevent the possibility of contaminated water entering the system. You must at the same time turn off any water heaters and shut down your boiler. To prevent valuable clean water from being used for flushing, you should tie up the ball cock in your WC system. From now on,
conserve your water supply. Having dealt with the inside of your house, you should now put on gumboots or stout shoes, a coat done up to the neck, a hat or headscarf, and some gloves, before going to see what needs to be done outside. This must be done, regardless of the unknown risk of fallout. Make sure your house is safe from any fires which may have started nearby, or fires which may spread from other houses. When you have dealt with your own home, be ready to give assistance to your neighbors if they need help. But whatever you are doing, listen for the warning signals of approaching fallout. If you have been in the open after an attack, when you get indoors, take off your outer clothing and leave it outside the fallout room. Have a wash if possible. By these precautions, you will get rid of any fallout that may have settled on you. Once this has been done, go to your fallout room and stay there. It is vital that you should know what to do immediately after an attack. On your actions may depend the safety of your home, your family, your neighbor, and yourself. Any delay on your part may endanger the lives of everyone living around you. Once the black warning has sounded, it means your home is in a fallout area, and you must remain in your fallout room. Remember, you may have to remain under cover for at least a week. Then our general guide for the days will have to spend in your fallout room.
Stay in your refuge room.
During this period, listen for announcements and instructions on your radio. It will be all right for you to leave the fallout room to collect more food or water, or to go to the lavatory. But time spent outside your fallout room should be kept to the absolute minimum. Except for these reasons, you should never go outside the fallout room. Fallout dust cannot usually be seen. Only the wardens and the police, with their special instruments, will know the level of fallout radiation. The amount of fallout will vary from place to place. It will be heaviest in the middle of the fallout area and grow less and less towards the edge of the plume. Where fallout is particularly heavy, people may have to be moved to a safer area. If this does become necessary, you will be told by radio or by the warden or the police. Keep your suitcase to hand and be ready to move, but on no account leave home before you are told. If you have to be moved, put on some warm clothes and take with you enough food to last for 24 hours. This food should be packed in airtight containers. Private car owners will be asked and expected to fill every available seat. As few people as possible will be moved, and for most of you, it will be stay in your fallout room. Use your food and water carefully, and always remember the danger of radiation. For your own safety, you should wear plastic or rubber gloves. Keep all your food covered. If the cover is unbroken, then the food will be safe. Before you open the food, wipe the packing carefully. This will prevent any fallout dust that has settled on the package from getting into the food. When you have unwrapped the food, you should immediately dispose of the wrapping in the dustbin. Your water must also be kept covered. Do not use any mains water for cooking or drinking until you have been told that it is safe. In the meantime, use your water sparingly and reuse the water for different purposes. Always remember, boiling contaminated water will not make it safe for drinking. Everywhere, the dangers from fallout will decrease as time passes. When the danger from fallout is lessened sufficiently, The civil defense or the police will tell you when you can go outside. Do not go out until you are told it is safe. And even then, you may only be able to go out for a very short time. Essential work will be restarted as soon as possible. Emergency arrangements may be made for the distribution of water. You will be told when it is safe to stay out for longer periods, but there will still be danger from fallout, and nobody should remain outside for longer than necessary. You must still be careful not to bring fallout into the house from outside. Wear some stout boots or shoes to go out, and change before returning indoors. Wash the boots thoroughly when you get back. Wipe down all the working surfaces in your kitchen, your larder, and also anything that may come into contact with food. You should wear plastic or rubber gloves, and when you have finished, you should wash the gloves. Burn all your rubbish. Although the fire will not get rid of radioactivity, it will reduce the bulk of your rubbish and help to prevent the spread of ordinary disease. If the present world situation does lead to a nuclear attack on this country, it is vital that you shall have taken the necessary measures to safeguard your home as much as possible. It is vital that you should know what action to take in the event of a nuclear attack. If you fail in this, your negligence could endanger the lives of your friends and neighbors as well as your own family. Remember that the civil defense wardens and the police are here to aid and advise you. But wherever you live, you must know how to help yourself and be prepared to help others if their lives are in danger.
Nuclear explosions are caused by weapons such as H-bombs or atom bombs. They are like ordinary explosions, only many times more powerful. They cause great heat and blast. They also make a cloud of deadly dust which falls slowly to the ground. This is what is called fallout. So these are the two dangers. First, heat and blast, which is followed by fallout. The heat and blast is so severe that it can kill and can destroy buildings for up to 5 miles from the explosion. Fallout is dust that is sucked up from the ground by the explosion. It can be deadly dangerous. It rises high in the air and can be carried by winds for hundreds of miles before falling to the ground. You can protect yourself and your family, and later on we will show you what steps to take. These are the warning sounds you must recognize. First, the attack warning. If an attack is expected, the sirens will sound a rising and falling note like this. Next, the fallout warning. When fallout is expected, you will hear 3 bangs in short succession. They will be sounded by means of maroons like this. Or you may hear 3 gongs, like this. Or 3 whistles, like this. These all mean that fallout is expected. Warnings of the attack and of fallout will also be broadcast. When the immediate danger of air attack or fallout is passed, the siren will sound a steady note like this. Here are the warning sounds again. Attack. Fallout. Here is a reminder of what the air attack warning sounds like. This is the sound. When you hear the attack warning, you and your family must take cover at once. Do not stay out of doors. If you are caught in the open, lie down. And now here is a reminder about fallout warnings. When fallout is expected, you will hear 3 bangs in short succession, like this. In some areas, the warning may be given by means of 3 gongs, like this. Or you may hear 3 whistles, like this. All these 3 types of sounds indicate that fallout is expected. When you hear them, you must stay in the safest position in the house. Keep the doors shut. Do not go outside the house until you are told it is safe. Here is the all clear warning. When you hear this sound, you can leave your cover. But keep listening for further warnings. must now choose a room in your home which will give the best protection from fallout. If you live in a house, the safest place is the ground floor or basement. Choose a room with the smallest amount of outside wall. The farther you are from outside walls and the roof, the better the protection. If you live in a block of flats, which is more than 5 floors high, it is important not to use the top 2 floors. The safest places are inside passages away from outside walls and windows. If the block is 4 floors or less, the best place for a fallout room is the basement or ground floor. If you live too high up to be safe, you must make arrangements now with your neighbors in the lower floors, or make some suitable arrangements to shelter with someone close by. If you live in a 1-story house, like a bungalow or prefab, the building itself will not give you much protection. So the best thing is to make arrangements now to shelter with someone close by. If this is not possible, look for a space in your home which is farthest from the roof and the outside walls. Later, we shall be telling you how to strengthen and improve your fallout room. We have told you how to choose a fallout room in your home. The best place is farthest away from the roof and outside walls. Your fallout room will protect you, but you will make it even safer by strengthening a small part of it. This part will be your inner refuge during the worst of the attack. Making a refuge is not difficult. The main things you will need are shovels, boxes, cartons or large plastic bags, earth or sand. Start collecting them now. These things may also come in handy. Hammer, saw, screwdriver, nails, screws, string or thin rope, scissors or penknife. One idea is to make a lean-to of wood, resting against an inside wall. Strong boards or doors taken from their hinges of white wood. Stop them slipping down the wall by fixing them to the floor with a strip of wood. Then cover the wood with bags or boxes filled with some heavy material, like sand, earth, books, or rolled up clothes. Don't forget to fix the bags and boxes so that they don't slip off. Across the 2 open ends of your refuge, you should make thick walls of bags and boxes of earth or sand, or heavy furniture, packed tightly with heavy material. Don't forget to leave an easy way into and out of your refuge. Next, a cupboard under the stairs. That is another good place for a refuge. Put boxes of earth or sand on the stairs and along the walls of the cupboard like this. If the stairs are on an outside wall, make the wall thicker with bags of earth or sand. Stack the bags up to a height of about 6 feet. Here is another idea. Use tables if they are strong and large enough for you and your family to shelter in. Make solid sides around the tables out of heavy furniture, boxes filled with sand, earth, or books. If you can, lay strong boards or doors across the top and cover them with bags of heavy material. This will make a good roof over your refuge. If you live in a caravan or other building of lightweight construction which provides you with very little protection against fallout, your local authority will be able to advise you on what to do. Whatever type of refuge you have, the main thing to remember is that the more heavy material you have around you, like earth or sand, the more chance there is of safety. Start looking now for materials for your fallout room and inner refuge. Here is a list of things and some ideas for you. Bricks, concrete blocks, bags or boxes filled with earth or sand. If you cannot get hold of sandbags or boxes, try travel bags, haversacks, suitcases, pillowcases, or anything which will hold sand or earth. Strong pieces of wood, heavy furniture, doors taken off their hinges. All these things can give you good protection. Think about it and make plans now. Decide what you already have in your home that will be suitable for making a refuge. Decide what you may need to bring into the house: earth, bricks, sand, etc., to strengthen it. Decide where you will store all these materials, so that you will know exactly where they are when you need them. You can use these materials like this for thickening the floor above your fallout room, for building your inner refuge, for blocking windows, doors, halls, or passages, for thickening outside walls. All these materials can save your life. If you have taken the advice we've been giving you recently, you will by now have chosen your fallout room and gathered your materials for an inner refuge. The time has now come to make everything ready for you and your family in case an air attack happens. This does not mean that war is bound to come, but there is a risk of this, and we must all be prepared. So don't waste time. Start now. To help you, we will remind you once again about choosing a fallout room and an inner refuge. First, choosing a fallout room. That should be a room in your house which will give you the best possible protection from fallout. A room that is farthest from the outside walls and the roof, or one with the smallest amount of outside wall is safest. Whatever room you choose, remember that the further you can get away from radioactive dust in or around your home, the safer you will be. So in a house, the safest place is the ground floor or basement. In a block of flats, do not shelter in the top 2 floors if the block is 5 floors high or more. Go to the lower floors, ground floor or basement. The central corridors will give good protection. If you live in a bungalow or similar one-story home, it will not give you much protection. If you cannot make alternative arrangements, choose the safest place, which is the space farthest from the roof and outside walls. And now a reminder about your inner refuge. We have told you that your fallout room should be the safest place in your home. Even this is sometimes not safe enough, however, particularly for the first 2 days and nights after an attack, when the danger from radiation could be critical. So you need, inside your fallout room, an inner refuge. a fortified area to give you greater protection during the worst of the attack. The inner refuge should be thickly lined with dense materials to resist radiation, away from outside walls if possible. Now for its construction. Make a lean-to with wood, resting against an inside wall. Use boards or doors taken from their hinges. Stop them slipping down the wall by nailing a strip of wood to the floor like this. Cover them with dense material and fix some rope around it so that it won't slip. Partly close the open ends, leaving an easy way in and out of your refuge like this. Another good place for a refuge is a cupboard under the stairs. Reinforce the stairs and the side like this. If the stairs are on an outside wall, stack up containers of earth or sand to make the wall thicker to resist radiation. If you've got tables large enough to give you and your family sufficient shelter, use them. Make the sides solid with heavy furniture or boxes of books or sand. Reinforce the top with strong boards or doors and cover them with dense materials. More details are given in the booklet, Protect and Survive. If you haven't got one yet, get one from the post office now. And start right away making your home and your family as safe as possible from nuclear attack. Start now on your fallout room and inner refuge. Thicken the floor above your fallout room. Start blocking windows, doors, halls, passages. Thicken the outside wall if your fallout... Fallout dust gives off dangerous radiation. It cannot be seen or felt. It has no smell. Anybody staying within reach of fallout for too long can fall ill or die. So you must keep away from fallout until it is safe. And this may mean staying in your fallout room for up to 14 days. Prepare yourself for this now by storing all the things you need. Put them in your fallout room or stacked up within easy reach close by. Here is a list of the most important things you will need. Drinking water. Food, mostly in tins. Portable radio and spare batteries. Tin opener, bottle opener, some cutlery and crockery. Warm clothing. And now here is a list of some things which will make living in your fallout room much more comfortable. Bedding, sleeping bags, portable stove and fuel, saucepans for boiling water and cooking, torches with spare bulbs and batteries, candles, matches, table and chairs, toilet articles, soap, toilet rolls, change of clothing, first aid kit, household medicines and prescribed medicines, box of dry sand, cloths or tissues for wiping plates and utensils, notebook and pencil for messages, brushes, shovel and cleaning materials, rubber or plastic gloves, toys for children, books and magazines to pass the time, clock and calendar. Finally, don't forget your booklet, Protect and Survive. It tells you how to make your home and family as safe as possible. All the items we've just told you about are listed in it. A warning may come quite unexpectedly. We will now tell you what to do if a warning sounds when you are at home. And then we will explain what to do if you are out of doors. First, if you are at home. If attack is imminent, you will hear the attack sound like this. So take cover at once. Send your young children to the fallout room, then go quickly and turn off the gas and the electricity at the mains. Close down stoves. Damp down fires. Shut windows. And draw curtains. Then go to your fallout room and stay there. If the fallout warning sounds are heard, they will be like these. You should now move yourself and your family to the safest area in your fallout room. That is, you should get inside your inner refuge and stay there. After 2 days, the danger from fallout will get less, but don't take any risks by contact with it. The longer you stay in your refuge, the better it will be for you. Listen to your radio. Stay where you are and keep listening to your radio. Now, this is what you should do if you are out of doors when the warning sounds. Take cover at once when you hear the attack sound. If you cannot reach home in 10 minutes, take cover in the nearest building. If there is no building nearby, try to find some solid cover. If there is no solid cover, lie flat in a ditch or a hole and cover your head, face and hands as fast as you can with some of your clothes. If you hear the fallout warning, seek the nearest and best cover as quickly as you can. But before entering the building or cover, brush or shake off any fallout dust you may have picked up and get rid of it. Change your outer clothes if you can. Stay under cover. When the all clear sounds, like this, it means that you are safe from attack or fallout for the time being, and that you can go out again. But keep listening for further warnings, or to your radio for further advice. After an attack, You may have to stay in your home for about 14 days. So make sure to store plenty of water and food for your family. Water is more essential to life than food. You can live for a long time with a little food if you have enough water or liquids to drink. How much is enough? Well, each person should drink about 2 pints a day. So, for 14 days, 3.5 gallons is enough for one person. But you should double this amount if you can. Then there will be some to spare for washing your face and hands. Keep drinking water in your fallout room. Store it in plastic containers with a screw top, or in bottles or jars covered to keep out dirt. Store the rest in kettles and saucepans and in basins in the bathtub. Try to keep some tins of fruit juice as well. Now, food. Stock enough for everybody for 14 days. You may not be able to cook anything hot, so buy foods you can eat cold and that will not go bad. Buy food well wrapped or in tins. By the way, don't forget your tin opener and bottle opener. You will do best to buy lots of different kinds of foods if you can, so that you won't get bored with too much of the same thing. Stock up with meats, vegetables, fruit, tinned or powdered milk, and special foods for babies or invalids. You will also need some sweet things, like sugar or jam, and biscuits. Keep the food in a cool, dry place until you have to take it to your fallout room. Foods that will go bad quickly should be the first to be eaten. Try to ration everything so that it will last out. A nuclear explosion produces intense heat. This can get through unprotected windows and set fire to things in your home. But there are steps you can take now to cut down the risk. First, whiten your windows with white paint to reflect some of the heat away. This will cut down the risk of these fires. Then get rid of junk lying about in your attics and upper floors, especially old papers and magazines, which can catch fire easily. The heat from the bomb strikes at attics and upper floors most easily, and fires there are usually the hardest to put out, so pay particular attention to these places. In other parts of the building, clear away papers and magazines. Then net curtains from windows. And any old rubbish inside or outside your home which is likely to catch fire easily. Small fires can be put out easily if they are tackled at once. If they are left, they spread fast and soon get out of control. The fire brigade may not be able to reach you, and you will have to protect yourself without any help. So prepare now. If you have a fire extinguisher, keep it handy. Or a garden hose would be very useful. Keep buckets of sand and water ready on each floor. When you take cover in your inner refuge, you must not go outside until it is absolutely safe. And if the fallout is heavy, you may be in your refuge for quite a long time. Although the danger from fallout will get less and less as time goes by, you will never be able to judge for yourself how bad it is. Advice will be given to you on the radio, so keep listening. This advice over the radio and other instructions and news will be very important to you while you're cut off from the people living around you. So make sure your radio is in good working order. And if you have a spare radio, keep it in your fallout room. Radios must be battery operated because your electricity may be cut off. So be sure to get some spare batteries. After a fallout warning, you have been advised to take cover in your inner refuge. The first 2 days will be the most dangerous period because fallout will be at its worst. So it is in your best interest to stay in your inner refuge the whole of that time, however cramped or uncomfortable it may be. But if you must leave the refuge to go to the lavatory or to get more water or food, don't stay out a second longer than is necessary. In any case, don't go outside the fallout room at all. After 2 days, the danger from fallout will be less, but it may still kill you. So the longer you stay in your inner refuge, the better your chances are. Although it may be fairly safe for you to move about inside your fallout room, it certainly will not be safe for you to go outside the house until the radio tells you. So keep listening to your radio for advice. At first, you'll be told when you can go outside the house for a short time to get rid of lavatory waste and rubbish. Then, as the danger from fallout begins to pass away, you will be able to stay out for longer spells. There may still be a lot of fallout dust lying about, so be careful not to bring it back with you into the house. Keep a separate pair of boots or strong shoes for going up. Before coming in, take them off and wash or wipe them, soles as well. It is also a good idea to wear rubber gloves while you are outside. Try to keep the younger people indoors as much as possible. In fact, it will be far wiser for only people over 30 to work outside until things get better. And now a reminder of some of the things we have told you in earlier films. Fallout can kill, though you cannot see it, feel it, or smell it. There is danger outside, so don't go outside. Stay in your fallout room until you are told it is safe to come out. After an attack, fires will start in many places. The fire brigade may not be able to help everyone, so it might be up to us to tackle the fires in our own homes. Here is some advice on how to do it. Make sure that you have turned off gas and electricity at the mains. Don't smoke. Then start checking for fires. Start at the top of the house. Check roof space and every room, putting out fires before they get out of control. Small fires can be put out quite easily if they're tackled at once. If they are left, they spread quickly and take hold. Use water from the tap if there is any. Earth and sand are also useful. Put all the members of your family to work putting out fires in the house. When you are satisfied that the inside is safe, check the outside of the house and make sure that you are safe from any fires which have started nearby. When you have seen to your own household, help any neighbor in need. If you have used any of your precious drinking water to fight fires, make good your reserve. Fill up all your containers again and put covers on. Turn off your water supply at the mains. It may become contaminated. If your house is damaged, you may have a little time before a fallout warning to carry out minor jobs to keep the weather out. Curtains or sheets may be used to cover broken windows or holes. Then listen for the fallout warning. If it comes, take cover in your inner refuge and stay there. Earlier we told you what to do to prepare emergency lavatory arrangements in or near your fallout zone. It will not be easy for you to keep clean in shelter conditions, mainly because it is unlikely that there will be any water to spare for washing or for flushing the lavatory. But cleanliness is essential to prevent sickness, and here are a few simple rules to help you. All toilet containers should be covered when they're not in use. Pour in some disinfectant. It will cut down the smells and keep off flies. When you have used the bucket lavatory, wipe your hands with toilet paper soaked in a little mild disinfectant. Throw the paper into the container and put the lid on. Keep an eye on small children and see that they do the same as you to keep clean. Don't let the bucket get too full. If you have lined it with a plastic bag, tie the neck tight before lifting it up. And put it in a separate dustbin well away from the fallout zone. Put a fresh plastic bag into the bucket with a few drops of disinfectant. Cover the bucket with a lid. When it is safe to do so, take the dustbin and its contents outside the house. Remove the waste and bring the empty bin back. Food scraps, empty tins and other rubbish should be wrapped up tightly in newspapers and put in a separate dustbin. Keep the lid on. If you have got only one dustbin, use that for toilet waste only. Put all other rubbish separate in plastic bags or paper until you can take it outside the house. Keep your hands as clean as possible. Wear rubber gloves for dirty work. Try to avoid touching food with your hands as much as possible. Keep your knives and forks, plates and cups, etc. clean. Dry, clean sand is quite good for this. After an air attack, your water taps may run dry, or the water in them may be too dangerous to drink because it has been poisoned by chlorine. So your life may depend entirely on what you have stored. Keep it clean by covering the containers. Its main use is for drinking, but use it sparingly. For each person, you should have stored at least 2 pints for each day. Don't waste water on washing or anything else. If you must use water for cooking, use as little as possible. If you heat cans of food in a saucepan of water, don't throw the water away. It can be used over and over again. By the way, make sure you pierce the top of the can before heating. Dip your dirty knives and forks into the pan while the water is still hot. Water is life. Save it. You should by now have built up an emergency reserve of tinned food or other foods that don't go off quickly and that can be eaten cold. Keep your food reserves in your fallout room. And remember to keep them well covered to protect them from fallout dust. There might be fallout dust on the packaging. Take care this does not get into the food. So wipe the tins, packets, and bottles. You may not be able to replace your stocks of food for a long time, so make them last. Most of the time, you'll be resting in your fallout room, and you won't need to consume much food. Eat the smallest amount you can get by with, and plan meals carefully so that there is no waste. And remember, keep your food covered from fallout. Wrap open tins and loose food. Prepare small amounts at a time. You may not be able to replace your stocks for a long time, so ration food carefully. After an attack is over and the all clear has been sounded, arrangements will be made as soon as possible to treat any people who are ill or injured. Listen to your radio. Details will be given about what to do, when to do it, and how. If anyone dies while you are kept in your fallout room, move the body to another room in the house. Label the body with name and address, and cover it as tightly as possible in polythene, paper, sheets, or blankets. Tie a second card to the covering. The radio will advise you what to do about taking the body away for burial. If, however, you have had a body in the house for more than 5 days, and if it is safe to go outside, then you should bury the body for the time being in a trench or cover it with earth and mark the spot as a burial.
raging nuclear furnace. It shoots out showers of particles 2 times the matter as we conceive it, along with invisible forces that we call radiation. This radiation and these particles travel through space at fantastic speed until they strike some other matter which may make new flares of radioactivity. They strike wandering asteroids, moons, and planets such as our own. Everything in space, Earth included, receives. We don't worry about the small amounts of natural background radiation. But to safely handle larger amounts, we must keep our distance and shield ourselves. For as the amount increases, so do the dangers. The amount of energy generated by a nuclear explosion is enormous. Atoms produced in the explosion join with the particles of earth and debris. Millions of highly radioactive particles of matter that we call fallout. The strong winds of the upper altitudes go to work on the cloud, blowing it off in one or more directions. Gravity tugs on the particles. The larger and heavier ones stick toward the ground, while the lighter particles continue to drift with the wind. Some of the lightest particles remain suspended in the upper atmosphere. As time passes, their radioactivity grows weaker, so that the longer they remain aloft, the less dangerous they are. But the heavier particles, spread by high-altitude winds, fall to the ground within 24 hours. Several miles from the explosion, they are about the size of table salt and fine sand. These are the most dangerous, because they carry the greatest number of radioactive atoms, and so emit the largest amount of nuclear radiation. Which brings us to an all-important fact. Deadly as radiation can be, it has important weaknesses, a rapid rate of decay. And this gives us an invaluable ally, time. Suppose a nuclear explosion takes place at 12 noon. By 1 o'clock, the total force of the residual radiation is at a high level. By 7 o'clock, it's down to 1/10. In 2 days, although still dangerous, it's only 1/100th. But in 2 weeks, it's only 1/1000th. With this decay rate in mind, consider radioactive fallout conditions which might confront us after a massive attack. Within an hour, fallout would be a serious problem in the vicinity of explosions which occur on or near the ground. By 7 hours after the attack, the fallout area covers more and more of the country as the prevailing winds expand the fallout in a downwind pattern. 24 hours. 48 hours. Without shelter, millions would face death. A few days later, those who have taken shelter will survive. In many areas, people can even leave shelter for brief periods of time to carry out important tasks. Within 2 weeks, most people can leave their shelters for longer periods as the radioactivity decays to lower levels. The lesson is obvious. We must shield ourselves from radiation through the dangerous period. To do this, we need more than time. Fortunately, we have another ally. The greater our distance from the fallout particles, the less radiation we receive. You would receive less radiation in the middle of a tall building than you would receive on the top or bottom floors, because there would be more distance and precision between you and the source of the radiation. The fallout particles would cover the roof and the ground around the building. Only an insignificant amount would get inside. offers a small amount of mass and distance from radiation, but not enough protection in an area of heavy fallout. The solution is plain. Fallout shelters are the best defense against nuclear radiation, whether in a home for a single family or a large community type in an apartment building. They offer the kind of protection from radiation you would probably need in case of a nuclear attack. But the best shelter would be worthless unless it was used. Most people find it hard to understand how silent invisible rays, which cannot even be felt, could be so damaging. Let's see what happens when radiation penetrates the body and attacks the cell. What is a cell, and what happens when it is attacked? It's a simple organism, which reproduces itself by dividing. Our bodies are... The key then is the amount, the total dose of radiation received. We measure radiation the same way speed is measured by a speedometer. Only instead of a speedometer, we have a rate meter. And instead of miles per hour, we measure the rate in Roentgens per hour. We need another device, called a dosimeter, to record how much radiation a person has accumulated over a period of time. In the same way we record accumulated distance in miles, the dosimeter records accumulated dose in Roentgens. With this in mind, let's return to background radiation. In an average lifetime, a person might expect to accumulate about 10 Roentgens from his natural environment. Not enough to affect his health. This same healthy person would need medical care if he received more than 200 Roentgens within a few days. 300 Roentgens in the same period would cause severe radiation sickness or possibly death. And as we go beyond 300 Roentgens, the danger of death increases rapidly. So now we see why shelter is vital. The difference between accumulating a large dose because of little or no shielding and a small dose because of adequate shielding is the difference between death and life. No clothing, of course, could possibly provide enough shielding. However, if you were to be in the open during fallout conditions, clothing would keep the particles from touching your skin. There is no such thing as a fallout suit, but ordinary clothing would help until you could reach the safety of the shelter. Then the fallout particles can be brushed off and outer clothing removed. If fallout settles on your food, the food itself is not harmed, since radiation damages only living tissue. And you can easily decontaminate it using almost the same method you use in everyday food preparation. Actually, even if you accidentally swallowed some fallout particles, it wouldn't kill you. The effect, if any, probably wouldn't show up for years. Still, since there is a possibility of long-term effects, such as shortened lifespan, cancer, or hereditary damage, it's wise to remove the radioactive particles by simply washing, wiping, or peeling. But it's vital to remember this. Neither water nor chemicals can destroy radioactivity. The fallout particles can only be moved or washed away. Only time can reduce their potency. And what of water? Well, here again, the same rules apply. If necessary, you could drink water containing fallout particles without worry or immediate harm. The chances are you wouldn't have to for long. The water helps to wash itself through the natural processes of sedimentation and filtration.
like this will carry most fallout particles downstream. In still waters, most particles would settle quickly to the bottom. Others might remain suspended in the water for a long time, while a small percent of the radioactivity would dissolve. The normal processing of a water treatment plant would make it safe to drink. And water coming from a covered well would be safe from radioactive contamination. There is no problem with breathing, for air is not contaminated once the fallout is on the ground. Fallout is not a poison gas. If ventilation is needed in a shelter, a simple inverted U-fitting on a ventilating pipe would keep fallout particles from entering the pipe and getting inside. Of course, surviving a nuclear attack means more than just waiting in a shelter for radioactivity to decay to safe levels. Survival, reconstruction, and recovery would involve decontamination in many areas. A very difficult job.
Unit 8 at Elman Morgue. Dose rate 15 Richters per hour.
Fallout would have to be removed from important areas by street sweepers. And the remaining particles to be flushed out of the way. Food would be a problem. After a nuclear attack, we would first use existing food supplies in shelters, markets, and surface food stores. When fallout had decayed to safe levels, people could begin to work in the fields for limited periods of time. In a few areas, the land would not be suitable for food, but such crops as cotton could be grown. Crops produced in summer would be grown in areas that had received the least fallout. The reason we would be able to grow and keep food planted in this land is the transfer of radioactivity from soil to plant is extremely low. So if nuclear attack should ever come, in spite of every effort to avoid it, we must be able to survive and rebuild for the future. But survival can only come through knowledge. The basic facts we must all know are relatively simple. First, there is nothing new about radiation. It has always been written. What is new is the vast amount we would be exposed to as a result of nuclear explosion. Much of this change would come to us in the form of fallout. But we are not without personal weapons or defense. One of these is time. Radiation decays, so we will not have to take maximum precautions in rescue. Another defense is distance. Radiating particles 50 feet away, for instance, would not affect us as much as particles a few feet away. And our third defense is mass. Any material with enough weight will keep the penetrating rays from hurting us. The greater the weight of the material between us and the particles, the safer we will be. The best way we can use all three weapons of defense is with an adequate shelter, thick enough to shield off a good part of the radiation until it has decayed to safer levels. In radiation attacks, the cells of our body are damaged. Most
of them can repair themselves if the total dose over a period of time is not too high. Even though the rays penetrate our bodies, causing damage, they will not infect us and make us, or anything else, radioactive. That's why food remains good no matter how much radiation has passed through it. If fallout accidentally swallowed with water or food will do you no immediate harm. But for long-term safety, it's best to wash, wipe, or peel the food and filter the water. Even if you were caught outside under fallout conditions, ordinary clothing would keep the radioactive particles from touching your skin. But you would still need to find shelter quickly. If we remember these facts, if we act on them intelligently, we can increase our chances of surviving nuclear attack. And the key to survival is adequate shelter. That is why the federal government has a nationwide fallout shelter program. The goal is adequate fallout shelter space for every man, woman, and child. And this goal can be reached. For with knowledge of radiation, we can face the facts about fallout, take action to protect ourselves, and learn how to live in the nuclear age.
Mid-afternoon, USA. A community like thousands of others throughout the country, like your community. You are a housewife doing your shopping, or a little girl out walking the dog. You're a boy trying out your new baseball glove. You're a construction worker with a day off, catching up on some chores around the house. Or a senior citizen catching up on it. Suddenly, something happens. Something that halts the normal routine of your day. Your nation has become the target of a nuclear attack. To prevent you from being a casualty, you must stop what you are. Be prepared to take cover, most likely in a public shelter. What will you do there? How will you react? How will you adjust to the new and different way of life you will encounter, living in a public shelter? nuclear detonation has taken place several hundred miles from this site. Dangerous radioactive fallout is being carried downwind for the air. This is one of several public fallout shelters in the town with the same shelter manager inside. Ronald Barnes attended a shelter management course given by an instructor who had received federally sponsored training. Barnes knows the importance of prompt organization within the shelter for the welfare of the occupants. In this shelter, each person is given a registration form which will indicate important data about the occupant. The form provides a ready means to determine the skills and capabilities of the occupant, who which may be used in the various shelter functions. Not all shelters will be organized or operated in the same manner. Procedures will depend on the size of the shelter, its floor plan, facilities, supplies, and the availability of trained personnel. Where the number of occupants is large enough, a supervisor for each shelter function may be needed. Members of the community who have prepared themselves with training in civil defense adult education programs, or in such areas as disaster aid or medical help, can provide valuable guidance in the shelter situation. Housewife Lenore Casey has listed on her registration form that she had taken a Red Cross home nursing course. In the absence of professional medical personnel, Manager Barnes assigned her the job of nurse. A section has been set aside as a first aid. Mrs. Casey will check the medical supplies and arrange facilities for care of the sick and injured. To Hal Denton, construction worker and former military policeman, goes the appointment of security and control, a necessary function in any situation where many people are confined in a limited area for a length of time. Seeking solace in this time of trial, office worker Bert Gaines finds in himself a native ability to comfort others, to bring them spiritual guidance and hope. The alert shelter manager is always on the watch for the emergent leaders who can help to ease the burden of shelter living. Harry Wilson, cashier at the supermarket, is put in charge of vital food and water supply. Mrs. Wilkins will keep a careful check on these provisions, their handling, and distribution. This includes those provisions furnished by the federal government in shelters which meet certain basic requirements. In many shelters, these will be the only provisions there. Other assignments are made to complete the supervision of key shelter functions. The first meal in the shelter. To facilitate the procedure, the shelter population is grouped into units, each with its own leader selected from the occupants, who keep the record of the rations issued to the people in its unit. Water is stored on the basis of 3.5 gallons per person. Federal rations provide 10,000 calories per person. Additional food items may be added to shelter provisions by the community. These might include special foods for persons with dietary needs, utensils for cooking and washing, and additional water rations for cleaning. We're going to be in this shelter for an undetermined length of time. Now, this will be a different experience for all of us. It will require understanding, tolerance, and cooperation on the part of all. It will be necessary to establish certain rules and regulations patients is a major consideration. Anyone with a special medical condition is asked to notify the appointed nurse to collect medication and keep them in attendance. Sickness in the shelter can present a very serious problem, and preventive measures against illness are taken to spare recovery. People in a stress situation often find comfort in religion. The religious counselor sees that everyone who seeks the consolation of his faith is given the opportunity for counsel, meditation. One of the most important There may even be overt antisocial behavior which might jeopardize the safety of the other occupants. Necessary measures to maintain order and security will be taken by the shelter manager. Some shelters have a forced ventilation system, which may be inoperative during some portions of the shelter. In this situation, it's comfort of the occupant's safety, human tolerance to temperature rises in confined areas, as indicated, and dangerous levels. Depending on time, place, and population, shelters may be more crowded than the one you see. Normal requirements are an average of 10 square feet of floor space per day. Almost 2 weeks have passed. There has been some illness. Some of the occupants have developed sick, but their ordeal is nearly over. Some remain distressed. Others have accepted the situation. Occupants are thrown back on their individual resources to pass the time. One question is foremost in their mind. How long will they have to remain in shelter? The answer depends on several factors, primarily on the radiological situation in the area. The most important thing for the occupants to remember is, the longer the shelter waits, the less danger because fallout decays with time. The Emergency Operations Center authorities will decide when people should leave the shelter. It is a vital decision, and it is made only after the fullest possible information about the local situation has been obtained. The shelter manager will present reasons for stay, or reasons why it would be better to go, so that the shelter occupants are safe. Periodic reports have confirmed that the radioactivity has been decaying steadily. Now it appears it will be reasonably safe to get departure from the shelter for a short period. Plans are made for emergency. Persons will also be permitted to leave the shelter for rooms in the same area. Later work details will be sent out to help restore normal community function. Finally, there will be permanent replacement. Remember that life in the shelter will not be like living under normal conditions. Suppose, in our story, there had been no shelter, no plant, no organization, no trained personnel. Suppose no one was there who understood the nature of the trouble the shelter occupants faced. Suppose no one had known when, or if ever, there would be hope of returning to a life previously known. In the perilous world of this nuclear age, shelter is preferred. Community shelter planning will result in the best use of our shelter facilities. Should the siren sound, would your community be ready with the kind of shelter preparation you have just seen? Would you be better prepared, or would you not be prepared at all? Shelter living will be what you, the community, make it, what you have provided for. That our normal, everyday way of life may not be suspended, this is our wish and our hope. But housewife, children, working man,
face of changing nature, all living creatures must evolve, adapt, and struggle to survive. Man, too, must survive. Man also progresses, but along the way, times result in dangerous changes in our environment. Unchecked, these changes may threaten our very survival. Man must stop his mishandling of nature and work toward a future with clean air to breathe, clean water to drink, uncontaminated soil in which to grow the food he needs. Oxygen producers like these, vital to our environment, must be protected. This is our deep commitment to the future. But how do we meet it? The science of the peaceful uses of atomic energy is one of the ways man is responding in the fight to preserve and restore his environment. The Atomic Energy Commission, from its inception, has had a vigorous program in environmental research. The application of atomic energy to meet environmental objectives moves in two directions. First, supplementing the conventional power plants that pollute the atmosphere with clean atomic power stations. Secondly, use the atom as a research tool to study our environment, especially the burden placed on the environment by modern industry. This challenging work offers many exciting career possibilities for scientists and technicians. Power production is one example. Electric power requirements in this country have been doubling about every 10 years. Sometimes the heavy demand exceeds the supply, causing power blackouts and brownouts. The basic principle of power production is simple. A heat source generates steam, which turns a turbo generator. The heat source may be coal, gas, or oil, called the fossil fuels. But there is another heat source, the atom, the nuclear fissioning of uranium. The discharge of noxious chemicals into the atmosphere is one thing coal and oil-burning power plants have in common. Atomic power plants, on the other hand, don't release smoke containing such contaminants that pollute the atmosphere. Both conventional and atomic power plants discharge some excess heat into adjacent waterways. These thermal effects must be controlled and minimized. Methods are being developed, such as giant cooling towers and man-made lakes. Whatever the heat source, water is converted into steam, which turns the turbine, which drives the generator. When the steam leaves the turbine, it must be cooled and condensed back to water and returned to the boiler. The cooling water does not make contact with the radioactive core. Cool water is usually taken from rivers, lakes, or the ocean. At atomic power plants, the water is pumped through the condensers and returned to its source as warmer water. Although so far, no significant detrimental effects of warm water on fish and other aquatic life have been found in the vicinity of nuclear power plants, thorough investigation will continue in order to assure that environmental impact will not be excessive when weighed against man's growing need for electricity. But of course, slightly warmer water may be used beneficially for agriculture and even recreational purposes. Future, more efficient nuclear generating stations, such as the breeder, will release less heat per kilowatt. However, nuclear power plants do release very minute quantities of radioactivity into the cooling water and into the atmosphere. But federal standards carefully and conservatively regulate such releases to protect the public. In actual practice, the amount of radioactivity released is held to only a very tiny percentage of the amount permitted by the standards. The natural background radiation you would receive from taking a plane ride across the country or from spending a summer in the mountains would be about the same as you would receive if you lived next door to an atomic power plant for an entire year. One of the reasons for the success of our agriculture was the use of insecticides, resulting in more abundant crops due to the elimination of pests. But unfortunately, insecticides can be harmful to livestock and wildlife. However, insect control is a necessity. So, by using atomic energy as a research tool, experiments are underway in a number of universities to develop insecticides which will do their job without causing side effects that harm the food chain, from plant to animal to man. At the University of California at Riverside, the Department of Entomology is doing decisive research work in this area under the guidance of scientists such as Dr. Roy Bakuto. The purpose of these scientists is to aid in the development of insecticides which are selectively active. To put it simply, the goal is the creation of insecticides that control pests but do not harm humans or livestock. Well, how does nuclear energy come into the picture? Radioactive carbon is the research tool that traces the effectiveness of the insecticide being tested. 2 samples of insecticides are being tested. Sample A, used as a control, is a compound currently on the market. It is poisonous to warm-blooded animals. The new compound B is selectively toxic to insects, and therefore may be used without harmful effects to our environment. Both samples were previously tagged with radioactive carbon. The presence of radioactivity is detected with the radiation counter. The bottle caps have to be removed to obtain a measurable radiation count. Here we see some highlights of the experiment. This mouse is fed with compound A, the currently used toxic insecticide, and placed inside a metabolism chamber. A second mouse is given a sample of compound B, the new insecticide. Another metabolism chamber. The test animals spend predetermined time periods in the metabolism chambers. At certain intervals, urine specimens of the 2 test animals are taken to determine the relative metabolizing action of samples A and B by the test animals. Specimens are placed into this radiation counter to measure the radioactivity. Now a tiny amount of both samples is placed on this chromatography plate. The compounds will move to different places on this plate. The positions will indicate the nature of the compound. The slight radioactivity of the compounds makes it possible to trace them on a photographic film for easy visibility. Thus, atomic energy, through the position of the spots, helps the chemist reach the conclusion that compound B, the new insecticide, is indeed less dangerous to warm-blooded animals than the sample taken from the currently used insecticide. Although it is illegal to dump oil into coastal waters, some ships still flush out their fuel tanks, discharging oil into coastal regions, usually at night. As a result, oil slicks may be washed up on beaches, destroy marine life, even cause fires. Since our bodies of water are already burdened with more waste material than they can manage, the Coast Guard has added another duty to its routine patrol: protection of the marine environment. be able to relate the sample to the polluting ship. Samples for comparison can be taken from ships suspected of dumping the oil in that area. The link between the oil slick and the suspected ship can be established by a novel use of atomic energy called neutron activation analysis. It produces atomic fingerprints in samples under investigation. A small nuclear reactor is used for the next step. The oil samples scooped from the ocean, as well as the samples collected from the suspect ship, are made radioactive. Then, a radiation counter is used to produce a profile of each radioactive sample. The information is also recorded on a printout. The atomic fingerprints are compared. In the event that an oil sample from the suspected ship matches one of the oil samples retrieved from the ocean, the authorities can be reasonably sure who caused the pollution, and existing laws can be enforced. Wave energy and strong ocean currents often cause beaches and sandbars to appear and disappear. Beach erosion is a constant threat to recreation areas and homes near the sea, and sand eventually clogs channels. In some cases, constant, expensive dredging is required to clear harbors and channels from shipping. In order to learn more about the mysterious movements of the sand, and perhaps help prevent our valuable beaches from eroding, the Atomic Energy Commission, working Engineering Research Center, and Oak Ridge National Laboratory, is studying how the pounding of the waves and currents above affects the movements of the sand below. These boxes contain sand tagged with tiny quantities of radioactive gold. Not enough for a treasure hunt, but sufficient to gain certain important information about our environment with the help of atomic energy. This sled is used to place the gold-tagged sand at certain predetermined locations. Plastic bags will disintegrate in salt water. Tagged sand is placed along the beach according to a predetermined pattern. These experiments are conducted at Point Mugu in California. Deposits are made also below the waterline. Fragments place stationary radiation monitors to help measure the radioactively tagged grains of sand that are spreading along the ocean floor. This roller-shaped apparatus, called the ball, is a highly sensitive mobile radiation counter. It is used to survey the gold-tagged sand. The study of one series of placements may continue for a week until decay and dilution make radiation undetectable. The ball is pulled along the beach through the water. Distances up to 1,500 feet from the shoreline. The signals picked up by this atomic radiation detector accurately reproduce data as indicated by this map, showing for the first time the movement of the sand under the sea. Rivers, by their very nature, have their own cleaning mechanisms. But ever-increasing amounts of waste dumped into rivers often exceed the flowing water's capability for self-purification. With the use of AEC-produced radioisotopes, the Georgia Institute of Technology is studying the problem. These men are preparing atomic tracers for use in this research work. Bottles containing the atomic tracers in red dye are emptied into flowing water. The red dye so that the movement of the radioactivity can be easily followed. Samples collected at various points downstream will be taken to the Institute for Atomics. The tests will indicate the decrease of radioactivity of the atom. These data relate to the amount of oxygen absorbed from the air. will give a much more precise picture of a flowing stream's ability to purify itself. That is, to absorb oxygen, upon which the very life of a river depends. The findings will aid in the proper placement of sewage plants, industrial facilities along rivers, and help determine permissible waste output. Industrial wastes are killing fish in the Great Lakes. In order to fight the problem, scientists are determining which pollutants are mainly responsible. They collect fish throughout the Great Lakes. The case history of every fish is fed into a computer. Then the vital organs of the fish are removed for analysis. AEC's Argonne National Laboratory, in cooperation with the U.S. Bureau of Fisheries, is trying to isolate fish killers. Neutron activation analysis is used to identify poisonous elements, such as mercury, copper, zinc, and arsenic, shown here in their specific profiles, their telltale atomic fingerprints. This information helps to provide a picture of the dispersion and types of the pollution in the Great Lakes. Belching batteries of smokestacks used to be the hallmark of industrial success. Today, they are signposts of deep concern to ecologists and the medical profession. AEC's Brookhaven National Laboratory, in conjunction with the National Air Pollution Control Office, took off on an airborne program of diagnostic studies to determine the extent and composition of typical plumes and their effect on the surrounding area. Industrial plumes contain polluting sulfur dioxide. In this compound are naturally varying amounts of two types of sulfur. The ratios of the two types of sulfur can be measured by means of stable atomic isotopes. This information helps determine the intensity and dispersion of corrosive smoke particles and predict pollution patterns over our cities. The planes fly through the plumes at predetermined intervals to gather samples of the spreading pollutants. Samples brought back will provide knowledge of pollutants in industrial smoke. Such information is important to pollution control and will help decrease the damage to man and vegetation in the environment. This geodesic dome, the climatron, houses a tropical forest in the center of the United States at the Missouri Botanical Gardens in St. Louis. Experiments in the fight against pollution are conducted under the guidance of Dr. David Gates, using radioactive tracers to study the way plants convert carbon dioxide into oxygen, and to what extent plants can absorb substances such as sulfur dioxide, one of the most dangerous pollutants from coal-burning furnaces and automobiles. Photosynthesis is a key link in the chain of life. The functioning of the green leaf and other green plants is responsible for the survival of the human race. Changes in the environment due to pollution could jeopardize the process of photosynthesis. So it is essential to investigate the effect of pollution on the plant life of the world. Studies conducted here with the help of the atom yield valuable answers. Other answers will come from experiments in this forest at AEC's Oak Ridge National Laboratory under actual outdoor conditions. The tagging capability of radioactive cesium is used to learn more about the growing process of plants and trees, and to help determine the flow of elements through the forest and its grasses, shrubs, and trees. And now, take a look into the possible future of the atom's fight to help our environment. Perhaps underground atomic explosions could provide safe storage space for waste material. New types of power plants employing nuclear fusion, producing temperatures hotter than the sun, hopefully someday could supply almost limitless, pollution-free energy for the world of tomorrow. And perhaps the same energy, in the form of the fusion torch, would reduce the vast amounts of industrial and household wastes to their original elements, making the continued recycling of our resources a possibility. Yes, the fight for the preservation of the Earth's environment goes on. And one very valuable weapon in the arsenal of the ecologist is magic of the atom.
This, our country and all its people, could be in danger of nuclear attack. In minutes by enemy missiles. In hours by enemy aircraft. Our cities, our farms, our factories. Prime target would be our air bases. With all our aircraft on the ground, our weapons of interception or retaliation not instantly available, we might face another and infinitely more costly Pearl Harbor. To avoid surprise disaster, some of our aircraft must always be in the sky or on the alert, carrying nuclear weapons. These weapons are always unarmed. They will be armed only following a decision by the President of the United States. Only these ready aircraft with nuclear weapons can form our first-line deterrent force in peacetime. Our sure striking force in case of attack. We, the American people, understand and accept this necessity for our survival. But we want to know the facts about one question. Do we live in danger of nuclear explosion and radioactive fallout if one of these airplanes should crash, or one of these nuclear weapons accidentally drop? To give you the facts, the United States Air Force presents carries a nuclear weapon. It is a well-designed, carefully maintained, skillfully flown airplane. But airplanes, just like it, have crashed and burned. There was no nuclear explosion, no radioactive fallout. These are the facts. The bombardier watches over controls as safe as human ingenuity can make them to prevent accidental bomb release. But nuclear weapons have been dropped inadvertently. There was no nuclear explosion, no radioactive fallout. These are the facts. And specially instrumented aircraft verify these facts in a continuing nuclear safety program that tests our nuclear weapons under controlled conditions that simulate every conceivable hazard. Vital to this nuclear safety program is Air Force Special Weapons Center at Albuquerque, New Mexico. Here, in ultra-modern laboratory buildings, work scientists in and out of uniform. They work with the incredibly complex equations of nuclear physics which derived from Einstein's famous relationship of mass to energy. These cryptic figures, programmed into lightning-fast computers, are the theoretical base upon which these scientists, together with those of the Atomic Energy Commission, can build nuclear weapon safety. By research, design development, and laboratory tests, they ensure weapons not yet built against accidental nuclear explosion. They have been doing this successfully since 1945 in safety conferences with other Defense Department agencies and the Atomic Energy Commission. In 13 years, there have been a few accidents, but not one has resulted in nuclear explosion or radioactive fallout. These are the facts. What keeps our nuclear weapons safe? To understand why there has never been an accidental nuclear explosion, you must first know how these explosions can be produced, the general principles of nuclear explosion.
Any explosion is the result of a very rapid release of a great amount of energy. Conventional explosions result from the rearrangement of whole atoms in some explosive material. For example, in TNT, the rearrangement of whole atoms of hydrogen, carbon, nitrogen, and oxygen produces explosive force. On the other hand, nuclear explosions result from the rearrangement within each atom. This may be a joining together or fusion, as in an H-bomb, or the splitting apart or fission, as in an A-bomb. At present, an H-bomb explosion starts with fission. So the splitting of the nucleus of the atom is the basic principle of nuclear weapons. All matter is composed of one or more of the 100-odd elements. Of these, the atoms of the metals uranium and plutonium can be most readily fissioned to cause nuclear explosion. These elements are mildly radioactive. They emit short-range, low-penetration alpha particles while in their unfissioned state. These alpha particles do not have the harmful effects of the longer range and stronger gamma rays, which are given off by certain elements such as radium or by the products of nuclear fission. The atoms of uranium and plutonium are among the heaviest. Heavy because the nucleus of each atom contains large numbers of the fundamental particles called photons and neutrons. When a free neutron hits this nucleus, it splits into two parts, releasing more neutrons which may go on to split other nuclei. The resulting fission products become highly radioactive, emitting the long-range and dangerous gamma rays. The split nucleus weighs less than the full one, and this difference in weight is released in the form of energy, nuclear energy. After fission, harmful gamma radiation. Before fission, innocuous alpha radiation. To build up a nuclear energy release, the fissionable material must be of a certain size, shape, or density. Then one of the neutrons escaping from a split atomic nucleus will, in turn, split another, and a chain reaction is set up. The mass is now releasing nuclear energy, but not quickly enough to cause a nuclear explosion. This condition is called critical. If the mass is now suddenly increased, so that more neutrons are trapped each time an atomic nucleus is split, a multiplying chain reaction is maintained. Now the mass is supercritical, causing a nuclear explosion. Density of the fissionable material can be as important as mass in building up a nuclear explosion. The same sphere can be compressed so that the atoms are closer together and neutrons split more atomic nuclei, making the smaller mass critical.
If compressed still more, a multiplying chain reaction sets in, causing the mass to become supercritical in a nuclear explosion. Nuclear weapons make use of both of these principles. A gun-type device can increase the mass of fissionable material to a supercritical state instantaneously. One subcritical mass is propelled forcibly into another by an ordinary Potter charge. The increased mass becomes supercritical. A multiplying chain reaction builds up until the nuclear explosion. Obviously, if any mechanical device keeps these two subcritical masses apart, the weapon is nuclear safe. Applications of this fact prevent accidental nuclear explosions in gun-type weapons. Another kind of nuclear weapon is the implosion type. It compresses the fissionable material to greater density to make it supercritical. To do this, the sphere is enclosed by a shell of ordinary explosive designed to direct its explosive force inward. This effect is called implosion. The detonators attached to the explosive are connected to a complex firing device, which can fire every detonator simultaneously. When all the explosive is detonated simultaneously, the nuclear material is compressed into a supercritical mass, which results in a nuclear explosion. Implosion-type weapons are nuclear safe because only the specially designed firing device can produce the simultaneous detonation of all the ordinary explosives, a deliberate effect possible only by the precise firing mechanism. Should a single detonator be fired accidentally, whether by malfunction, crash impact, or fire, the explosive would not provide the all-around compression necessary for implosion. Instead, it might push the nuclear material out of the shell, break it into small pieces, or even burn it. This unfissioned material emits only alpha particles because no nuclear explosion has taken place. These alpha particles do not penetrate the skin. The simplest precautions can prevent their intake into the body, and the simplest cleanup measures can remove them. So you see, each type of nuclear weapon has its own safeguards against accidental nuclear explosion. These are the facts.
And they are based upon practice as well as theory. Specially instrumented aircraft fly the tests that verify what happens inside a weapon, what accident hazards the nuclear components may have to withstand. Nuclear safety is everybody's business. Although Air Force flies the test missions, scientists and technicians from the Atomic Energy Commission and other services man the test range and evaluate the findings of the elaborate instrumentation. Drop tests measure impact characteristics of various weapon types. They are made without nuclear components, so that this precious material is not wasted. They supplement the detonation tests that have been made with the complete nuclear weapon. Impact or shock does not cause nuclear explosion or radioactive fallout. What has exploded is the ordinary explosive, which is an essential part of nuclear weapons. The ordinary explosive in a nuclear weapon can be a hazard, exactly as in a conventional bomb. Depending upon the amount and location of the explosive and the speed and height of the drop, we may experience a variety of ordinary explosions. Large ones, small ones, or none at all from impact of the bomb. Beside the hazard of impact, frequent tests are run on the hazard of fire.
To learn what temperatures and pressures would be created inside a weapon by an aircraft fire, various types of bombs are subjected to a flame bath of burning fuel. Because fire would also destroy the precious nuclear material, it is replaced by instruments. Their readings are compared with known characteristics of the fissionable material to assure that temperatures higher than any aircraft fire will not set off a nuclear explosion. The characteristic white flame indicates that the ordinary explosive is burning in the weapon. Sometimes the explosive detonates because of close confinement and intense heat. The effects of such explosions are measured and compared with those in an actual nuclear weapon. Fire and ordinary explosives do not create the conditions necessary for nuclear explosion. These are the facts. And on the vast desert ranges of the Atomic Energy Commission, the facts are verified by safety testing live prototypes of all new weapons before they go into production for our stockpile. The tests are costly in money and manpower, even more costly in the fissionable materials on which our nuclear strength depends. But they do provide insurance against nuclear accidents, which makes them a bargain at any price. Some take place deep in the earth. Fantastically complex instruments replace the five senses. They record what happens when some of the explosive that surrounds the nuclear material of a new weapon is deliberately detonated. They record only an ordinary explosive blast. A random detonation has not created the implosion which would compress the nuclear material to a supercritical mass. There was no nuclear explosion, no radioactive fallout. Each new design must be proved nuclear safe, able to withstand accident, fire, or random explosive. Other tests with nuclear weapons are made above ground. These are also designed to test the nuclear safety of new weapons types by intentionally detonating the explosive which surrounds the fissionable material. Sometimes these tests also provide data on the side effects to be expected if the fissionable material is broken up by the explosion. Air samplers and test pads are used to gauge the area, intensity, and duration of these side effects. In this way, they learn not only what does not happen when a charge is deliberately fired, but what does. The explosive does break up the nuclear material and scatter parts of it over a small area. This fissionable material is mildly radioactive. If the explosion or fire should suspend any of this material in dust or smoke, it should not be inhaled or otherwise taken into the body in quantity. That is why the trained monitoring and cleanup crews may wear respirators until air samplers or alpha counters have determined that no injurious concentration exists. The alpha particles emitted do not penetrate skin or clothing, so this material is harmless when on the ground. Only simple cleanup measures are necessary, plus an effort to find and save the valuable material. The findings from all tests set up to measure possible radiological hazard are no external radioactive hazard from material on the ground, slight radioactive hazard from prolonged inhalation of material suspended in a small area near the accident, but none from the short exposures necessary for firefighting, rescue, or cleanup of the small area involved. These are the facts. Facts that have dispelled the fearsome myths about accidents involving nuclear weapons. For anyone near an accident, whether or not the crashed airplane carries a nuclear weapon, Here are the safe and simple rules. Stay away from the crash unless you are needed for rescue. Bystanders endanger themselves and hamper others. To be safe, keep at least a quarter of a mile away from any burning airplane. At this distance, you are safe from the flames, which may explode the jet fuel, from detonating explosives, and from flying debris. These are the real dangers in rescue or firefighting, as they have always been. The trained men who bear these responsibilities know how to do their job and get quickly away from all these hazards. After the emergency is over, the area is monitored for radioactive material and, if necessary, cleaned up by specially trained teams. Other specialists care for burned or undetonated pieces of ordinary explosive. Until this is done, access to any crash area is controlled to prevent accidents and speed up the work. The tests you have seen have proved the safety of our nuclear weapons program over and over again. But the grim reality is the payoff. How safe is a nuclear bomber coming in for a crash landing? Even detonation of the ordinary explosive in the weapon cause nuclear explosion or radioactive fallout. The safety that was designed in during research, built in during development, proved in the laboratory and on the range, has withstood the ultimate tragic test. These are the facts. They prove that you, the American people, can stay both safe and strong. Safe because the weapons your Air Force must carry have been tested nuclear safe. The possibility of an accidental nuclear explosion is so small as to be practically non-existent. Strong because an Air Force, nuclear armed and combat ready, stands guard against surprise attack. Under this shelter, you and your family may live in peace, free from the fear of nuclear accidents.
Disaster is never pleasant. For a long time, schools have been improving ways of protecting children from the kinds of disasters and accidents we have come to expect. These safety measures are essential. Today, however, we are threatened with a new form and magnitude of disaster. For this is the age of the atom. So long as we are confronted with this unprecedented threat, protection of our children must be a basic goal of every educational program. We can achieve this goal only by undertaking a comprehensive civil defense program in all of our schools. Protection from nuclear attack is possible. Local conditions will dictate the courses of action. There is a general concept for every school system to follow in developing a civil defense program. First of all, the general objectives and main features of the plan must be carefully worked out by the superintendent for presentation to the school board.
We presented this program to you a week ago at your meeting, and I need hardly tell you that this proposal to expand our school protection program was worked out with the close cooperation of Mr. Miller, our city civil defense director. The program consists of two main parts: protection to take care of our immediate survival needs, and a curriculum program to include civil defense in our courses of study. Before I describe in detail...
In this meeting, the school superintendent is seeking the board's approval of the general proposal. Before he can proceed with a more detailed plan, the board must endorse the proposal and authorize funds for development and implementation of the plan.
Thank you, Mr. Douglas. The board has already studied the outline of this proposal that you gave us last week. Those in favor of proceeding with a more detailed plan? Opposed? Carried. And now I think we should review.
A few days later, the superintendent meets with his staff and all principals to explain the new directive and to make specific assignments for detailed planning. The curriculum coordinator heads the curriculum committee. The safety supervisor is appointed chairman of the protection committee. The school architect engineer is made chairman of the fallout shelter committee. Many others, such as the chief school nurse and the head building custodian, are assigned responsible positions. Everyone on the staff has an important role. The civil defense director is present to explain how the schools fit into the total community survival plan. Principals are charged with full responsibility for developing and executing both the protection and curriculum programs in their own schools, programs which will conform with those established for the entire system. Before calling a meeting of the entire staff, principals in turn discuss the program with some of their key people. The school safety supervisor is appointed as the civil defense coordinator, and teachers serving on the curriculum committee are told to prepare for special meetings to find ways of building civil defense into the courses of study. One of the first steps in developing the protection program is to decide on the best and most economical ways of providing shelter from radioactive fallout. With the aid of the local civil defense director, the school superintendent and his architect engineer make detailed plans for including dual-purpose fallout shelters in all new school construction. Plans are approved, funds obligated, and the real work gets underway. When this shelter is completed, it will also serve as the school cafeteria. Existing school buildings throughout the system are surveyed to determine what areas within them are best adapted for shelter use or for ready conversion to shelters. This area, for instance, was formerly used for coal storage, but now it serves as both fallout shelter and workroom for school theatrical production. This school needed more classroom space, but to add it above ground would have taken away valuable playground area. The problem was solved by building dual-purpose shelter classrooms underground according to specifications furnished by the Office of Civil and Defense Mobilization. Alternate plans for evacuating the schools in target areas are also developed. If there is enough advanced warning of an attack, civil defense plans in many target cities call for sending children home from school. Some target cities, such as this one, if there is adequate warning time, plan a general evacuation to safer areas. With the help of the local civil defense director, the school superintendent makes certain that arrangements for evacuating schools in his system are coordinated with those already established for the community at large. Cooperative arrangements must also be made between school and local government officials at reception areas. Development of an adequate internal warning system for the schools also is carefully worked out to supplement existing civil defense warning facilities. This community has a good outdoor warning system with sirens covering the entire area. Everyone here knows that the alert signal, a steady blast of from 3 to 5 minute duration, means to take action as directed by the local government. And that the take cover signal, a wailing tone or a series of short blasts of 3 minutes duration, signifying attack is imminent, means to take cover at once in the best available shelter. To supplement these outdoor signals, an indoor warning system is needed. Although there are other approved systems for instantaneous relay of warnings, bell and lights are used here to alert the school. Public address systems are installed so that emergency instructions can be given to the students and staff in the shortest possible time. Here's how the whole system works. When a warning is received by the local government through the attack warning system, sirens and bell and lights throughout the community are activated simultaneously. Informs the principal. Using the public address system, he gives appropriate directions to his staff and to the students. It cannot be stressed too strongly that any civil defense warning signal used in school must be clearly distinguishable from other types of alarms.
schools can be effective without the full cooperation of an informed staff. The importance of the role of teachers in conducting shelter drills, for instance, cannot be overemphasized. Efficiency of their teachers, youngsters gain confidence in arrangements made for their security. While individual schools may have different requirements, all must hold periodic drills to assure immediate response to warning signals. An adequate school fallout shelter should contain enough provisions to sustain students and staff for at least 2 weeks. In this combination shelter cafeteria, the cafeteria manager is in charge of emergency feeding facilities. It must be stocked with blankets for everyone assigned to the shelter. If the school is dependent on a vulnerable community water system, a special well may have to be provided for emergency water supply. Battery-powered radios with Conelrad frequencies 640 and 1240 clearly marked on the dials must be available to receive emergency information. A telephone tied in with the city's Civil Defense Control Center. First aid and medical supplies. Sanitation facilities and means for safe disposal of rubbish and wastes. Radiological monitoring equipment. An emergency electric power generator. And adequate ventilation are among the special items which must be provided. Because children would need some form of recreation, an area within the shelter should be available for physical activities and play. Of course, if time would permit, they would be in their own shelters at home. While the protection program is taking shape, civil defense is introduced into the curriculum at all levels. This third grade class, for example, visits emergency facilities in the community, like the local fire station. Here they learn that the people who protect them every day are a vital part of civil defense. In this 5th grade class, children make posters on home preparedness. Gradually, an awareness develops that civil defense is as natural, as meaningful, and necessary as everyday safety rules. The conditions of survival are learned. Preparedness becomes a personal responsibility. Discussion of the effects of natural disasters leads to a realistic grasp of the consequences of a nuclear war. The objective of curriculum planning is to give each student a background in the needs and methods of civil defense so that he will be prepared for living in the nuclear age. Under the supervision of the school nurse, first aid courses are taught as a regular part of the physical education program. homemakers in the 10th grade are getting some first-hand tips from their cafeteria manager on ways of preparing food for large groups of people. They learn that there is a real relationship between good food and good morale. Civil defense concepts should evolve naturally from existing subject matter, as in this 12th grade class in American government.
And if we were ever attacked, we would need more than ever the help and leadership of our government. Most states and many localities have already adopted this program to help us recover and to preserve our constitutional government. The first point in this continuity of government program is to establish automatic lines of succession to important positions. In a serious disaster, many officials may be unable.
This is a sound peculiar to our time. A sound that is meaningful to this 12th grade physics class studying the effects of radioactive fallout. Radiological defense instrument kits for use in science classes have been distributed to high schools throughout the nation by the Office of Civil and Defense Mobilization. From experiences like this, young people grow in their understanding of the problems they must face, of the responsibilities they must accept as citizens of the nuclear age. If it is to be a successful program in our schools, civil defense must also be understood and practiced in our homes.
It's vitally important to everyone. We have been talking about some of the precautions schools are taking to protect their children and to help them meet the challenge of our time. But I want to stress that it's just as important that we carry this knowledge, these preparations, into the home. Let's take a look at some of the things that we as parents and as citizens are obligated to know. Warning signals, what they mean. Your community plan for emergency action. Protection from radioactive fallout through shelter. First aid and home emergency preparedness. Use of Conrad 640 or 1240 on your AM radio for official direction. And these are some of the things that we must do. Prepare a family fallout shelter and equip it with 2 weeks' supply of food and water, a first aid kit, and a battery-operated radio. Since we are in a target area, prepare an evacuation kit for your automobile. Include a supply of food and water, a first aid kit, a battery radio, and blankets. First, let's talk about the family fallout shelter. This is a model of one of the types of family shelters recommended by the Office of Civil and Defense Mobilization. It is best to
the protection of our families at home and in schools is basic to the success of any community or national survival program. For the sake of clarity, let's review some of the steps in preparing a school civil defense program. After outlining a general plan with the help of the local civil defense authority, the superintendent makes his proposal to the school board. With the board's approval, he calls a meeting of his staff and principals to explain the new policy. Starting with the emergency plan, a shelter program is developed under the supervision of the architect-engineer who worked with the Civil Defense Director. If evacuation is called for in the community survival plan, school procedures are designed to conform with it. The The entire school system is provided with a reliable warning system. Individual schools carry out their directives and refine their programs through regular drills and exercises. Following committee recommendations, the curriculum is modified to incorporate civil defense and survival techniques into the existing courses of study. And home preparedness is stressed as a necessary extension of the school survival program. Approaches to the development of school civil defense programs will necessarily vary according to local conditions. But if these guidelines are followed, while working closely with local civil defense officials, schools will be better prepared to meet any disaster. A nuclear war may never come, especially if we are prepared. But we cannot ignore the threat. The stakes are too high.
Over 19,000 disasters strike somewhere in our country every year. That's more than 50 disasters every day. Some are major, like Hurricane Camille. I witnessed this awesome destruction. But Hurricane Camille, and even the greatest natural disaster we could imagine, would be dwarfed by the loss of lives and property in a nuclear attack. I'm saying this because I have good reason to be concerned. My name is John Davis, and I am the National Director of Civil Defense in Washington, D.C. Our purpose in civil defense is to protect you and to help you protect yourself in time of emergency. That's the reason we have prepared this special film to tell you what actions you should take to help protect yourself and your family in case of a nuclear attack. The protective actions you take today would not be wasted if a nuclear attack did not occur. Experience tells us that these actions save many lives in natural disasters and other emergencies. The surest way to invite disaster is to do nothing to avoid it. We give this film your total attention.
Most likely, the most important fact in the world today is this. We've been living in the atomic age since 1945. For a long time now. And none of the catastrophes so freely predicted, so honestly feared, have come to pass. True, there have been dangerous moments like the Berlin and Cuban crises. But so far, sanity has prevailed. And hopefully it always will. And yet there's no point in looking away from reality. We live in a troubled and uncertain world. And it's got to go on being troubled for a long time to come. The nuclear genie is out of the bottle. And until the world finds a way to clap it back in, and then put a lock on the stopper, there'll always remain the outside chance that what our nation and a great many others have been working so hard to avoid could conceivably happen after all. And of course, so long as even the slightest possibility exists, it's something we must reckon with, guard against, prepare for, just as a common sense precaution. So let's talk a little about these things, about what's being done to protect you, and about what you can do to protect yourself in time of emergency. Of course, our first and strongest line of defense lies in what the strategists call the power of deterrence. In our intercontinental missiles, our nuclear submarine fleet, strategic air command, in the ability of all our military forces to retaliate, even after a surprise attack, and do it with such enormous force that the aggressor would be defeated, most likely destroyed. And in that fact, that knowledge alone, lies the strongest incentive any enemy could have to avoid launching a nuclear war. But behind the sword, there's also a shield. Very quietly, but steadily over the years, we've been building a nationwide system of civil defense, designed to save lives, to protect as many of our people as possible. It consists of many things. The National Warning System, tied in with NORAD, the North American Air Defense Command, able to alert the whole nation in a matter of minutes. A monitoring network with more than 65,000 locations to measure and report fallout radiation. And most important, a very large and growing public shelter system to protect us from that radiation. Local governments have been making detailed plans to deal with all kinds of disasters. An emergency broadcast system, organized to keep you informed, and thousands of special emergency control centers to direct life-saving and recovery operations. In short, if attack ever threatened, there'd be help available from many sources. You would not be alone. But a lot, inevitably, would depend on you. There's no point in denying or trying to minimize the grim fact that a nuclear attack would take a heavy toll of lives. But in all the Defense Department studies, and there have been many of them, two things come clear. Even under heaviest attacks, our nation could, in fact, would survive. And our losses would be much less, your own chances of survival much greater, if each of us would take time to do just three things. First, understand the dangers you face. Second, make some fairly simple preparations to meet them. And third, learn exactly what to do if emergency comes, and then do it. 1, 2, 3. Now, about those dangers. There are some you can't do much about, but others you can. And knowing the distinction between the two could very well mean the difference between staying alive or dying an utterly useless death. When a thermonuclear weapon explodes, 4 things happen. First, a brilliant white flash of light. Then, a searing wave of heat shooting out from the nuclear fireball. The blast wave hurling debris before it. But even under heavy enemy attack, only 4 or 5% of our land, 1/20th of the country, would be affected at all by blast and heat. All the rest and all the tens of millions of people in it would escape untouched, except by radioactive fallout. It could spread on the wind to cover not just 5%, but 80 or 90% of our country. But that's one danger you can do something about, if you know a few facts about fallout. When a nuclear weapon explodes anywhere near the ground, tons of dirt and debris are pulverized into millions of tiny particles, swept up into the fireball, turned dangerously radioactive. They drift downwind in the mushroom cloud, then start slowly falling back to Earth. The heaviest and most dangerous particles first, after 15 to 30 minutes in the area nearest the explosion. The lighter ones later, perhaps hours or days later, and hundreds of miles away, wherever the winds may take them. But wherever they fall, in fields and streams, on rooftops, or in the streets, they spell danger. Each one of these fallout particles, no larger than grains of salt or fine sand, is like a tiny X-ray machine, shooting out deadly, invisible gamma rays that can damage or destroy the cells of your body. Too large a dose in too short a time means sickness or death. But it's a useless way to die. Useless because it's unnecessary if you use the three defenses you have against it. One is time. The most dangerous period would be the first 24 hours after fallout arrives. But fortunately, radiation decays very rapidly. It's like an elevator going down fast. For example, if all the fallout were down on the ground 1 hour after the burst, then by 7 hours, the radiation would have dropped to just 10% of that 1 hour level. By the end of 2 days, it would be down to 1%. And in 2 weeks, it would be just 1/10 of 1%. In short, with shelter, you can wait it out. But while you're waiting, you'll need protection. And that comes from two things: mass and distance. Mass, meaning thick, heavy, dense materials. Concrete. Steel. Even ordinary earth, to absorb or deflect those deadly gamma rays, reduce the amount of radiation reaching you. And distance, because the farther you are from the source of the radiation, fallout particles settled on the roof or on the ground outside, the safer you'll be. Put those two together, mass and distance, and you've got a fallout shelter. You'll find it wherever you see this sign, the black and yellow sign that marks our community fallout shelters. And they could mean the difference between life and death in time of emergency. Of course, if you're convinced of the utility of it all, and you want to just stand out there and stare your breast to radiation, that happens to be your privilege. But as we all found out in the Cuban crisis, that kind of talk becomes just talk. As the real danger mounted, so did our will for survival. We all discovered a reason for living: ourselves, our families, our children, and we were all looking for shelter. Well, it's there now, ready for use. A nationwide system of more than 100,000 large public fallout shelters located in office buildings, apartments, schools, factories, stores. And it's a good idea to look around, to know at all times where the nearest ones are, just in case they ever prove needed. Of course, there's still not enough, and they're not everywhere. Usually, there's plenty of fallout shelter downtown where most people work, but less in the suburbs where a lot of us live, and not nearly enough out in the country where there aren't enough buildings with heavy construction. If that's the problem, if you're just too far away from the nearest community shelter to reach it in time, then you'd better do something about it. One answer may lie in your own home. If the house has a basement, earth and concrete may give you some shielding already built in. And to help fill in the gap, the Office of Civil Defense has been conducting home surveys in many of our states, asking each homeowner to fill out a questionnaire, then telling them by means of computers exactly how much fallout protection is already there. If you've already taken part in one of these surveys, you already know if your house has enough. And if it hasn't, well, usually all it takes to improve it, to build a home shelter in your basement, is some do-it-yourself effort, plus a couple of $100 at most for concrete blocks and other materials. And in extreme emergency, if crisis seems imminent and no shelters available, it's still possible to improvise some last-minute protection against fallout. Not as good as you'd find in a regular shelter, but any protection's better than none, and it could be enough to save your life. Remember, use mass and distance to reduce radiation. Choose the corner of your basement that's most below ground level. Set up a sturdy table or workbench there. Wall it in with the heaviest materials you can find. Bookcases, chest of drawers, appliances, trunks. Then, fill the drawers with earth or sand to give added protection. Cover the top with as much heavy shielding as it will hold. House doors, bricks, flagstones, firewood. Then, once your family is all inside, block up the entrance, leaving an opening at the top just large enough to let air in, of course. If you live in the country and your home lacks a basement, a storm cellar outside can serve just as well. If the existing roof is made of light wood, put in extra posts and braces to support the added weight. Then cover the roof with a foot or more of earth to give you solid protection. After everyone's inside, use bricks, sandbags, or heavy concrete blocks to wall up the entrance, leaving just a few inches open at the top, again for ventilation. Or you can improvise a shelter in your yard. Dig an L-shaped trench, 4 feet deep and 3 feet wide. Make the longer side of the L big enough to accommodate your family. The other leg will serve as an entranceway and help reduce the amount of radiation getting into the shelter area. Shore up the sides of the trench for safety. Then cover it with house doors and heavy timbers. Then pile on a foot of earth for protection. As a last resort, even if there's no basement or storm cellar available, you could get some limited fallout protection by improvising a shelter on the ground floor of your home. Use a hallway, an inner room, or large clothes closet, away from outside walls and windows. With doors, chests, trunks, and boxes filled with earth or sand, you can create an enclosure large enough to live in for the short time of that first peak period of density. If the inner space you've chosen is too small to allow room inside for all these shielded materials, place them against the other side of the walls, in the surrounding room. All these are last-minute measures, of course, for use only in extreme emergency if you just can't reach a regular fallout shelter. But it's better not to wait that long to make some preparations, particularly when it comes to supplies. Most community shelters, though not all of them yet, have been stocked with the basic requirements: emergency food rations, water containers, sanitation equipment, medical kits, radiation detection equipment. But even so, in a time of crisis, shelter living would be Spartan, none of the comforts of home. And there are things you'd better plan to take along to help ease that shelter stay. A battery-powered radio, flashlight and extra batteries, a blanket for each member of the family, any dietetic foods or special medicines your family may need for reasons of health, like insulin, heart tablets, antihistamines. If you have a baby, don't forget bottles, disposable diapers, cans of formula, and special baby food. And of course, if your neighborhood shelter is not stocked with the basic supplies, you'll need to take as much water and ready-to-eat food as you can carry. That's true of a family home shelter, too, for here you'd be on your own. So keep a 2-week reserve of supplies around the house for use in emergencies. For shelter use, canned goods are best. Soups, canned meats, all the pre-cooked foods. And packaged goods like crackers and wafers that don't need refrigeration. And water. That's even more important, for you can't live without it. As a minimum, 3 or 4 gallons for each member of your family, and store it in tightly capped bottles or plastic containers. If the supply runs low, don't overlook all the alternate sources right inside your house. The canned fruit and vegetable juices on the kitchen shelf. Soft drinks, milk, and ice cubes from a refrigerator. The 20 to 60 gallons in your hot water tank. And of course, all the water trapped in the pipes of your house plumbing system. In case of attack, simply turn off the main water valve in your basement to avoid having it all drain away if there's a break in the outside main. Then, turn on the faucet located at the highest point in your house, probably the upstairs bathroom, to let air into the system. Then, draw the water as you need it from the faucet located at the lowest point. It'll be pure, drinkable, and free from fallout. If some fallout particles are on food that you brought in from the outside, don't worry. They can't make it radioactive. Simply remove the particles, and you remove the danger. Just wash or peel the fruits and vegetables. Wipe off the packages or cans. For safety, it's better to make sure that babies or small children aren't allowed food or liquids that might be contaminated. However, in extreme emergency, thirsty people should not be denied water, even if it contains fallout. There's little danger that any adult could swallow enough to hurt it. It'd be like trying to swallow sand. Of course, we've only skimmed the surface here of things you need to know and do. But you'll find everything covered in fullest detail in this Citizen's Handbook prepared by the Office of Civil Defense. It's titled, In Time of Emergency. It deals with natural disasters as well as the dangers of enemy nuclear attack. And you can get a copy from the Civil Defense Office of your own local government. Read it. Study it. And above all, keep this quick checklist of emergency actions in mind. First, know your local emergency action plan. Hundreds of cities and counties have prepared and printed specific community shelter plans, complete with maps and detailed instructions, telling every resident where to go for the best available protection against fallout. Make sure your family knows the plan, where the nearest shelters are, and how to get there in time. Second, keep a stock of emergency supplies on hand. Foods that require no cooking, enough drinking water and other liquids, special medicine, radio, flashlight, blankets. And if you're planning to use a home shelter, don't overlook the problem of sanitation. Lay in a metal container with a tight-fitting lid, some plastic liners, and household disinfectant. You'll need them for disposal of waste and prevention of disease, to keep your family healthy through a shelter stay. If attack seems imminent, take precautions against fire. Close doors, windows, Venetian blinds. If you don't have Venetian blinds, cover the windows with household cleaning powder, aluminum foil, whitewash. For even in the fringe areas, miles away from any nuclear explosion, the heat wave could ignite trash and dry wood, set fire to your home. Have some basic firefighting tools on hand, especially a good fire extinguisher, and keep your garden hose connected. Unless your local authorities advise otherwise, fill the bathtub and other containers with water. For under enemy attack, the fire department may not be available. You'll have to help yourself. Above all, make sure you know what your local attack warning signal is. There are a few exceptions because of special local conditions, but in most communities, the standard attack warning is this. A wavering, undulating sound on the outdoor siren lasting 3 to 5 minutes, or a series of short blasts on whistles and horns. And when you hear that sound, believe it, an actual enemy attack has been detected. Don't reach for the phone to find out what's happened. The lines need to be kept clear for official emergency use, and you need to find shelter promptly. If you're caught in the open, if there's a sudden flash and you feel warmth at the same time, don't look at the flash. Move. Take cover instantly. Behind a tree, or a wall, in a ditch, or a culvert. Curl up on the ground and cover your head with hands and arms. Stay there till heat and blast waves attack. Then Get to shelter before the fallout starts falling. Then, turn on the radio. The emergency broadcast station serving your area will be bringing you news, presidential messages, civil defense instructions. You would not be alone. In many shelters, you'd find friends and neighbors who've been specially trained in shelter management, radiological monitoring, medical self-help. All across the country, the Civil Defense Monitoring Network would be measuring and reporting fallout conditions. And from the state and community emergency control centers, your own local authorities would be directing life-saving and recovery operations, keeping in close touch with each shelter. Just follow their official instructions and stay in the shelter till they tell you it's safe to come out. All these things are easy to remember and fairly simple things to do. None of them cost much in time or effort or money. If nothing ever happens, if the world maintains its sanity and enemy attack never comes, that time and effort will still have been well spent. For the better, both we and the nation are prepared. The less chance, really, that anything will happen. And if they ever prove needed, they could save your life in time of emergency.
Medical self-help is an emergency measure to be used only in cases of sudden or extraordinary misfortune. If people require medical care in the course of normal, everyday living, they should always be treated by a doctor. However, when disaster strikes, you may not be able to obtain trained medical aid in time. There are many forms of disaster. They can happen to you and your family at any moment. This film is one of a series on medical self-help. Its purpose is to teach you what to do in an emergency situation when there is no doctor.
This powerful X-ray machine, a tool of medical science, is being used for healing purposes. The radiant energy it emits is able to kill all living tissue within its beam, both sick and healthy cells of the human body. Its invisible rays so highly penetrative that protective shielding with lead glass windows must be used. X-rays are much like the gamma rays of radioactive fallout. We began our picture with X-rays because you are all to some degree familiar with their effects. But radioactive fallout is another matter. If you're like most people, it creates many questions in your mind, and you have doubtless read or heard some falsehoods and misconceptions. This film will tell you what you need to know about fallout, so that if our country is ever subjected to a nuclear attack, you can help yourself and your family to survive its dangers. For fallout is probably the most dangerous product of nuclear disaster in terms of the number of people who could be affected. It is also the one from which we are best able to protect ourselves. Let's examine what happens when a nuclear weapon is exploded near the Earth. First, there is blast, or the pressure wave created by the explosion, along with heat, the most intense ever created on Earth. Both will extend great distances from the point of the explosion, from 1 to 20 or 25 miles, depending on the size of the weapon. However, the further away you are from the site of the explosion, the less are the chances you will suffer the fatal effects of blast and heat.
There is yet a third immediate result of a nuclear detonation: initial radiation. The final effect is residual radiation, the main concern of this film, or radiation that follows the explosion and one that may remain at high altitude for some time before falling back to Earth. What exactly is residual radiation? Our sun, like other stellar bodies of the universe, is a giant nuclear furnace, burning at temperatures of millions of degrees, while emitting various types of radiation. Among these are gamma rays, shorter in wavelength than their closest neighbor, X-rays. The Earth's atmosphere prevents these radiations, dangerous to the health of man and animal, from reaching our planet. However, when a nuclear weapon is exploded, man is creating on Earth, in the splitting of atomic nuclei, his own nuclear furnace to produce the gamma and beta radiations of outer space. Let's see now just how this radiation is created. At the time of the burst, vast amounts of dirt, stone, and other debris, vaporized by the heat of the explosion, are sucked up into the rising cloud. As the mushroom cloud forms, these particles are made radioactive, for as they cool and condense, they are contaminated by residue from the bomb. These particles, when they fall back to Earth, are what we call radioactive fallout. Can you or anyone else predict with accuracy the pattern by which fallout particles will return to Earth? The answer is no, for fallout will depend on the number, size, and location of nuclear weapons exploded and the direction of upper air currents. Let's, for example, explore the fallout produced by one of these nuclear weapons. It sends its column of radioactive material up to 80,000 feet, or about 16 miles or more above the Earth. Here, the radioactive particles, beginning to drift downward, are at the mercy of upper air currents that vary from day to day, descending at various altitudes through many different layers of air that may be moving at varying speeds and directions. Thus, winds on the surface of the Earth give little help in determining the direction or the occurrence of fallout. Meteorologists, with their special instruments, however, can appraise altitudes as well as the total distance fallout will be carried. In a nuclear attack, keep tuned to your local radio station. It will keep you posted where fallout is taking place and its approximate amount. Though you may be able to see this dust once it reaches the Earth, you cannot see or detect the radiation it emits without the aid of radiological instruments. Nor can you taste, smell, or feel this radiation. Why is fallout so dangerous to human and animal life? Because each particle gives off radiation as if it were a tiny X-ray machine. This radiation consists mainly of gamma rays, which are extremely penetrating. Like X-rays, gamma rays are able to injure, even destroy the cells of our body if we are exposed to a sufficient dosage long enough, or if we eat or drink material contaminated by fallout particles. Exposure to gamma rays can make you sick, can even cause death. However, no matter how long one may be exposed to fallout, he does not become radioactive, nor can anyone catch radiation sickness from him like a contagious disease. In fact, this radiation cannot make anyone or anything radioactive. Now let us suppose that fallout has descended on this can. We'll let salt represent fallout dust. The particles don't go through the tin. The radiation does, but radiation is harmless to all except living material. It has no effect on the food inside. Now, if you wipe away the fallout particles, or better still, wash them away, the food inside cannot be contaminated and is perfectly safe to eat. The same is true of all foods and liquids that have been protected by packagings or containers, even the thinnest layer of cellophane. If you don't swallow the dust, there is no ill effect. If water for washing is in short supply, canned goods that may have been exposed to fallout can be handled safely with a piece of paper towel. Use one sheet of paper to lift the can and turn it upside down. There is no dust on the bottom. Now dispose of the paper. Wipe the sides of the can with a new piece of towel. And don't forget to put the contaminated paper in a covered receptacle. Now open the clean top. There will be no harmful particles in the food itself. A sealed loaf of bread that has been exposed to fallout can be salvaged in a similar manner. Turn the loaf upside down to expose the bottom, which will be clear of dust. Then dispose of the towel. Now insert a sharp knife through the wax paper at the center of the loaf and cut upwards, making a slot 4 or 5 inches lengthwise. Insert your fingers through the slot and rip the paper slowly open. The bread can be safely removed to a clean plate. Finally, dispose of the wax paper. Contaminated vegetables, such as potatoes, can be pared like this. Use a clean piece of newspaper and, working first in one corner, cut off one end. Move to a clean surface of the paper and peel in this manner. Move to another area of the paper and remove the other end. Dispose of all peelings and soiled paper carefully. After handling any contaminated food containers or vegetables, wash your hands. Fallout dust is dangerous, but it can be dealt with by following safe procedures. There is another widespread legend, the fear that fallout spells death to all life on Earth. The plain fact is that even if a great number of nuclear weapons were exploded, the resulting fallout would cover only a small area of the world's total land mass. The real concern then is this: if we are in that area, how do we protect ourselves? Like X-rays, radiation from fallout can go through almost every kind of building material. Over 99% would pass through glass, 66% through wood sheathing, 50% through a brick veneer wall. But only 1% of gamma radiation would penetrate 18 inches of concrete. And though it's not a building material, it's important to know that only 1% would pass through 25 inches of earth. Quite aside from the shielding effect of building materials, the intensity of radiation decreases with the square of the distance from the source. Thus, 10 feet away from a particle of fallout, the radiation rate is only 1% of that encountered at a distance of 1 foot. Other things being equal, the central parts of a building are safer. The radiation rate, or the intensity from fallout, decreases with the passage of time. In fact, for every 7-fold increase in time, the radiation will be reduced by a factor of 10. That means that at 7 hours after the explosion, the radiation level will be about 10% of its intensity at 1 hour. At 49 hours, it will be about 1%. Within 2 weeks, the radiation rate can be expected to decay to about 1/10 of 1%. Therefore, the most vital period to seek protection from fallout is the first few days after nuclear attack. Even more so, the first few hours. But remember, even with the passage of time, a low level of radiation can be dangerous. That is why you may need to remain within a sheltered area for as long as 2 weeks. These, then, are the 3 basic factors in protection against fallout: time, distance, and shielding. Time, meaning the longer you stay protected from fallout, the safer you will be. Distance, or the further away you get from fallout, the safer you will be. Shielding, meaning the more mass or weight you put between yourself and fallout, the safer you will be. You have often seen this sign on buildings. It means that indoors is a public fallout shelter, one of many and various kinds of buildings in your community that are similarly identified. Architects and engineers have carefully surveyed the shielding qualities of these areas to ensure they offer a minimum protection factor of 40 or more, meaning that in the event of fallout from a nuclear explosion, the mass and weight this shelter will place between you and the source of radiation will make you at least 40 times safer than if you were outdoors. Each of these shelters will hold at least 50 people and has been stocked by the government with austere supplies: food, water, sanitation equipment, medical kits, and radiological instruments. But what about millions who live in suburbs or rural areas, often far beyond quick walking distance of the nearest public shelter? With foresight, you can have a home shelter for the protection of your family, built from specifications and cost estimates for various types of shelters provided by your local civil defense office. The home shelter should be stocked with supplies of food and water sufficient for 2 weeks. Here you are afforded time, distance, and shielding if and when fallout, so dangerous to human health, should ever occur in your community. Just how much radiation can you receive without becoming sick? We measure exposure to gamma radiation from fallout in units called Roentgen. They're the same units used to measure X-rays, named for Wilhelm Conrad Roentgen, the discoverer of X-rays. People and animals may develop radiation sickness if they have been exposed to large amounts of radiation over a short period of time. Few people become sick who have been exposed to a total radiation dose of 100 Roentgens or less. However, exposure to more than 300 Roentgens over a period of a few days will cause sickness, may cause death. And if you receive an exposure of 600 Roentgens in that same period of time, death is almost certain. How can you tell just how much radiation you've been exposed to? These are the instruments commonly used to detect and measure radiation. They are part of the equipment supplied to the radiological monitoring team of every public shelter. With them, you can determine not only the total amounts of radiation received, but also the dose rate per unit of time, or the dose rate in Roentgens per hour. This is the dosimeter, conveniently shaped to be worn on one's person at all times. It is able to measure the total accumulated radiation exposure in Roentgen. The charger adjusts the dosimeter to a 0 reading prior to its use, with each separate exposure to radiation building cumulatively on the dosimeter gauge so that a reading of the total dose is available at any given time. Next, the Geiger counter. This instrument measures radiation in fractions of roentgens per hour within or outside the shelter. Finally, the survey meter, able to measure higher intensities of radiation that may exist outside the shelter. For home shelters, detection and measuring instruments are available from commercial sources. However, most householders will rely chiefly on their portable radios to receive readings as they are taken by civil defense monitoring teams. If there is a nuclear attack and you survive the initial effects of an explosion, you will have at least a half hour to get to a public or home fallout shelter. Therefore, to be safe from radiation sickness, get into the best available shelter as soon as possible. Once there, stay put, because each time you're exposed to fallout radiation over a period of a few days, the dosage continues to build until it reaches dangerous quantities. If you're among those compelled to travel through a fallout area on essential errands, there are certain rules to follow. Protect your body with boots or rubbers, gloves, headgear, and outer clothing that can be removed before you re-enter the shelter. On returning, brush off the rest of your clothing thoroughly, as well as any parts of your body that may have been exposed to fallout. If sufficient water is available, wash your face and hands carefully. Remember, these are the dosages of radiation as they affect human health. 100 roentgens, little or no effect. 300 roentgens, sickness or death. 600 roentgens, death. Recovery from radiation sickness is nothing new. Patients who are treated by X-rays routinely experience this sickness and get over it. Of course, the dosages they receive are carefully measured. Just as in combating the virus of the common cold, your general state of health will often govern how quickly you can throw off the effects of mild or moderate radiation sickness. In an emergency situation where there is no doctor, always treat radiation sickness by treating its symptoms. In fact, these symptoms are often similar to those produced by extreme anxiety or emotional stress. So it's best not to try to determine their cause. I repeat, do not try to diagnose. Merely treat the symptoms, just as you would if they were the result of any other type of illness. These are the symptoms of mild as well as moderate radiation sickness, one or more of which may appear shortly after exposure to fallout. Fatigue, loss of appetite, nausea, vomiting, prostration. The treatment is rest. For nausea, you may give the patient any of the commercial preparations that settle an upset stomach, or 1/2 teaspoon of baking soda in a cup of water. Tea and other hot liquids may be helpful. When a high fever is present, apply cold wet pack. Aspirin also tends to reduce the fever. In severe radiation sickness, along with the early symptoms, other symptoms may appear a week or more after exposure. Recovery is possible, but it'll take longer. The symptoms are diarrhea, inflammation of mouth and throat, loss of hair. For treatment, control the diarrhea and give aspirin and warm water gargles. People are naturally alarmed at the thought of bodily changes that may follow severe radiation sickness. such as loss of hair or sterility. These conditions are usually temporary and will disappear with recovery. So I hope we've dispelled another commonly held myth. You can get over radiation sickness just as you get over many others. Nevertheless, don't minimize the danger of fallout. Remember, its effects are cumulative. The only real protection against it is to take shelter. Now, let's review some of the outstanding facts we have learned in this brief exploration of a vitally important subject. Fallout is composed of trillions of particles of dust that are made radioactive by residue from the nuclear weapon during the aftermath of the explosion. In a nuclear attack, depend on your local radio station to tell you where fallout is taking place. You may be able to see some of the fallout dust when it reaches the earth, but you cannot taste, smell, or feel the radiation itself. The gamma rays given off by fallout are able to injure or destroy the living cells of our body if we are exposed long enough. Food or water in containers that prevent contamination by fallout dust is perfectly safe. Radiation is harmful only to living tissues. Packaged foods that have been exposed to fallout should be opened carefully. By following proper procedures, you can eat such foods without danger to health. Radiation can pass through most building materials, but its intensity is diminished in proportion to the weight and mass of the material or the shielding. The intensity also decreases with distance from the fallout. The radiation rate will decrease or decay rapidly with time. It is most dangerous in the first few days after explosion. Thus, the three basic factors that protect you from fallout radiation are time, distance, and shielding. You should know the location of the nearest public shelter in your community. Inside it, you will be at least 40 times safer from fallout than you would be outdoors. And it has been stocked with supplies to sustain its occupants for up to 2 weeks. If you're not within walking distance of a public shelter, you can provide a satisfactory home shelter for your family. Radiation is invisible, but we have accurate instruments with which to measure it in Roentgen units. The dosimeter can be worn on the person and measures the accumulated radiation exposure, the total dose at any given time. The Geiger counter measures radiation in fractions of Roentgens per hour, inside or outside the shelter. The survey meter is used to measure the higher intensities of radiation that may be present outside the shelter. Assuming that you have the protection of a good shelter within a half hour after nuclear attack, you will probably have little or no radiation sickness. If there are victims who appear to have radiation sickness, do not diagnose. Treat the symptoms. Perhaps the most important thing you have learned is to see the danger in its true perspective. Make no mistake, nuclear attack would be a terrible catastrophe. Millions of our people would be killed by the initial blast and heat. Millions more would be threatened by death from radioactive fallout. But that is a threat that can be combated. Can, with knowledge, preparation, and courage, be faced and conquered.